distinguished invitees, speakers, delegates, and my dear colleagues. Good morning to all of you. I hope that your stay at Tarapur was comfortable and memorable. I welcome all of you to the second day of this third Dae-Brns National Symposium on recent advances in nuclear fuel cycle activities, NUSUC-2022 at Tarapur. So in today's program list, we have a total of 4 technical sessions, a parallel poster session for offline and online poster presenters, and at last we have a small valedictory function. So without wasting much time, to begin with the first technical session, I request Shri P.G. Dae-Brns sir, Head Radio Metallurgy Division BRC Mumbai, to chair this session, and Dr. T.P. Valsala, Superintendent NLPO Lab FFI NRPO, to assist with him as secretary of this session. And I request them to please conclude the proceedings of this session as per the allocated time. We have extraordinary speakers in this session. The first invited talk is by Dr. K. Anand Sivan, Director, the Processing Group, Indira Gandhi Center for Atomic Research, Kalpakkam. Second by Dr. Vivekanand Ken, Director, Materials Group, BRC Mumbai. And third in the line, Shri D.B. Sathi sir, General Manager QA and AGMFF. Now I hand over the proceedings of this session to session chair and secretary, and there is one important announcement for the poster presenters. Please remove the previous day posters so that we have to prepare for the poster presentation of today's poster session. So that is all from my side, and now over to session chair and secretary. Thank you.
Thank you, Dr. Patil. Let me first recall yesterday's session in brief. They were very nice lectures yesterday, followed by a very nice cultural event, and I think the lectures, as they have enlightened the knowledge of all the delegates, definitely the cultural program also must have given a lot of enjoyment to all the delegates. Now today is the second day of this NUSUC-2022 conference. Let me invite Dr. Krishnamurthy Anandashivan for today's first talk, and I have pleasure in introducing him to the August gathering here. Dr. K. Anand Shivam is he is an outstanding scientist and he is director of reprocessing group. He has postdoctoral done from Purdue University, IN USA, and PhD in chemistry from University of Madras. He has got many awards in his credit. Few of them I tell you. DA Group Achievement Award 2020, DA Group Achievement Award 2013, and Homi Bhabha Scientific and Technology Excellence Award 2009. And he is President of ENCAS, IGCAR Kalpakkam chapter also. And here this is the seminar which is being hosted by ENCAS Tarapur chapter. So with this brief introduction, I request Dr. K. Anand Shivam to deliver his technical talk. I hope the timing given is 30 minutes, and then 5 minutes for question and answer. Yeah. Dr. Anand Shivam, please.
Thank you very much. A very good morning, Mr. Chairman, and a very good morning to the august audience out here. It's indeed a matter of great pleasure for me to be here with you at this wonderful morning of this very eventful and nice conference, and also to be here with the fraternity of the NCAS, which is a very vibrant association, continues to do a lot of services for the nuclear technology and popularizing it and taking it to the students and the public at large. Today's talk titled The New Avenues and Challenges in the Fuel Cycle with Advanced Fuels with BRs will be, I wanted to chronicle the experiences that we have gained with all the young audiences in the young colleagues, scientists, technologists in the audience. I thought probably it will be worthwhile to ponder upon some of the aspects of the fuel cycle which had been very enlightening and which had given us a lot of avenues for doing research in terms of fundamental aspects and also highlighting how they were applied to the actual development of the carbide fuel. And it's indeed very important that we need to chronicle all this, whatever we have done so far at the Department of Atomic Energy. Probably this could be a prelude to all that. Well, I would like to place on record my sincere thanks to the current director of IGCAR, Dr. B. Venkatraman, and the erstwhile director, Dr. A.K. Baduri, and all the contributors from the reprocessing group at IGCAR, as well as from the materials chemistry and metal fuel cycle group at IGCAR. Of course, collaborators, as well as Professor K.C. Harikumar from IIT Madras, who had been instrumental in guiding many of our students as well. Of course, last but not the least, I would like to place on record my sincere thanks to all my students who made wonderful contributions to many of these works. Of course, when we look at the sustainability of nuclear technology at large in the world, and in particular with respect to our country, fast reactors are certainly very important because they, in addition to their fundamental advantages, they also give an additional bonus advantage, which is mitigation of the, which is basically the mitigation of the radioactive waste and the ill effects of the minor actinides, which are long-lived radioactive nuclides. So, through the minor actinides partitioning and transportation, as of now the only viable technology available with us, ADSs being a far-fetched ideal even today, the fast reactors would provide us a wonderful medium. Now, apart from the other two fundamental advantages in the fast reactor, which every one of you know, effective utilization and a very good breeding potential, the fast reactors are also efficient heat engines because they operate high temperature and provide you with higher thermodynamic efficiency. Well, incineration of minor actinides, as I told you, continues to be a very important, attractive aspect of the fast reactors. Typically, a fast reactor, which is at 500 megawatt electrical capacity, consumes about 15 tons a year of the fuel, heavy metal. And of this, if you could load something like 0.3 tons per year of minor actinide, calculating at about 2% of the total load, then probably you'll require two such reactors to incinerate the current level of generation of the minor actinides in the country. That tells us how important it is for us to have the fast reactors going for the future necessities of the country. Now, looking at the fast reactors themselves, they're viable, they're excellent because of the fuels that we use in them. And normally fast reactors demand different kinds of fuels, though the conventional fuel that's been earmarked for fast reactors is the uranium plutonium mixed oxide, MOX for short, and this is a wonderful place which makes all the MOX fuels, and also BRC makes all the advanced fuel for the fast reactors. Now, these advanced fuels are called so because they have definite advantage over the conventional fuel, that's a UPU mixed oxide, but yet they are to be commercially exploited. So they come in different forms, like the microspheres, coated particles, a variety of composites, metal-metal composite, ceramic metal composite, and ceramic composites. Yesterday we talked about the upgraded Apsara fuel. Again, that is a composite fuel, the dispersoid fuel. The monoliths, the coated particles, and granules, which are being perpetrated by the Russians, I would say, in a big way with the vibro packing of the fuels. And now, as far as the compounds are concerned, we could talk about the carbides, nitrides, carbonitrides, and metallic fuel. I know there's going to be a wonderful talk here later today on metallic fuels, but I will restrict myself to the work on the carbide fuel done entirely in the DAE and how that has taken us forward in terms of the advancement of science and technology. Once again, the advanced fuels are particularly very important because they have high thermal conductivity, high heavy metal atom density, and low light atom density, which reach to a higher breeding potential, which in turns reduces the doubling time, which is a very important index for understanding how efficiently the fast reactor is breeding. So now this is directly proportional, this is indirectly related to the specific power. Specific power is very high when you go for advanced fuels, therefore the doubling time comes down. This everybody knows. In addition to that, lower doubling time, we also have a larger negative shut-off margin, saying that the fast reactor is inherently very safe. And also, they have a higher burn-up potential, which means we can extract more energy, which means utilization is far better. Right, now coming to the fast reactor fuels that are being considered, of course the oxide is not an advanced fuel, but the carbide, the metal fuel and the nitride, the international reference composition for a fast reactor is uranium 0.8, plutonium 0.2, carbon with about 2-6% enriched uranium in the uranium component. So whereas we have used a different composition, namely 70 atom fraction of plutonium or 55 atom fraction of plutonium, namely the Mark 1 and Mark 2 fuels for NBTR. Why did we do that? So what is the science behind it? What's the technology behind it? Let's try to ponder over this. The major problems that are posed by challenges posed by the carbide fuel are owing to their pyrophoricity, extremely chemically reactive. They will catch fire, react with oxygen and moisture. Therefore, there are safety concerns related to it. Therefore, special lines have to be created, which are wonderfully done at BRC and in the nuclear fuels group. And again, the carbon to metal stoichiometry had to be understood before they could fix even the stoichiometry of the carbide fuel. Then the control of impurities, the oxygen impurities, is a very important factor as well. And finally, the carbothermic reduction methodology itself had to be standardized. So now, typically looking at the composition of the two Mark 1 and the Mark 2 fuels, you look at there's a difference in terms of the non-metallic impurity concentration, especially when you go from the Mark 2 to Mark 1, there is an increased amount of oxygen content which is very vivid here. We'll understand as to why this was done, how it was done, why we had to compromise, we had to have some kind of an impurity here, what is the limiting factor and what is the science behind it. Now looking at this is simple. First let me take why M2C3 as a problem, how it was addressed. So in the sesquicarbide content was absolutely essential because unlike the oxide fuel, with the burn up, many of the fission product elements form carbides, therefore the availability of carbon to the heavy metals is rather low. Because of which, when we go across this line, we will be slipping from here to here. Before I come to that, this is a ternary triangle and everybody knows an equilateral triangle, and these lines which are called as isograms, which are drawn in such a way it goes to the apex and the opposite base, these are nothing but constant composition ratio lines. So along this line, the simple property of the equilateral triangle, the perpendiculars drawn from both these sides would be bearing a constant ratio. In other words, if you had to define the Mark 1 fuel, you just need to draw this line and spot it on this line. So this is the line where the Mark 1 fuel could be represented, and as you go down, the carbon goes down away from the carbon is depleting. So then you fall into a region where the metal would form a liquid which is going to be very rich in terms of the plutonium, and therefore this could lead to a problem. Therefore, we cannot start from the monocarbide zone. Instead, we would like to start from a little bit of sesquicarbide, and that is how the sesquicarbide came into the picture. Second important aspect was when you compare the composition, normally we say U.3, Pu 0.7, but it is not same for the sesquicarbide. If you look at this line, which is again called as the tie line, the phase is in equilibrium. The sesquicarbide is always richer in plutonium, whereas the monocarbide is always richer in the uranium component. When you come to the other phase field, the carbide is richer in uranium, whereas the metal is going to be richer in plutonium. Plutonium has got a low melting point, and these are going to form alloys with the clad elements. Therefore, this would cause a melting and breach of the clad. So we could understand the composition using the isograms. We should understand the two-phase field. We could understand the plutonium segregation. All this is possible by a simple thermodynamic analysis. For simplicity, I have only taken the UPUC system. In principle, we should take the quinary system UPUCON, and there has already been done. Lots of calculations were done, both at BRC and much later at IGCAR, to define the fuel and its composition and the effects. Another very important aspect was the preparation of the carbide itself. One of the commercially best methods for preparing the carbide, though there are a variety of methods available, is the carbothermic reduction. So we take the mixer oxide, the mixture of the two oxides, and then mix carbon with it and make a carbothermic reduction. This reaction is not thermodynamically viable at high temperatures unless you remove the carbon monoxide. So the efficiency of the removal of the carbon monoxide will define this particular reaction. So it could be done in multiple ways. One popular way of doing it is by application of vacuum. Another way of doing it is by flowing in inert gas. So again, this had to be optimized. Once you have done all this, this is nothing but the flow sheet that was evolved for the first time. Even though international flow sheets were available for the production, this was first time done here at BRC. This is Dr. Chaitanya Ganguly himself sitting in the glow box and working in those days. Wonderful work indeed. He, along with Dr. Wolath from KFK, now it's become FK, the kern has been removed, Kenforschungszentrum at Germany, had made a wonderful technology, a technique by which we can measure the concentrations of MC and the M2C3, the monocarbon in the cis carbide phase, by using a rather non-conventional method, which is the XRD. The X-ray diffractions are usually used only for qualitative identification of phases, but then it was used for a quantitative assessment of the two phases. Otherwise there's nothing else that was possible. And this shows the photograph with the autoradiography of plutonium showing the even distribution, and this was somehow accomplished with great vigor and I would say with amazing technological superiority. So this is done. That's great. Now the next problem was, what is the major problem in the carbothermic reduction? The carbothermic reduction, we don't want to lose the plutonium during the reduction itself. So it looks very simple when you write the equation like this, but the equation is not as simple. It's much more complicated. During the process, some of the oxides of plutonium, the monoxide of plutonium, PuO, which is stable only in the vapor phase, can vaporize. So which means we're going to lose plutonium, which we don't want to do. Again, we do thermodynamic analysis of the plutonium carbon oxygen system for simplicity, and we graduate from this point. This is a point where we have the mixture of the oxides and carbon, and we want to go towards this where we have the plutonium carbide. If you could concentrate here, there's a small little region instead of a point. The point represents plutonium carbide, the region represents some oxygen dissolution into it, and that's pretty generous. So we're going to have always some oxide in the final product, that's for sure. Simple thermodynamic analysis tells us that. But then as you try to increase the temperature during the carbothermic reduction, what happens is carbon monoxide comes out and plutonium oxide comes out. If you remove the carbon monoxide, you're going to do carbothermic reduction. If you lose plutonium oxide, it's not good. So therefore these lines here, the black lines represent carbon monoxide, the red lines represent the plutonium oxide. So we always want to see the carbon monoxide pressures are more than the plutonium oxide pressures. These are the famous crossover points, and then when you do it at a low temperature, we see we have to live with this much of oxygen. This is oxygen content, this is the partial pressure, and oxygen content is about 0.25, which is not a great thing. But then if you jack up the temperature, you can reduce it, sorry, but the compromise is when you go up, the absolute magnitude of the pressures goes up, so that's not good. Therefore you'll have to settle for a lower temperature and effective extraction of CO without losing plutonium. So simple an analysis, but so important. So this is done very nicely. It's brought out in Dr. Chaitanya Ganguly's thesis, and these are discussed in greater detail, not in the papers but in those theses. I think it's very important we need to chronicle it. Much late, during those times when before the fuel was put into the reactor, they had to do an analysis whether it's going to react with a clad for the first time. AASA316 clad was used. So how to analyze this? So there should be a transfer of carbon from the fuel to the clad. So this could lead to clad carburization, which could lead to ultimately the clad failure, loss of mechanical strength of the clad, and so on. So this will be decided by the ability of carbon to get transported from the fuel to the clad. In other words, this is in thermodynamics, it's called the carbon potential, the ability of the fuel to lose or gain carbon. So this could be simply analyzed by taking the carbide and then reacting it with hydrogen to form methane. The more the methane is formed, higher will be the carbon potential, less the methane, less will be the carbon potential. This experiment was beautifully done by S.P. Garg et al. 1984-85. They made a closed capsule equilibration technique known as the isopiastic technique. Even though the uncertainties in that measurement was higher, but still that is a very valuable information with which only they could get the regulatory permission for charging the fuel into the reactor. Much later, 10 years later, which shows even currently this is particularly relevant, and measurements were made for only 1-2 compositions. Still we are yet to explore the entire gamut of compositions as far as carbide is concerned. I think there is still a lot of scope for work in this. So this is done by a different technique called the methane hydrogen gas equilibration technique. This is the experimental setup that is shown. So I will not go into the details of the experimentation. Just I would like to say that the carbon potential or the ability of release of carbon from the fuel depends on the relative stabilities of the two carbides, namely the sesquicarbide and the monocarbide. That's written here, and this is going to react with hydrogen, and that's going to give out the methane. Now if you look at the dependence of this carbon potential, whether it's really going to carburize or not, was a major concern. So now you do an analysis. These are all the lines here you see are theoretical calculations, and I see the 2 dots out here, the 2 dots out here, and the 2 dots out here are all the measured values. So that's all what's been measured so far. Still there's a lot of scope. So the news here is oxygen impurity is going to marginally affect the carbon potential, whereas it's a very weak function of plutonium content as well as M2C3 content, which is good news for us. So which essentially means the carbon potential is not going to vary, which means the transfer of carbon from the fuel to the clad will not be appreciable. So again, what happened subsequently? We took the fuel to 25, 50, 110, 155 gigawatt days per ton of fuel burn up, and then we examined at IGCAR the post irradiation examination. The fuel was done, the fuel clad gap was closed, and interestingly, no visible clad carburization. So the story was right. So whatever predictions, whatever experiments were made earlier, absolutely were found to be in correlation with the experimental observations done much later. There were also wonderful experiments done on melting point measurements of carbide, wherein Garg and others took a carbide, encapsulated in the ASI stainless steel tube, and then simply jacked it up to high temperature and then made it to melt, and then cut it open and saw what's happening. Nothing was happening. So they were very confident with that. They got the regulatory permission. That they also had a rough estimate of the melting temperature called the incipient melting technique. But it's a very difficult experimentation to do, but they did it with the limited experimental systems available. Therefore, better experimental systems has to be evolved and made, which was part of my work at IGCAR as well, along with my colleagues. So here we made, Garg himself had made a wonderful experimental system at Argonne National Laboratory during his postdoctoral times, and wherein he had made a technique called the spot technique, in which the sample is taken in a small crucible, kept inside another crucible called the neutron cell, which is closed with a lid. And this is a very interesting experimentation. You have to heat it by a non-contact technique. Then what happens is something very simple that we observe in our day-to-day life. When you sit inside a room during the night time and look at the window is dark. But when you go outside and look at the window, if it's illuminated, the window is bright. So if you keep a mirror inside the room, go outside and look at the window, you see a bright window, and at the center you see a mirror, and at the mirror the same window appears dark. Same thing happens when you take a metal and put it inside a cup like this and then allow it to melt. The metal melts and forms a mirror which reflects the image of this orifice as a black spot, and that happens during the melting. Therefore you have found out a beautiful technique for measuring the melting point. This has become a very celebrated technique called the spot technique, and there are a lot of other variants to it. So we implemented an experimental system at IGCAR with which more specific experimental mandate to measure the melting point of the Mark 1 fuel. It's already been measured. Mark 2 also we had completed. In fact, during those time they made the incipient melting. Look at the uncertainties, about 25. Here the uncertainties were plus or minus 3 degrees. So we are able to assess this. So a series of compositions, if you could make and continue, will be the first one after, I think it was Pascal or someone 1965 who had made the first measurements on the carbide fuel system at all. So there is still a lot of scope for us to continue, because soon I think the carbide fuel saga will be closed once FBTF ceases to exist and we are going to graduate to the metal fuels. So before that, I think we should complete and exhaustively all our experimental investigation, which is very important. And this experimental system itself took a lot of time to build, and this is a first of its kind, very similar to the experimental system used by Garg in Argonne National Laboratory, excepting that this is an all metal system. That was a glass based system. So this is much more amenable for high temperature experimentation. This could go up to more than 3000 degrees. Temperature is not a limitation. Now we are also trying to set up another experimental system based on laser heating, which was developed by Manara and Konings and ITU, and then that will be also able to take material to container-less research. Here the problem was the container. We had to make exotic crucibles out of thoria, and also all in-house made, and also carburized tantalum crucibles and so on. So this is another very important. In addition to this, we did not stop there. We did measure the carbon potential in other system using the same technique, which could be used for getting regulatory permissions for taking the reactor fuel to much higher temperatures. And we didn't stop with the spot technique experimental system. We continued to work on it. This could be extended for measuring the melting points of UZR, and the complete phase diagram, the solidus liquidus region, was done by a single technique for the first time. Even the raw data was asked by people like Chang and others who are very good in experimental thermodynamics. And we have also done the solidus temperature and the liquidus temperature of the UPUZR, which I hope will be present in the subsequent lecture. And a new technique was also discovered with which we can even go to sub-zero temperatures, still measure the melting point in such instances where the materials are highly reactive. So as many as 10 different binary phase diagrams or ternary phase diagrams have been investigated using this technique. This is a recent result obtained by my student on the zirconium aluminum system, and the entire solidus liquidus at this zirconium rich end has been completed. So this is a spin-off from the carbide fuel research. So in all, the optimized preparation and fabrication techniques could be done Detailed thermodynamic calculations could be done. The K ratio method was developed. Incipient melting was developed. Isopiastic equilibration technique was developed. The methane hydrogen equilibration technique was developed. A spot technique experimental system was developed. It was not just the fuel preparation. This is much more than science. So we will not look at the fuel cycle as simply a technology. It's more of a scientific ground. Coming to the closing the fuel cycle is very important. So now we should talk about the reprocessing, for which I am working for the past 3.5 to 4 years. So now the fast reactor fuel reprocessing itself is very different as compared to thermal reactor fuel reprocessing. So there are the key aspects of very high burn up, therefore the activity goes up, and the short cooled fuel that adds to the activity, specific activity is very high, and unfortunately or fortunately we have a variety of fuels to be handled in the prototype plant. You could see this. In fact, the Mark II is missed here. Even there are test fuel pin irradiations which are done, like for example 44% F-beta oxide fuel and so on. These are all very important for qualifying the fuel for PFBR. So all this had to be reprocessed now, and we have to evolve the technology for this. And also, because of the constraints that I have shown here, remote handling should become much more rugged and more robust as far as fast reactor fuel reprocessing plant are concerned. There have been a lot of changes, advancements of course in the thermal reactor reprocessing technology. Kudos to our team which has been working, the NRB team. Wonderful job they have done. But then we have to extrapolate it to this, and the mandate is again with them in the FRFCF, which I'm sure we'll be able to do together. And the containment is a major problem, whereas the huge cells in the thermal reactor case, they're only dynamic leak tightness is necessary. Here we have to do static leak tightness, which is very difficult, but I'm very happy to share with you we've achieved better than 0.05 volume % per hour in these things. So this is again the fuels. So to sum it up as far as the FBR fuel challenges in terms of the reprocessing, solvent damage is going to be very high. Therefore special equipment had to be developed, which are nothing but the centrifugal extractors, which have very less contact time. We're able to do the extraction with single cycle process, almost the wonderful decontamination factor. So that's been a surprise even to us. Dissolution gave a lot of problems. My first paper 1996 was on carbide to nitrate conversion as a possible head and step for carbide fuel dissolution. It was a big nightmare for all of us. Photocatalytic methods as well as chemical methods, everything was being tried in those days. Finally simple reflection with nitric acid solved the problem. This is amazing. So we could close the fuel cycle. That's a great thing. And criticality is a major issue because of the high plutonium content. Alpha containment, once again, just now I highlighted, that's going to be a major problem, which we again address very nicely. Fuel pins are slender. Unlike the thermal reactor fuel pins, we don't do bundle chopping, we do pin chopping. Therefore, the chopper has to be entirely different. Again, pyrophoric carbide needs argon flushing. The entire glow boxes, the containment boxes, we can't afford to have argon because that's not going to be possible for us. And soluble organic interference has to be carefully addressed, which was addressed. So, now, looking at the FBR fuel cycle or the reprocessing programs at IGCAR itself, we have a pilot plant facility at a 12 kilogram per year, which is currently operational. We have surpassed our mandate of 14 sub-assemblies, and 62 campaigns have been completed. Even as I speak to you, the plant is running. As far as DFRP is concerned, we have taken a lot of time to commission this, but I'm very happy to share with you, we have come to the 4th stage. After the water runs, acid TPP runs, we are at the uranium cold runs. We have just started that. And we are of course building another plant called the FRP, which is about 20 tons a year. This is being currently done by NRB with a technical input from the reprocessing group at IGCAR. So this is the phased method in which we have proceeded. In the earlier days, we started the reprocessing program in a humble way by reprocessing the J-rod which were discharged from Cyrus. And now, the entire cycle, this is the process flow sheet of the reprocessing is very akin to the thermal fuel reprocessing, excepting that there is the sodium cleaning and sub-assembly dismantling. These are not part of the thermal reactor recipe, and pin chopping is slightly different. Dissolution is okay, excepting that we have to address when it comes to carbide, the acidities are different. And fleet clarification, again, we don't use the back type filters, instead we use these centrifugal clarifiers, basically centrifuges, which are all indigenously manufactured. That is again a challenge. The technology was not available at that time. Feed conditioning, pretty much like the thermal reactor fuel reprocessing. And fuel solvent recycling, yesterday I was talking to the thermal reactor colleagues, that's going to be a nightmare for us because the solvent damage is very high. We are still working on it. Partitioning, we have no problem. Decontamination factors, we have no problem. So, now coming to the coral plant, of course, this is just the account on what's happening at the coral plant, which I've already just narrated to you. So, we are very happy to see that the plant has provided a lot of information for operations at both the DFRP as well as for upgrading to FRP. Now at the DFRP, these are the some of the photographs which I would like you to see to show, seeing is believing, therefore we have already commissioned. There's about 60 kilometers of piping, more than 8-9 complicated cells, all of them have been leak tested, radiometry tested. Now we are at the threshold of the cold commissioning. We just started chopping the uranium oxide fuel pumps. Now, in addition to this, again here, the technological advancements, there are a lot of scientific advancements as well. I will not be listing them here, though I will orally say them. But the technological advancement was, this is totally indigenously developed a chopper, like for the thermal reactor fuel as well. The dissolver was very different because titanium and stainless steel had to be explosively welded, they're dissimilar materials. This was achieved. And then we suddenly had a problem. The remote handling equipment, which was ordered at the cost of over 1.5 crore, was not found suitable. So within 15 days during the lockdown period, we developed in-house with our own engineers a very innovative remote handling system, and all that has been prototyped, they've been manufactured, installed, tested, and then documentation has been completed. So we are very happy that we could do it. Again, some of the problems with the ejector mixture settlers, which are used for the solvent wash, had a problem of the tud formation and choking. Therefore, we had to qualify it with modifying the design to air sparged mixer settlers, which are also again tested, and the aerosol generation was also addressed. So this has been again made, tested, implemented, and then documented. And again, another problem was the in-cell cranes are very different as compared to the thermal reactor fuel reprocessing. They had the VFD, the drives outside, and we have used ball screws for the first time, and they are all driven from outside. The sync was done electronically between the two different drive motors which drive the two shafts from outside. And another very important development is the LED lamp with a high lux capacity, 40 watts. And this was developed with a firm in Hyderabad. This is a special heat type cooled thing because the cavities do not have enough scope for cooling the lamps. Otherwise the lamp would fail prematurely. And of course we have about 8 patents so far. 3 of them have already been awarded. Another 5 are in the pipeline. So for different components with elastomeric seals and feed throughs, which are all indigenously locally done. And finally, we have also developed with the help of MMG the in-service inspection devices for both the dissolver as well as the waste tank form. And a lot of elastomers have been done, and we have interfaced with many of the companies outside. This is something very special, the polyimide based sleeves for all the cables. And also, sure.
Can you complete in?
Complete. Yeah, sure. I'm almost done. Thank you. So, and so on. And this has also been done. And now, what is the way forward? This is the last one. So, like already, there was a wonderful presentation of this. We have to, of course, take out the minor actinides, which have to go into suitable fuel form to be incinerated in the fast reactors. So, there are different methodologies that we could talk about. There's going to be another very interesting talk by Dr. Mohapatra in the afternoon. So, he will be elaborating more on this. But then, right now, we have been working on the TODGA and DODGA based. These two are the two molecules which have been developing. My colleague Dr. K. Venkatesan and his group have been working assiduously pursuing this, and they are coming up with solutions to this. We also plan to put up, if possible, in FRFCF a small pilot plant in which we will also start doing the minor actinide extraction. So that's all in summary. But what I want to say finally, the advanced fuel cycle is indeed a gold mine of problems for the seeking minds. So I want to again appeal to the youngsters that it is not just the technology, it is not the difficult technology, it is a lot of science. So there's a lot of scope for us to publish, there's a lot of scope for us to flourish in our career with the right kind of attitude. Thank you so much. Once again, on behalf of the NCAS chapter at Kalpakam SRC, I thank the organizers for this great opportunity.
Thank you, Dr. Nusum. It was a nice lecture in which the technology and science of FBTR fuel has been very nicely explained. Definitely, I think youngsters must have been benefited by that. Now the session is open for 2 or 3 questions because other lectures are there. So, any questions from audience?
Yeah, please.
Good morning, sir. I'm working in NUMAC, Nuclear Material Accounting and Control. So my question will be pertaining to that only. Reposing of fuel, that is fast breeder fuel. So where the plutonium intake is more, 21 to 29%. So what sort of modification we need to incorporate in our accounting system so as it should not quickly exceed my 1 SQ.
Okay, as far as the nuclear metal accounting is concerned, there is not much of a modification. Excepting that, the only major problem which always pops at the back of my mind is the actual accounting of the fuel as you receive it as a spent fuel. See, what we have to do is we have to refine the method of calculating the actual plutonium inventory that we receive. Most of the MUF you get only from the inaccuracies in the estimation of the plutonium that's present in the spent fuel or the used fuel as we call it. Other than that, in terms of the recovery, we have been doing pretty good. We are not throwing anything into the raffinate, beyond the set levels, and extra care is taken. In fact, some compromises even in the processes are made for recovering the plutonium at the last stage. But the two things, we need to quickly process the plutonium and take it out before it polymerizes and get stuck with the compensation. So the MUF in the plant, in terms of the whatever is the residues which is sticking around the plant, that has to be reduced. The hull has to be perfectly cleaned. All that we have taken care. But the only uncertainty that remains is a very good method for estimating the actual plutonium content, which is still defying us. I think we should use other methods like the radiometric techniques or any other technique for that matter, where we'll be able to do a more accurate estimation.
So my question was that presently we are using isotopic dilution mass spectrometry as a tool for input accounting,
Right.
and that is the robust method as far as
Correct.
reposing facilities are concerned.
Right.
But it has its specific accuracy and precision, 0.2%. So even if we take that 0.2% and my plutonium intake is high, very very high compared to PSW or reposing fuel, so within quick time, with no time, we will exceed that 1 SQ. So my approach will it be possible to go for a dynamic inventory system incorporating in our reposing facility?
Dynamic inventory system is possible, but there are two things in terms of the answer. I have two aspects to answer you. One is the major uncertainty is not in the analytical uncertainty alone. The major uncertainty comes from the inventory filing itself. You do not know what the inventory is, to be exact. So till date, they say 533 something XYZ, some number, whatever number you give. I don't know whether that much plutonium I'm taking in. And finally, I am making all the inventory based on my dissolved solution. Again with isotope dilution mass spectrometry. That's all. That's the first number I get in the plant. So am I okay or am I not okay? I don't know. So this has to be first fixed. This is going to be a major problem. Isotope dilution mass spectrometry, yes, you can have online techniques, specific techniques. Their analysis can be improved. That is not an issue. To me, that's not a serious issue. That can be addressed. There is even online monitoring like LIBS have come in. We can LIBS, laser-induced breakdown spectroscopy, which you can do interventions at the lines, at line and online you can do. That's not a problem. The problem is much more serious with respect to the inventory control.
We are already running short of time.
Sure.
So other questions from audience may be discussed with Dr. Anandshivan because he is available whole day here. And thank you very much, Dr. Anandshivan.
Thank you very much.
Now we switch over to next lecture. Next lecture is by Dr. Vivekanand Kane. I briefly introduce him to all audience. Definitely he is also a well-known figure in PRC and DAE. Dr. Vivekanand Kane is a metallurgical engineer and has been working in BARC since 1986. His research areas include corrosion of materials, performance of components in operating plants, failure analysis, and providing metallurgical and corrosion support to operating plants. As Head Materials Processing and Corrosion Engineering Division since 2016, Dr. Kane has steered the R&D programs on uranium, rare earths, e-waste recycling and refractory materials at BARC. Dr. Vivekanand Kane is an outstanding scientist and Director Materials Group at BARC and steers the R&D programs of BARC related materials. Dr. Kane is Fellow of ASM International, NACE International and Maharashtra Academy of Science and recipient of VASVIK Award in the field of materials and metallurgical science and technology. So we are very happy to have you for this talk and request you to deliver. Dr. Kane, please.
Thank you, Mr. Chairman. Good morning to all of you. What I am going to talk on is materials which are used in very aggressive nitric acid applications. I will be explaining to you why I am calling highly aggressive nitric acid applications. Nitric acid by itself is aggressive, but it can become much more aggressive in the plants of where we do the reprocessing and waste management of spent nuclear fuel. The specific topics on which I am going to focus in this talk are going to be what are the key factors which lead to degradation in the plants where we handle nitric acid as the process fluid. So basically reprocessing and waste management plants. Within that, I will not be able to go through all of those degradation modes which are there for materials of construction, specifically stainless steels, but I will focus on what is the effect of halides, specifically chlorides and fluorides, which are present in these plants. If they are present, what will be the effect on degradation of stainless steels? Then what I defined as highly aggressive nitric acid application is when that nitric acid with higher concentration and temperature has either fission products or corrosion products which are in higher valence state. If they are in higher valence state, this becomes highly aggressive and the corrosion degradation of stainless steels becomes much more accelerated. What are the control strategies to take care of these aspects and whether we are looking at alternate materials, alternate to stainless steels? So what are the operating conditions here? Operating conditions are that we have concentrations, different concentrations of nitric acid at temperatures up to boiling point. We do add in the process certain chemicals. We have cyclic heating going to boiling and condensation also. Condensation also leads to number of factors which lead to degradation. But then concentration buildup of fission products as well as corrosion products in certain components where we do where we have number of cycles of concentration of the process fluid to reduce the volume of that. Similarly, in waste management, we have those aspects which make the process much more aggressive to the materials of construction. So what are the key issues of degradation in plants which use nitric acid and stainless steels as the material of construction? The first and the foremost is intergranular corrosion due to sensitization, due to welding it comes sensitized zone in heat affected zone. This is the classical form and we try to avoid it by proper material selection, a robust quality assurance program implemented for these plants during fabrication itself. That takes care more or less of this issue. However, inside those components, certain components will be prone to end grain attack. End grain attack is where from the cross-sectional surfaces like ends of the tubes, the intergranular corrosion would attack even in a non-sensitized stainless steel and it will go deeper inside. So those components which have the cross-sections exposed to the nitric acid fluid would be prone to this. Crevice corrosion, certainly crevices by itself concentrating the ionic impurities in the nitric acid and also the higher valence ions which are present in that. So crevices, whether they are in the weld or by design, we have tube to tube sheet joints, etc. If that is operating, concentrating those ions, then there is going to be more degradation at those joints. But then nitric acid in condensate phase is much more corrosive than in the liquid phase, and that remains an issue, is tackled by the process parameters itself. And this is the topic on which I am going to talk to you more in this presentation. So this is a typical intergranular corrosion mode which happens due to sensitization. This is the end grain corrosion typical attack which happens on this. Coming directly to the effect of halides. Halides, both chloride and fluoride, what does it do in water, aqueous phase? Not in nitric acid, but in aqueous phase. There are lots of studies reported. Stainless steels, particularly austenitic stainless steels, are highly prone to localized corrosion when chlorides or fluorides are there. Here, the chloride content as low as at neutral water conditions, stress corrosion cracking at these levels is very much possible. So material stainless steel will crack by stress corrosion cracking if in water you have 10 power 5 ppm. But in acidic condition, you will have even at 60 degrees Celsius 10 power 4 ppm of chloride causing cracking. That is very much feasible. It is in long-term exposures, about 1 year of exposure. But if you come to lower pH condition in aqueous phase, even 100 ppm is able to cause pitting. 1000 ppm certainly causes pitting to austenitic stainless steels. So pitting and stress corrosion cracking in aqueous environment, non-nitric acid aqueous environment, is a very well known phase, modes of degradation. There are number of studies done where it is shown that compared to solution annealed material stainless steel, which pits at a given potential, the sensitized material will pit at a much lower potential. So sensitized condition of stainless steel is much more prone to pitting compared to solution annealed condition. These are very well known facts. So this annealed material showing pitting potential with a level of chloride. So even 100 ppm will be able to cause that pitting. Let us see what happens in nitric acid. 65% nitric acid, practice C. If we do those particular tests, but in this time, let us add certain levels of chlorides or fluorides, different levels. So nitric acid, we have now with us stainless steels which show less than 10 mils per year corrosion rate in practice C. Now without any addition, now we add fluoride here. You add even 500 ppm of fluoride and the corrosion rates jump up, very high corrosion rates. So we did not proceed further even to complete 5 cycles of the test. But with chloride, let us look here, even 500 ppm chloride to 3000 ppm chloride, the corrosion rates are in the same range as they were in the practice C condition where no addition of halide was done, no addition of chloride was done. So practically no effect of addition of chloride up to 3000 ppm in 65% nitric acid. Nitric acid is a highly passivating agent to stainless steel, and that is, these are the two opposing effects. The chloride tries to break locally the passivity to cause pitting, but nitric acid reinforces the level of passivity. These are the conditions after the test. This is where only nitric acid test was done, no addition. This is where chlorides of 3000 ppm were added in the test. A black layer has formed on the surface, but no increase in corrosion rate. And this is where 1500 ppm fluoride was added and we got whitish layer. Heavy uniform dissolution happened here, whitish layer formed, but at the same time from the cross-sectional surfaces, pitting started. Not on the longitudinal surfaces, but on the exposed cross-sectional surfaces, pitting corrosion started in case of fluoride. We did lot of experiments in the lab to understand the mechanism of that, and we were able to see that in lower concentration, 1 molar nitric acid here, if you are adding smaller concentration, you are having the current density in the given range, but as you increase the concentration of chlorides, the current density increases. That means the level of dissolution increases. This is, mind you, only uniform dissolution level which is increasing. Similarly, if you increase the concentration of nitric acid in 6 molar, these effects are lower because the passivating power of the acid is much more. But still you are able to notice increase in the uniform corrosion rate only. It did not result in pitting corrosion in this case. Similarly, acid concentration effects or chloride addition effect, when we do with 6 molar nitric acid up to 3000 or 1 molar and 6 molar, acid itself has a great influence on the corrosion behavior of that. Finally, we came to levels which are tolerable in nitric acid. Tolerable under those conditions of nitric acid concentration like 1 molar, 3 molar and up to 6 molar we went, where if we add 3000 ppm of chloride, we find that the uniform corrosion rates, there is practically very narrow band in which there is a movement in that. Whereas if you go to 6000 ppm under those same conditions of molarity of nitric acid, then the increase in corrosion rate, uniform corrosion rate, is substantial. So 3000 ppm appears to be a uppermost limit in which you should be able to tolerate chlorides. Let me come to the actual corrosion rates in these concentrations. 1 molar, 3 molar, 6 molar, you will find the corrosion rates are very, very low, in the range of 1 to 2 mils per year only. And there was no observation of any pitting or stress corrosion cracking in these. So based on these studies, when the matter was referred to us by the plant, quite some time ago this was, that time we had recommended, and now it is being practiced, that we should not have an issue with even 1000 ppm of chloride, and that was based on, I will show you here, 0.5 molar, 1 molar, 3 molar, 6 molar increasing levels of chloride concentration. Based on these values, we recommended that we should not have an issue positively if you are exceeding 1000 ppm, but certainly you should be below 3000 or 1500 ppm to be the uppermost limit. Literature also shows you that, but at lower concentration of nitric acid, say if you are lower than 1 normal of the nitric acid solution, the same levels of chlorides are able to cause pitting and even result in stress corrosion cracking. This has been reported from some studies done in the lab as well as from the plant observations. Higher the concentration, more is the tolerance to chloride levels. Fluoride, on the other hand, increases the uniform corrosion rate drastically. There is a big shift in the uniform corrosion rate. If you are adding only 1500 ppm of the fluoride ion in, say, 6 molar nitric acid here, we took the hull basket as fabricated condition, and it has square cross-section wires which are welded in this hull basket condition. We exposed to 65% nitric acid containing sodium fluoride, a given concentration, and the similar kind of test was done, and what we found was only in the cross-sectional surfaces, these are those square wires which you are seeing, only in the cross-sectional surfaces the observation of pitting had started. Pitting attack started only in the cross-sectional, longitudinal surfaces were not affected. This is a study done by Sandeep Sathe, who had shown that if we take 9 molar boiling nitric acid, corrosion rate remains with time in this particular low range for stainless steel. But if we add 0.03 molar sodium fluoride, corrosion rate jumps up very high. This is high uniform, we say metal polishing effect due to fluoride. But you are able to complex the fluoride ion by adding certain other metal ions who have more affinity to fluoride compared to iron. So you have aluminum here studied as one, zirconium itself is there. So in our reprocessing, we already have either of these ions, and therefore tolerating fluoride is also not an issue if we have these metal ions present in the process stream. Let me now come to the second aspect of the talk which I wanted to show you, which is that inherent limitation of stainless steel in highly aggressive nitric acid condition. What is that? Typically, when we take 65% nitric acid, the operating potential remains in this particular range, in the passive region for austenitic stainless steels, in boiling acid also. This is the tolerance limit in terms of the operating potential which stainless steel has in the running plants. That means whatever will be able to push the potential from this value to this transpassive potential, that will push the material to undergo intergranular corrosion even if there is no sensitization. A annealed stainless steel also will start to undergo IGC if you take it to this transpassive potential. We had a setup developed and then we did lot of detailed studies. We studied the effect of temperature, effect of at a given temperature, effect of the molarity. Increase the molarity of acid, the operating potential shifts up towards the transpassive potential. Increase the temperature also, or this is at a higher temperature, 95 degree. Here you will find that very soon, if you take it to 6 molar, you are very close to the transpassive potential. So the margin to have other ions present in the solution which will push the potential to the transpassive potential is very little with higher concentrations of acid. Similarly, if you add these ions, these are corrosion products. In nitric acid, higher valence is present. They also push up the operating potential in addition to the increased concentration and increased temperature which pushes up the potential. So with increasing concentration of these ions, so components such as thermosiphon, where you have increasing concentration happening with each cycle of concentration, this value goes on increasing, as well as that of other fission products. They all push up the operating potential towards the transpassive potential, and that is what happens the moment for stainless steels you reach this transpassive potential, operating potential, you end in a regime which is intergranular corrosion, whether the material is sensitized or it is not, or it is solution annealed. This is the inherent limitation of stainless steels in these processes, Purex process or nitric acid handling plants. Below that operating potential is only uniform dissolution happening. So above that transpassive potential, even solution annealed material is corroding in intergranular mode. Below that potential, it is having a passive layer and no such selective corrosion is happening in that material. What is the effect of using different alloy compositions, stainless steels? Very little effect on the transpassive potential. Very little value change if I change from one to the other alloy in this case. What is the effect of microstructure? Again, very little effect on the transpassive potential regime. So it doesn't help me much if I change the alloy or if I change, let us say here, grain size. If the grain size is very fine, the corrosion rates due to intergranular corrosion will be very, very high. But as I make it coarser and coarser, I will get lower and lower of those effects, intergranular corrosion effects, but it will be there. With time, it will catch up. Similarly, with the concentration of acid, higher the concentration of acid, there will be some improvement or some more tolerance level is getting added in terms of operation, but then that is also very limited, from around 910 millivolts to around 980 millivolts. Slight increase in margin is there, but then we operate our components at a given concentration, so we are limited there, we cannot change it that freely. Grain boundary engineering is another aspect which has been told, but then grain boundary engineering slightly improves the tolerance towards the transpassivity. Slight improvement in terms of corrosion rate in a grain boundary engineered material compared to commercially available stainless steel. But in our process, we have all of these ions, higher valence ions, which take the potential beyond, let us say, 975 millivolt, which take it to much higher in that potential regime. And that is where we need to be careful that we should not be concentrating those ions in our processes to a level that I am getting potentials above the transpassive regime of the stainless steel. So stainless steels do have these inherent limitations. Slight improvement comes by grain boundary engineering or alloying, but very slight. Therefore, we should develop techniques and be able to monitor electrochemical operating potential during service and stop further cycles of concentration so that we are not entering into transpassive limit of potential. And try out alternate materials. If they work out, That will be a very big advantage against this mode of degradation. Other than these ions which I talked about, in the process we also add certain other chemicals like formaldehyde. Formaldehyde addition, the moment I do at this particular level, the potential is here, the potential jumps. So it also takes you closer to transpassivity. If you are using formaldehyde in the process, it will take you closer to higher and higher corrosion regimes. Hydrazine on the other hand is reducing the potential. It is giving you some advantage, and same thing in quantitative term is shown how much potential increase is there by adding formaldehyde or hydrazine. Let me now come to the third part of the presentation, which is looking at alternate materials. How do we tolerate those highly aggressive conditions in the operating plants? Can we use certain alternate materials? So we have these thermosiphon evaporators which are there where number of cycles of concentration do take place, practically 2 to 4 molar of nitric acid, but then number of ions are there in that, and we go for boiling in that, boiling and condensation. We looked at, other than the stainless steel which is used conventionally, we looked at these two other aspects. There is a task force in BRC to work on this. They are getting it fabricated, these evaporators, which are made from, the tubes are made from either zircaloy or titan, a titanium alloy which is developed in DAE itself for its own internal application, that is being sought to be tried out. Now decision has been taken after a lot of detailed testing done. Here the corrosion rate or current density is given at the same scale. You will find zircaloy has the current density, this is in 1 molar nitric acid, and blue one is in 4 molar. All total tolerance to the increase in concentration for zircaloy, it remains in the transpassive regime, which extends up to 3 volts compared to stainless steels where less than 1 volt is the transpassivity. So even if you go on adding these ions, highly aggressive ions, making it more concentrated, the potential in stainless steel, the moment it crosses 1 volt, will lead to degradation of stainless steel, but not in case of zircaloy, because the passivity remains up to 3 volts. Huge advantage. Similarly, for this alloy Titan 24, the passivity remains up to same volt, 3 volts. Similarly, if you do with 4 molar, so from 1 molar to 4 molar containing these ions also, you have the same advantage. Zircaloy showing you lowest corrosion rate, followed by Titan and stainless steel corroding very fast. These are the actual rates where 3 molar nitric acid, 48-hour exposures to boiling nitric acid at those very high potentials. These are the potentials used much into the transpassive regime for stainless steel, beyond 1 volts. So stainless steel even at 1 volt at 95 degree gives you such high corrosion rate, intragranular attack. Simply grain dropping starts in that. But at much higher potential than that also, all of these alloys at temperatures close to boiling or at boiling are giving you very, very low corrosion rate. Look at zircaloy, practically no corrosion rate there. Even the other ones are giving you less than 1 mils per year. These are the materials which remain in those highly aggressive nitric acid condition, highly resistant and in passive state. They don't show any kind of degradation. What about the 3 phases of the liquid nitric acid? Whether it is in liquid phase, whether it is, so liquid phase exposure is in this, then you have condensate phase in this area, and vapor phase is exposure is in this area. This is the condensate phase. So let us see the behavior in all the 3 phases for these 3 materials. What comes out, simple exposure in boiling nitric acid 4 molar tells you that stainless steel has a given behavior, say liquid here, condensate here and vapor phase here. But Titan shows higher corrosion rate in liquid and also in the vapor phase as well as in the condensate. Zircaloy shows minimal rate in all the 3 phases. This is only 4 molar nitric acid. Not highly aggressive, but normal condition of 4 molar nitric acid. But you add ions in that, make it highly aggressive, potential is taken to higher state, in that case you will find, I will show you the corrosion rates also, the behavior of titan also improves when you go to highly aggressive conditions. So you have that behavior that if the concentration of ions is not there, you have very high corrosion rate in titan, but the moment you add these ions and increase their concentration, the corrosion rates are very low. So here chromium 6 ions are added and similar work has been shown. Stainless steel in all those conditions is showing you aggressive intergranular attack. It's simply crumbling there. But the other two alloys are remaining in highly passivated state. So these are the corrosion rates. Look at the corrosion rate in liquid when I am taking only, here it is 65% nitric acid, 8.8 compared to titan showing in aggressive condition practically nil, non-measurable corrosion. So titan resistance increases when the aggressivity of nitric acid is increased. Similarly, I increase the aggressivity further by increasing the amount of these ions which I am adding. That means the operating potential is taken further up from 1 to 1.2 volt to 1.5 to 1.7 volt. Stainless steel in 1 volt also will not withstand, but look at the corrosion rates here. Negligible corrosion rate for titan. Zirconi you look at, even much lower than that of titan, but stainless steel certainly shows you very high corrosion rate. So stainless steel here 80 mils per year, here 342, compared to that you look fraction of a mils per year. So these two alloys are the most potential materials of usage for these highly aggressive conditions. I will not go into further detailing, but just describe that this task force I mentioned, which is operating in BRC now, that is getting these two evaporators fabricated with these two alternate materials. There are a lot of challenges in that fabrication. Dissimilar joints are there, whether titan to stainless steel or zirconi to stainless steel. Explosion welding is being done, and we are on the road very well to have these two fabricated and put it in service to observe whether these behave much better than the stainless steel made evaporators. So these are the I would say two major things which can happen to avoid the issues, the degradation issues which we face today in nitric acid handling plants. And our understanding of the issues, possibly we have the full understanding in that. It is only now implementing in the plants how to totally avoid the issues which today we face from now and then, and in very few of those components. Otherwise, I must compliment the operators, the entire team which manages these reprocessing and waste management plants, that despite working in such highly radioactive and chemically aggressive conditions which are operating in these plants for the materials of construction, that it has been so nicely managed that safe and smooth operation of the plants is happening in our department. With this, I will close this talk. Thank you, Mr. Chairman.
Thank you, Dr. Kensab. It was a really nice topic to discuss here, because reprocessing plants are facing very serious problems in the equipment there, and I hope your studies will definitely come through to help the reprocessing plants. Now the session is open for technical questions. Some one or two questions we can take up.
Sir, such a very interesting talk. Sir, just I wanted to know, have you studied stainless steel LN for this intergranular stress corrosion?
So there is lot of literature available, our own data available. LN or whatever other variant of austenitic stainless steel will not offer any resistance, additional resistance to this mode of degradation which I said. LN will improve the resistance to sensitization we are not talking of sensitization induced degradation. We are talking of even in annealed condition material undergoing high intergranular corrosion. So all austenitic stainless steels have that inherent limitation on its usage in these conditions.
Sir, Ganesh here. It's very nice talk from you regarding corrosion. Sir, in Kakrapara Loka incident, it is attributed to nodular corrosion, I think. Can you throw some, because it is involved with zircoli.
So we did investigate in depth those issues in Kakrapara. They are very different than what I am talking here. What I talked here is stainless steels, that to the issues with austenitic stainless steels in nitric acid medium. Kakrapara issues are were with pressure tubes in the annulus gas, certain contaminants, possibility of contaminants which could have led to nodular corrosion and then led to the cracking of the tubes. So I think we should not try to bring that issue here. These are two very different aspects, and on that separate issue maybe another talk for 1 or 2 hours can be scheduled.
One question from backside.
Thank you very much, sir. Sir, actually, I have one doubt. This regarding corrosion. So, as we know, corrosion is a electrochemical process in which a metal get oxidized. So, in the we know this nitric acid is a oxidizing medium, and it will oxidize the metal from metal reduced metal means metal to oxidized form. And when you are adding HCl, which is actually reducing agent, we are saying that in your data this corrosion rate is increasing multifolds. What is the chemistry behind this, sir?
So because of paucity of time, I did not elaborate on a couple of slides which were there. There is sufficient data that in nitric acid, which is a passivating agent, which strengthens the passive film on stainless steels. So anything which is strengthening the passivity of the material will impart resistance to these ions which try to cause localized damage to the passive film. You have higher and higher concentration of nitric acid, more will be the strength of that passive film. Passivity will be enhanced on that. To break that passive film locally by these chlorides, especially chloride, I am not calling it fluoride now, by the chloride, you will have to have more and more concentration of that chloride required in order to break it locally. This is very well known. These are actually modeled also. Everything is known in that. Even rates are known under certain conditions. So as you increase the concentration of nitric acid, you can go on tolerating more and more levels of chlorides. But if you are having, as I showed you in the electrochemical runs, the corrosion rate in the passive potential regime, that increases, and that is because the moment M and Cl, they form a bond that immediately reacts with water to form hydroxide, metal hydroxide. That is able to lead to increase in corrosion rate locally, but is not able to, that reaction is not able to continue at a given point itself, at a given, say, grain boundary on that surface. That is not possible because by the time nitric acid again comes and passivates it. If the reaction was able to continue at the same location, we would have got a pit there, pit initiation. So pitting in absence of these nitric acids, passivating agents like in aqueous solutions, proceeds with that particular mechanism. Same reaction occurring at the same location, other locations remaining passive. Here that is not possible because this location also gets passivated by the remaining nitric acid.
Thank you, sir. Thank you, sir.
Thank you very much. The team is available for some more time. If any questions are there, they can be discussed personally or mail can be sent to him. He will reply to that.
On behalf of NITESH, on behalf of NITESH, May I request chairman of the session to present a memento to Dr. Keynes.
We move on to next lecture of this session. I invite Sri D.B. Sate from FFINRPO. Mr. Sate has joined department in 1994 through 37th batch of BARC training school batch. He is now holding the post of Assistant General Manager, Fuel Fabrication and Technical Services, and General Manager Quality Assurance at NRV BARC Tarapur. His field of interest are non-destructive testing specialized in X-ray radiography and digital radiography. So I request Mr. D.B. Sate to present his technical talk.
Thank you, Dae, sir. Good morning to all of you. At the outset, I would like to thank my superiors, earlier superiors, as well as my colleagues who have developed this, who have carried out this development. I am just presenting on behalf of them. Actually, in our A3F, this PU2 was introduced around in 1993, and since then we are into fabrication of MOX fuel for mainly all kinds of reactors in DI, and we take pride in that also. We have fabricated nearly MOX fuel for all the reactors, research, thermal, fast. These are our achievements. This is very common flow sheet, you might have seen it earlier. Central is mainly our processing steps, and right hand side is mainly, right hand side and slightly left is mainly our quality control steps, which ensures the quality of fuel. Actually topic is vast, but I would like to talk only on the advancements in various sections which have been made in last 5 years. You may find some repetitions also. Actually, as far as oxide fuel is concerned, mainly our developments will be oriented from glow box point of view. That is one restriction on us, from maintenance as well as operation point of view. In especially up to pelletization, whatever equipments we are using, the press is a central to that. So we have carried out lot of modification in rotary compaction press, which is used for compaction as well as for pre-compaction. These are list of some of the modifications or changes we have made. Actually, earlier we were using D3 material, we shifted to D2, which is comparatively tougher one. Then to achieve more wear resistance, we have provided PVD coatings. Right now we are working with CRN coating, that is chromium nitride coatings, and we are continuing trials with titanium nitride, aluminum titanate nitride, which have already been loaded on the press, and we are just studying its performance. Then we have varied the heat treatment, starting from vacuum hardening, cryogenic treatment, then multiple cycles of tempering to achieve the toughness as well as wear resistance. We have shifted to tungsten carbide dies. I will show the photo also. Then smaller modification, we have provided countersunken die for strengthening the tool neck. That is, just by lowering the neck length, we are strengthening this particular part. This is that countersunk, and because of that, this length, which is the weakest part in the tool, it is reduced. specific to bottom punch. Then previously we were using brazed rods, but by using this better grip, by using this grub screw of higher diameter, we have ensured that core rod will not come out during compaction. These are the few punches, bottom and top. This is the core rod. This is the core rod which ensures the annular pellet. That is the mechanism by which we get annular pellet. And here you can see two different appearances. Center one is actually tungsten carbide, which is act as an insert. And this is what I was referring to, countersunk. These are the just theoretical comparison of different PVD coatings. This particular coating has given us very good results, and we are now trying with these coatings also. This is anyway from literature only. You can see the surfaces after compaction. This is uncoated punch face before production cycle. This is after production cycle. This is after CRN coating. Before production, after production, the deterioration is comparatively less. Yeah, this is what I was referring to, tungsten carbide dies. This is the tungsten carbide insert. Actually, the idea of tungsten carbide, it is having very high Young's modulus, and thus the elastic expansion is very less. As our formulation is very abrasive and sticky, this helps a lot. Yeah, second equipment what we are using is, earlier we were using granulator. This is to basically to increase the flowability of the powder. But now we have modified, it is called rapid sifter. The literary meaning of sifter is sieving. But this term has been coined by our colleagues in A3F. Actually, this particular equipment is used for two purposes. One is for PU to powder sieving, which ensures the we will not get any agglomerate greater than our accepted limit. That is one idea. And second, as I told you, as a granulator, it ensures the flowability of powders by increasing the size of the powder, that is aggregates. So these are the advantages of using this sifter. You can see, as I already told you, from Glovox point of view, whatever developments we have made will always ensure easy maintenance, then reduction in dust, reduction in man rem, all these parameters will come in picture. This is again the photographs of that. By this, what we can see, it is, as far as cost is concerned, it is very, very less expensive. Then the time, it is only 1/5 what we used to take for granulation. I will show the photo of granulator also. Yeah, this is that used granulator which was put inside the glow box. The maintenance of this was also very difficult. And if you compare, this is rapid sifter. The size, weight, it is very easy to maintain. The time for maintenance is also very, very less. If you see the productivity, it has increased by 5 times. This is another equipment. This is used for coating of powders, especially for DDU2 powders. We are using solid lubricant. So this is a kind of coating machine which we are used. This is also very small. It is easy to bag in and bag out. In online condition also, means existing glow box also we can use this machine. Third problematic machine was grinding machine. Earlier we used to have very big machines with very high RPM, and that used to have vibration on glow box and so many sort of problems there. But now we have introduced mini centerless grinding machine, which is having all these facilities. We are using VFD here, VFD drive for regulating wheel. Then since the speed also is reduced, the dust generation is also reduced owing to less man rem problems. So many benefits we have received. Then one more advantage is this grinding wheel can be replaced inside the glow box also. That is a big advantage. Then next development was we are using this double window. Actually earlier single window whatever we had earlier, it used to get deteriorated and visualization was difficult. But by using one sacrificing glass which can be changed very easily, we have improved the visibility also. This is again the mini centerless grinding, and with that we have introduced some part of automation also for feeding the grinding machine, like linear feeder, ball feeder, etc. etc. This is that secondary window which I was referring to. It is another window from inside which can be changed easily. This is chain pulley arrangement for lifting this grinding wheel, whatever it is. This also advantage, as I already told you, size reduction, cost reduction. Yeah, whatever rejects we are generating, many people have talked about CRO and DRO. Whatever CRO has been generated, now we are, earlier we were recycling by wet route, which we face lot of problem with HNO3, corrosion of glow box line, etc. etc. Now we are shifted to even dry recycling route, where some temperatures and gas adjustment have been done, and we are successful in recovering this material also as a CRO. And with this, our acceptance has also improved a lot, and the problems related to nitric acid has been reduced. This is just to give the exact picture of microwave process. To start with, this is the first graph on the top. It is having all kinds of oxides. Then after oxidation, and this is after reduction, we can see only it is UO2 kind of, MO2 kind of oxides are present, which indicates that it has reduced perfectly. One more modification, third equipment is furnace. Actually, we are facing lot of difficulty because of water cooling. So now first furnace we have procured for with air cooling, and we have successfully carried out 20 sintering runs, and still it is under trial. Now we will turn to next section, that is fuel rods, that is pin making, you can say. This is a schematic sketch of PFBR fuel element. Actually this is very old development, but anyway it is important. Instead of continuous stick, we are using pulse stick. In our, it was implemented right from BWR time. This is actually basics of this pulse stick welding. This is indicates these overlaps. In continuous stick we will have one current, top current and peak current and bottom current. Here in pulse stick welding we will have peak current and base current, and these are the advantages we get with this pulse stick. And if you compare BWR, if you put on BWR, the acceptance has improved from 60 to 90%. And I will take pride, A3F is the first plant to introduce pulse stick welding for production. Next is laser welding. We have already introduced laser welding for bottom end of PFBR, and it has been accepted by specification committee of IGCAR also. And currently, recently we have modified our this machine for glow box adaptation also. This is actually glow box adapted laser welding machine. You can have this, you can see these advantages of laser welding, and this also has been qualified by specification committee of IGCAR, and we have started this production also. This is glow box adapted laser welding machine. These are all advantages of laser welding machine. Yeah, from our PM's Atmanirbhar Bharat, this is the indigenously developed automatic welding machine given by developed by RRCAT and our people, and this is also being right now it is being used for bottom welding of PFBR fuel pins. It is in operation now. The advantage is you can say it is one button process. After pressing one button, it will weld the fuel pin. Means in between maneuvers are not required in this. Then the next stage is, after bringing these fuel pins out of glow box, you have to decontaminate it. So this is also laser decontamination, which is also used in A3F first time. We are using series of decontamination technique, starting from laser, ultrasonic and manual. These are the comparisons of 3 decontamination technique. Each pin has to be marked for its enrichment and serial number. Earlier it was done by stamping. Right now we are doing with laser marking machines. These are the mark pins. Acha. We are using TIG and laser. Resistance also we are using. Basically resistance we are using for spacer wire welding. Actually this is our earlier plug. This we have modified, bottom end plug. Actually the problem is the cost and intricacy of fabrication is very difficult to fabricate. So we have modified this. Instead of having this groove for this bead of this wire, we have gone for the resistance welding or spot welding on this surface, followed by TIG welding. So this modification also have been accepted by IGCAR as well as NFC. This is for bottom weld. Same we have implemented for top weld also. This is our top end plug, and we have removed this groove, and we have gone for again resistance spot and TIG spot. The advantage of this, as I already told, actually because of this groove we have constraints on spacer wire wrapping operation, then fabrication difficulty of plugs, which both of them have been taken care. Chemical quality control. These are the series of chemical quality control techniques used in our fuel. I will just list the recent developments. This is Globox adapted WDXRF machine which we are using. Right now we are using for determination of PU and U in PAPR. This also has been accepted by specification committee of IGCAR. So this is non-destructive technique. The advantage over earlier technique is less waste generation, fast technique. This is recently procured thermalization mass spectrometer it is given by actually BRC Mumbai, and it is being used for isotopic determination. This is also calorimeter. Actually this calorimeter will be very useful in assaying PU2 in CRO and DRO samples. This is also developed by Mumbai BRC. Yeah, this is alpha active waste packet system. This is just to segregate the Cat4 and Cat1 waste. It consists of sodium iodide detector, and the drum is rotated in front of that, and we have calibration with PU2 content and these counts. By that we can easily segregate as per this criteria, waste criteria. This is also a very useful tool. This is quality control test. As far as physical quality control tests are which are carried out on pellet as well as on the pins. This is actually pellet sorting system which has been currently developed. Actually this segregates say class A, class B or class A oversized pellets. I have one video also if you can run. This is very fast, per minute some 60 pellets. Actually two ways are there. If it is oversized it will throw on this size. If it is under class A pellet, this will throw on this side. You could stop. This is actually when we are reconstituting the pins. We will take out all the pellets. When the pin is rejected, we will take out all the pellets, which will have all DDU2, that is solid pellets, as well as annular pellet, that is MOX pellet. Now those pellets have to be segregated. Actually earlier or till today also we are doing it manually, segregation of this annular as well as solid pellets. But this machine has been developed which by vision system it classifies annular as well as solid pellets. You can run the video. Yeah, this is annular pellet. All annular pellets are coming. Yeah, solid pellet it has thrown on this. This is very useful as far as reconstitution of pins is concerned. Yeah, this is a technique used for X-ray radiography of fuel pins. Earlier we were using film-based technique, and now what we are using is it is a combination of micro focus unit and flat panel detector, which is used for end plug weld radiography. These are typical radiographs. This is showing some defect here. This is top end, this is bottom end. Then wells, we continued with digital technique. Now we have switched over for, actually we have to carry out full pin radiography also. Earlier we were using films for that. That is actually carried out to identify this. You can see these different pellets here. This is annular pellets, this is solid pellet, this is DDU2, this is a crossover junction of this stack. These are the spring, these are spring supports. Earlier we were taking film radiograph for this, which is time consuming. Now we have turned to digital radiography for this also. These are typical digital radiograph. On the basis of this annular nature, we can differentiate between these two pellets, and if cross mixing is there, we can very easily detect. Here you can see some cross. This is an annular pellet has come into DDU2 stack. So that is something is not acceptable. Here also in annular stack, solid pellet has come. So it is again rejected. As you know, advantages is immediate results, then film processing, chemical environment friendly, no need of darkroom space, easy to store for longer time, because these radiographs we have to store at least for 10 years. So since it is in digital format, it can be very easily stored. Then as far as electronic instrumentation section is concerned, recently we have modified, or we have gone for new PLC for ventilation. This PLC was, I think, some 30 years old. Now this PLC has facility of SCADA. All these facilities are there in this particular PLC. So this has been changed last year only. Then on the recommendation of various safety committees, this clean agent based fire suppression system has been installed, which will take care of our servers, those things, CCTV racks. This is gas based system. Then this is modified PVC sealing machine. This is very important machine. From sealing of when we bag in or bag out, we use this machine for sealing, double sealing. And this machine, what earlier we had, is very bulky, and again it was expensive, and it was, I think, of foreign origin also. Our people have developed it locally, and this is working fine. The advantage is that many safety features, and it is fast also. New criticality monitors. Actually, our critical monitors are very old. Now we have installed new critical. So it is not development, but anyway, we have changed the criticality monitors. Yeah, the main purpose of carrying out this development or modification is to reduce the collective dose, and that we have achieved over the years. In between, this drop is because of this COVID time, but if you see from this 2017, it has slightly reduced. Here also it has reduced, and with this development, definitely it will go on reducing. So to conclude my talk, FF has successfully handled and can handle all fissile and fertile nuclear materials. Examples: oxides of U-230, U-235, PU, thoria. And our future plans are to introduce automation in existing glow box with practical approach. And second thing, we will be trying for DC and decommissioning of glow boxes, and if possible reuse also. That is our future aim, apart from fuel fabrication. These are our products. This is intermediate product, this is final product, and these are transported in these bird cages, combination of pin magazines and bird cages. Thank you, sir.
Thank you, Mr. Satyji, for almost elaborated developmental jobs carried out in fuel fabrication plant, which will be definitely useful for the future upcoming fuel fabrication plants. Now the session is open for some 2 or 3 questions from audience side. I have a question.
Yes.
Can you just take centralized grinder slide? There you have shown the grinding wheel little bit inclination. Can you tell the reason for that? Centralized grinder wheel. Yeah, just hold it here. Centralized grinder, that grinding wheel, there is some inclination. Yeah, can you explain that?
This is to, I think it is providing direction for pellets for coming out.
Oh, acha. This is while after grinding the pellets will be driven out by
Yeah,
due to
that
this
is
element.
it gives the motion to pellets to come out.
Yeah. Okay. Any other question from audience side? I think your presentation was self-explanatory. Thank you very much.
Thank you, sir, for the lecture. On behalf of ANCAS Tarapur, I request Chairman to present a memento to Sati sir.
Myself and Valsala Madam would like to thank the organizers who give this opportunity to chair this session. Thank you very much.
Thank you, sir. Particularly this session was really technologically as well scientifically, this was stimulating. On the behalf of organizing committee NUSUC-2022, I thank all the speakers of this session who has arrived at Tarapur at our request. And further going, I thank Shri P.G. Behre sir and Dr. T.P. Valsala madam to chair and become secretary respectively of this session and concluding this session in the allotted time. May I now request Shri R.V. Bhatt sir to present a token of our appreciation to session chair and session secretary of this particular session. That's it. Now we will break for a tea break of 15 minutes. We all will assemble around 11:35 over here. And I request the delegates and participants who have arrived today, they can contact Dr. Amrita Dhara for their kickbacks and related things. Thank you very much.
Velmurgan sir, please unmute your microphone.
Hello.
Murugan sir.
Velmurugan speaking from IGCAR, Kalpakam.
You want to test your presentation? As you are going to present live, kindly, now we are adding you as a co-host. Kindly share your presentation. You can present your screen.
1 minute, 1 minute. Sir, could you able to see the presentation, sir? Hello.
Sir.
Sir, could you able to view the presentation?
Yes, we are able to see the presentation OP3 ART 17 challenges
Yes,
in
yes.
qualification of hot cells.
Yes, yes, yes.
Yes, okay, but we cannot see your camera.
Camera, sir. 1 minute, sir.
So you have to go to your presentation window. You have to go to your presentation window.
1 minute, 1 minute. Yes, sir.
Yes, yes. Now you can go to the slideshow mode so that you will be able to see full screen here. Yes, yes. This camera, your camera was not connected.
Camera is connected, sir. 1 minute.
Okay. So you can alt tab and you can go to that.
Cam-
Access in Google Chrome to your camera.
Yes, sir. Yes, sir, yes, sir. Because when I started first, I'm visible, sir, in the camera.
Okay.
But how to do? I'm not-
Okay, we can go ahead without camera also, no issues.
No issue, sir. We will see, sir. No problem, sir.
We will not be able to see you, otherwise your presentation is visible, that is fine.
Okay, okay. Okay, sir. We'll check it, sir. No problem, sir. We'll check it. Okay, sir. Okay, sir. Thank you, sir.
12:45,
Yes, sir. Yes, sir. Yes, sir.
otherwise you can log in at around 12:30.
Yes, okay, sir. I am just watching other presentations also for my knowledge. No problem. Okay, okay, sir. Thank you. Thank you, sir. Thank you.
Okay, right now I am muting you. At 12:45
Yes.
I will again add you as a co-host.
Okay, sir. Okay. Thank you.
Hello, check. Hello, check. Request all delegates to have their seats in the hall. So now let me start the session number 6 of this conference. This technical session, to conduct for this technical session, I request Dr. K.S. Bindra, sir, Associate Director, Laser Group, Raja Ramanna Center for Advanced Technology, Indore, to chair this session, and to assist him, Secretary Shri J.K. Gayan, sir, General Manager, INRP Kalpakam. Please come on the dais, sir. This session has one invited talk by Shri V. Shivakumar sir, Head Fuel Engineering Section, RED, BRC, Mumbai, and has 3 oral presentations from contributory research papers. First one by J. Selva Kumar, NRB Kalpakam, second one by Dr. Ashish Pandey, BRC Tarapur, and third one, which is via online mode, by Dr. V. Will Murugan, IGCAR Kalpakam. So with this much introduction, I straightway hand over the proceedings of this session to session chair and secretary. Thank you.
Invited talk is for participants of post presentation are each 15 minutes. So I request Shri V. Shivkumar, Fuel Engineering Section, to come on the stage and give a brief introduction of him. Shri V. Shivkumar, Head Fuel Engineering Section of Reactor Engineering Division, DRC, Mechanical Engineer from Bank of Ministry, and he has about 30 years of experience in different areas associated with the research and power reactors. His silent areas of work and contribution are in design and development aspects for different research and power reactor fuel and structural material experiments and irradiation done, and he has participated in irradiation of T.A.P.S and boiling water reactors, 19-pin PHWR, uranium, plutonium, MOX fuel. He is associated with fuel fabrication and specifications and quality control aspects of different reactor fuels, coordinated activities for HWR thorium fuel cycle program, and participated in various fuel and reactor safety review committees. So maybe you start your presentation.
Thank you, Chair. As the title indicates, that it's going to talk from once through cycles to the recycle based fuel cycles, the transition, how do we go from this to that. So basically the structure is going to be something like this. I'll try to provide a brief overview, the global perspective on reactors and on fuels, and try to provide some leads for certain scenario aspects which can be used for evolving strategies for shaping and deploying fuel recycling. So with this in mind, I'll start the introduction of the nuclear power generation. What is the current global scenario? We have about 440 reactors operating worldwide, having an installed capacity of close to about 400 gigawatt electric, and most of them are PWRs, close to 300. Almost 100 in total are the other water-cooled type reactors, which are BWRs and the PHWRs. So basically it's a scene which is completely dominated by water-cooled reactors currently. Now how have we got to this stage of 400 gigawatt? In the initial 20 years it was spectacular, I would say. Almost till the late 80s we had a very spectacular growth, and then it has been more or less stagnant. There are reasons for that, and now in terms of how these were built or constructed, this is a general profile. So most of the construction activities happened in the late 60s and the 70s. There was a tremendous amount of construction going on during that period, and many of the reactors got connected during the mid 70s and the 80s. So all in all, almost every year 30 to 40 reactors were getting connected to the grid in that 2 decades, and after that has been a lull, practically in less than 10 in most of the years, at least recently. Now what has happened, that this phase has been converted to this phase. We'll try to see how this actually has happened, how it has happened. Just a different perspective of the same data. Most of the reactors are now 30 to 40 years old. Very few which are new. Less than 5 reactors typically being added every year in this phase, and here is the situation now. We have reactors which are more than 30, 35, 40 years old, and we at Tarapur have perhaps the oldest one, which is more than 50 years. And it's somewhere in this. Now coming to the electricity generation data, as was seen in the installed capacity, there was a spectacular growth in the electricity from nuclear power plants during the first 2 decades, that is during the 70s and the 80s. And then, although the installed capacity was not much, but there was still growth in electricity generation, aided by the improvements in the capacity. So earlier the reactors were operating at 60% capacity factors, close to 60. We have been able to achieve more than 80% now. So this is getting reflected in this zone. The first was due to the installation increases. The second was due to improvement in the capacity factors. And the one blip here is, as you all know, post-Fukushima. In a different way, this data is compiled. It shows the data of nuclear electricity generation in different countries. The top 3, US, China, France. India is somewhere here. But very shortly, you all know, will be somewhere in this zone. Now let me give you an overview of the developments that have happened in the field of reactors, reactor designs especially. This gives a picture of how reactors got evolved in the first 3 decades. Earlier it was the prototype reactors, small size reactors of capacity of about 100 to 200 megawatt in the 50s and 60s. This was followed by large commercial reactors in the 500 plus, close to 1000 megawatt reactors. And then during the 80s and the 90s, there was significant improvements in reactor safety. There was not much change in the reactor powers practically, but a lot of developments in safety features took place during this 90s and late 80s and even in the early 2000s. The first focus during the reactor development was to improve the capacity factors. As we see that it's now well above 80% for all types of reactors, the BWRs, the PHWRs, the pressurized water reactors. So all the reactors, all the 3 types of reactors have been able to achieve very good capacity factors during last 1 or 2 decades. The second aspect of focus was in reactor safety, and what triggered this was the incident or the accident at the 3 Mile Island and the Chernobyl. These were the 2 kind of showstoppers for the growth perhaps, but this is what triggered the improvements in reactor safety. And the third one has also been instrumental in initiating a lot of developments in the area of safety. Now, how it was done was the concept of defense in depth was introduced. What it means is we incorporate a lot of systems, multiple safety systems, redundancy, and to kind of have a philosophy of prevention, monitoring, and action to mitigate the consequence of failures. So we kind of preclude failure and try to manage it. So this was the first philosophy that was introduced in the safety. And anyway, there was lot of improvements in design and construction, quality aspects. And the other aspect which was introduced was to have a very elaborate and comprehensive monitoring along with regular testing to detect equipment or operator failures. And this was the period when we have very stringent tech specs for the reactors. And there are a lot of regulatory interventions in this aspects. Now coming to the first type of safety feature which was introduced in the reactors, and that can be categorized as active safety features. These are basically which rely on active devices driven by electrical or diesel motors. And these features, what it does is it tries to ensure that any operational disturbance or human errors don't get into problems for the reactor operation. Then we have, as I said, redundant and diverse systems to control the damage to fuel and release of any significant radioactive release. And both put together ensures that we confine the effects of any severe damage or any other problem in the plant itself. So this was one major step which happened after the 3 Mile Island. The second thing was the introduction of passive safety features. What it means is we try to use the natural forces or phenomena such as gravity, pressure difference, or the natural convection of heat. Although we have deployed this feature in the reactors camp, this has been used for the other aspects of reactor safety also. The two major focus areas were removal of core decay heat and in cooling of containment along with suppression of the pressure inside the containment. So these were the two major focus areas for this safety features. What it offers is, it offers high reliability at a reduced cost because we don't use active components. But the disadvantage is we have to manage with very weak driving forces. And this is a big issue, especially in demonstration of safety for a very broad range of accidents. It may be good for a few type of accidents or incidents, but when we have to use this for a engulfing type of accidents scenarios, it has a lot of challenges. But we have been able to manage all this reasonably well. The third focus area has been in terms of life extension. All the initial plants were supposed to have a design life of only about 40 years, 30 to 40 years. Now gradually we are trying to increase it to 60 or even 80 or perhaps even 100 years. That could be a kind of a high upper number for all these things. And these have been focused for the reactor pressure vessel. And in the case of PSWRs, we have been able to come up with solutions for replacement of the pressure tubes with enhanced life. And all these have required carrying out inspection, in-service inspection as well also, the repair and replacement, generation of data for all these aspects. And the fourth most important thing was to have provision or retrofitting of safety systems, because we cannot say that old plants cannot operate with the old safety systems. The regulators definitely are going to ask for the latest or the latest in terms of safety when you go for life extension. Now, what has been the recent focus? The recent focus in this last decade has been in the development of SMRs, which are basically which is S is for small, where you have very low or small capacity per unit, less than 300. It can be as low as 50 to 100 megawatt electric also. They are modular in construction so that they can be made at the factories, transported as a unit and installed at the location. And what it gives us is, it calls for a smaller footprint, so that, I mean, the advantage is it can be sited on locations which are not really suitable for large nuclear plants, close to cities, perhaps the area vacated by any thermal power plant, the coal-based thermal power plants. And the second thing is, we can have an incremental deployment of this as to match, especially for small countries, it can match with their increasing energy demands. And the third thing, which is still under work is in progress in this aspect, is trying to kind of optimize cost and construction time. Now, why construction time is an important aspect is, this kind of tells us a typical construction time for a reactor is almost 7 to 8 years. So it brings in a lot of uncertainty, a lot of capital interest, interest to be paid on the capital that is being invested. So this is one issue which is trying to get addressed with the use of or with the deployment of SMRs. On the next aspect, that is on fuel developments which have happened in fuel. The primary focus was on having an improved fuel performance. The fuel reliability was improved as our understanding of failure mechanisms improved, and they were brought out in the form of improvements in design, fabrication processes, and as well as in the reactor operation. And it helped us in providing a higher reactor availability. Along with that, there was a steady increase in burn-up, which resulted in having a lower fuel cost, longer operating cycles with shorter and less frequent refueling outages. This is an important aspect for LWRs, which is basically PWRs and BWRs. The PHWRs, anyway, with the advantage of having online refueling, we don't get this advantage. And during this period, lots of new clad materials and structural materials were developed to have better, higher corrosion resistance, along with some design enhancements to have better thermal margins. One important program which happened in this area was having a zero fuel failure program in the global scenario. Close to 10 power minus 6 is the target. And if you see, almost 80% of the reactors operate without any fuel failure in a particular year. And fuel failures which were significantly high, more than 200 into 10 power minus 6 to close to now 10 power minus 5. So this is the kind of improvements which have happened over the years. Earlier it was significantly high, but now it is fairly under control. And some of the root cause analysis which were kind of addressed. Even now we have a few major issues related to the grid to tube failures, Dae-Brns, and a minor fabrication and PCI related. Now, post Fukushima, this has been one major area of focus, development of accident tolerant fuels. What it tries to attempt is control the hydrogen generation rate under accident scenarios, control the cladding reaction with steam, the fuel pellet cladding interactions, as well as on the retention of fission products. And it involves focus on cladding materials as well as on the fuel materials, iron, chromium, aluminum cladding, the coated zircaloy cladding, the silicon based cladding materials, and the use of uranium silicide fuel, which has good fission product retention as well as good interaction with the coolant, that is water. To summarize, the first 3 to 4 decades of the nuclear program has been based on open cycle water cooled reactors with these key focus areas, which is economics, safety, improving the fuel reliability, trying to improve the uranium utilization, extend the reactor life, and have an improved construction management. Now coming to the topic of this conference, what are the key drivers for fuel recycling? We are practically living in a world of open cycle, and we have to move to the world of recycling. One thing which has to be clearly understood is the use of or the deployment of closed fuel cycle is an inevitable step. Why? Because we use only 1% of the uranium that is available in the resource with the open cycle. Second thing is, if you have to unlock the potential of the other more abundant nuclear source, which is fertile thorium, we need the closed fuel cycle. And the third most important thing is to have a sustainable or an acceptable waste management and environmental practice. But the major issue is, what is going to be the timeline for this? What is going to be the timeline for the large-scale deployment? Now that depends on 3 major aspects which is talked about. One is, what is going to be the fuel resource position, what is going to be the economics, and what is the technology maturity of this. Now coming to the resource position, we have, that is in the global scenario, almost 1 million tons of uranium which can be exploited at a price less than $40 per kg of uranium, for a price of $80 per kg uranium, almost 2 million tons of uranium, and for 130 and 260 it's 6 million tons and 18 million tons. So almost 17 million tons of uranium is still available with us. And at what rate are we consuming? Globally, the consumption is about 70,000 tons per uranium. So in the initial phase, it was all for military purpose. The uranium consumption predominantly was for the military purpose. In this phase, it is for the commercial generation of nuclear power. Some of this was used up in this phase, so that is why, although the production was not much, the consumption could be managed. So this was basically from the USSR and the USA, which was kind of dismantling of their military uraniums. The second thing which could call for recycling is, can we use MOX fuel in water-cooled reactors as an interim measure? Yes, that will help us in saving of uranium resource, but it has to be backed up with strong economics. The cost of reprocessing and the MOX fuel fabrication has to be at least comparable to that of the cost of uranium resource plus the cost involved in conversion and enrichment. Now, if we see the scenario, the costing which is there for uranium is, it had touched close to $100 at its peak. This was the time when there was talk of nuclear renaissance. It was at this stage that the price was close to $100, and at this price perhaps the use of MOX fuel can be quite attractive, at least for countries like India. What is the third thing? That this is going to be an important phase. it's not going to be business as usual, at least the next 3 to 4 decades, with climate change kind of having issues, and that provides us a strong impetus for growth in nuclear power. But the competitive environment is from the renewable energy and developments in storage. So with this scenario, the planning has to be done for the recycling aspects. At present, nuclear electricity is only about 10% of the total electricity generation, and what we have is 36 plus 23, almost 50% is from fossil fuels here, with a little bit contribution of oil. So more than 50 to 60% is still coming from the carbon sources of, for electricity, and that is getting reflected in the CO2 emissions. So there is, over the years, over this last 100 years, there has been significant increases in CO2 emissions, and this is what has to be reduced, and this is where the nuclear industry is in business. But it has to manage it along with the renewable energies. So it has to be in tandem with this. What can be the way forward? We need essentially a very robust and a sustainable strategy for this. Why? Because energy is an extremely fluctuating and a complex business. Unless we have very robust and sustainable strategy, it is very difficult to manage in this business. And for a large country like India, this aspect will get dictated by global factors as well as domestic factors. The third very important aspect is it's a very highly capital intensive business. So you need strong investment confidence, and time schedules are going to be very important. This is a critical element in this. So, and as we have seen in the morning, lots of challenging technological areas, and what it essentially means is we need a very clear demarcation in the two phases. In the first phase, which is R&D and technology demonstration phase, and in the second, which is going to be the large scale commercial phase. So this is one aspect that we need to kind of evolve for having a very sustainable strategy. Now in this phase we are currently, so what do we do for this? One is we need to select the technological fronts which are very critical in nature for this recycling. It should have potential for large scale commercial deployment as well as lots of performance monitoring indicators. That is going to be an area, because we will always be under the scrutiny of the person or the people who are investing on us. Second is we will need lots of innovative and cost optimized solutions for carrying out this development areas, because we don't have the advantage that we had during the early years of nuclear power, because lots of things were done in the name of defense, and on the contrary, we have now the non-proliferation hurdles to be managed. So this is one area of focus which has to be brought in, and probably try to work out some commercially viable options, like including carrying out partial recycling for generating a stage-wise or a stage-wise experience. It can be both at the reactor as well as at the fuel cycle front. Thank you.
Thank you very much for providing information on safety aspects and other issues related to the nuclear fuel. And the talk is open for discussion.
Thank you, sir. Thank you for such a nice presentation. I would like to understand, sir, that you have mentioned about the small modular type of reactors. So, my question is just a curiosity. Can't we sell nuclear reactors like a car, manufactured in a factory, assembled in a factory, and when this car has to be scrapped, this has to come back to a dedicated facility and where the recycling can be done. So, what about this concept? Definitely that regulatory aspects are there, but when it comes in a package, that has to be also taken care in that way only. So, what about that, sir?
Your question itself has got the answer. You have yourself told
That
what
has
you...
to be, yes, sir. That has to be managed accordingly. That framework has to be done in that fashion.
Yes.
Because, yes.
All the effort which has happened in this front, the last 10 to 15 years, has been in that direction only. You kind of make the components, bring it in a truck and install it. And after the service life of the reactor, you can take it back for decommissioning or decontamination.
Near future, sir, we can expect this kind of things to be a reality.
See, already 1 or 2 reactors have come into picture. The design and development globally, as well as at DAE, they have been initiated. So it's at different stages of maturity, you can say. Now, it is still at the preliminary stage as far as regulatory reviews are concerned, but it's still on the design board. Practically, it's on the design board, and maybe, yes, prototypes on certain key areas in terms of fabrication, that is being taken. So if there is no clear-cut timescales which are at least available, because see, in the Western and the advanced countries, there is no kind of pressure on them to replace their already operating reactors. So it's only in countries like India where we have a lot of kind of potential for growth, we are thinking on it. It could be in the next 1 or 2 decades. That's what is the kind of understanding people are having. At least by 2030, we will have a significant number of SMRs operating, or at least in some kind of advanced stage of construction.
Thank you, sir. Thank you very much.
Thank you, sir. My question has 2 parts. First one is, from your presentation I could learn that post-Fukushima, how India is prepared to deal with such eventuality. And the second portion of my question is that to meet the green power, we need to rely on nuclear power. So will it be advisable to go for MOX fuel in PSWR or rather than PSWR in BTR? Or MOX fuel in fast breeder test reactor?
See, the question is what is going to be the share in the total electricity production or the energy production? Now, how much can we influence? So if that comes into picture, yes, you need, if you want to make some impression at a very kind of in a very fast way, use it in the existing reactors, but it should not be at the cost of your long-term strategy. So obviously we can kind of think about these strategies of using it in water-cooled reactors, but it has to be backed up with economics. So as you see, the resource position is reasonably comfortable for the business as usual scenario for the next at least 2 to 3 decades. Maybe yes, after that, obviously that will come into picture when you need to exploit uranium resources which are expensive, more than $200 per kg. And as far as the Fukushima part, yes, it's mainly in terms of incorporating some more advanced features, kind of emergency preparedness. That has been the focus. It's mainly on emergency preparedness and trying to incorporate some more advanced features.
My apprehension was that more and more reactors are put into safeguard domain, and that reason is that we are relying on the fuel imported from outer worlds. So if you go for our MOX fuel in PSWR, which is our indigenous programs, and we have got a very good operating experience in that. So will it be advisable to go for that or not?
Yes, MOX fuel will provide in terms of increased burn up. So it has that advantage of kind of improving our discharge burn ups. Your refueling rates will come down. The daily business of refueling also can be, the load burden on the operator can be reduced. It has all those things, but the issue is we will not be able to put very high concentration of plutonium. It will be restricted to less than 1%. And will we be able to manufacture 10-20 tons for one 200 megawatt PSWRs? That is a question. And anyway, there will be kind of safety issues which will have to be addressed in terms of the smaller delayed neutron fraction. All those issues will be the reactivity issues, aspects will have to be addressed. But ultimately it will need almost 20 tons of fuel, MOX fuel for just operating a 200 megawatt PSWRs. Now, do we have the capacity for that? We'll have to see.
Yeah. For your good step. Now I request session chairman to give us comment to Mr. Sivkumar on behalf of organizers.
First presentation is by Dr. J. Selvakumar, and title of his presentation is Selective Removal of 106 from Impregnated ADS 400. Dr. J. Selvakumar from NRP Kalpaka.
Very good afternoon. I am Selva Kumar from WIP Kalpakam. Wholeheartedly thank the organizers given this opportunity presenting our small work before the eminent scientist of DAE. And also I would like to thank my guides, my seniors in our department, like AGM, GM, INRP, K and C, NRB, and authors of this paper. The presentation topic is selective removal of ruthenium 106 from ILW effluent using nickel compound impregnated polymeric resin. We have taken ADS 400, is a polyacrylic based resin actually. So let me introduce the topic like ILW treatment. This is the typical flow sheet we are using in that treatment of ILW. When we are receiving intermediate level liquid waste from reprocessing plant, so first we are carbonate destruction we are carrying out actually. We are conditioning with carbonate destruction by using 4 molar nitric acid. So after that actually the heavy metal, whatever the heavy metal present in that ILW, like uranium, plutonium, will be precipitated out by using 4 molar sodium hydroxide. And then the precipitated sludge will be dissolved using 12 molar nitric acid, and that solution is sent back to reprocessing plant for further use. And the supernatant will pass through that resorcinol formaldehyde column to remove cesium, and then heavy metal and cesium lean solution sent to centralized waste management facility for further treatment and disposal. In this process actually we are getting almost decontamination factor with respect to cesium 137 and heavy metal we can say more than 1000, but in the case of technetium and ruthenium we are getting 2 to 4. In all over the world actually people are like waste management communities working on to improve that decontamination factor of ruthenium and technetium. So we are also in plant as a plant chemist actually we are also trying our level actually. So how to improve that decontamination factor, because here maybe precipitation time ruthenium can give some small decontamination factor, but it's not enough to send it to centralized waste management plant actually, but finally they are putting it to the cement blocks. Actually there the dose will be higher when ruthenium is higher actually. So in that context actually we have started working on maybe last 1 month I can say. So technetium ruthenium, I told the main problem with technetium is because of high half-life, and ruthenium is very high specific activity. The two criteria actually given a idea to we have to work on that to remove technetium and ruthenium before sending it to the final disposal applications. Now another way actually the technetium we are taking out from that even HLW or ILW, it can because of N-gamma reaction can be converted to a low short-lived product as well actually, because the technetium 100 become ruthenium 100 can be treated that way. Even ruthenium we can say actually it will very well help useful for branchotherapy applications. So like this way yesterday energy director also given a slides actually. This way one of the application. Another application we can able to remove ruthenium from the ILW. So the management will be easier, like we remove it a better way, maybe better matrix will find out actually for ruthenium and technetium for final disposal, and not in that like zero waste concept actually we no need to send it outside. We'll contain it by using glass or geopolymer, some other better host material will design it, we'll do it inside plant itself. Because of ruthenium, this paper mainly concerned about ruthenium actually. Ruthenium because of complex chemistry in especially in alkaline condition, it's existing both ruthenium oxyanion in other oxidation state also. So we couldn't be able to identify a methodology, easy methodology. For example, ionic change I can remove 100%, I can elevate. Otherwise option method we can do it in 100%. Other precipitation, any method we can go. We are not getting that much, like more than 50 to 60% removal. We couldn't be able to do it by ruthenium. We are also tried with some of the inorganic ionic changes, anionic ionic changes. We have tried in our laboratory. We couldn't be able to do it. So in that way actually we are find out some literatures. So far literature is given like ruthenium recovery from alkaline waste by using material like this. These are all the material used actually, the different feed pH range, and methods are used ionic change, co-precipitation, sorption method. But we got some interest on nickel sulfide based on Tarapur work only, and also Sonal sir and Malsala madam is worked on that actually. Nickel sulfide we have some attraction on that because of high DF as well as KD values like 8000 to 9000 ml per gram is there actually. So in that way we started work. So aim and scope of the work is actually removal from alkaline waste using nickel compound. This is the methodology is used like by NL Sonar sir. They have made a nickel sulfide compound by two methods. One is actually nickel nitrate and sodium sulfide in the pH range of 12. They are getting a nickel sulfide, the black color powder, and then nickel sulfide combined with polymer based compound, and by using a binder can able to make a nickel sulfide BMMA beads. It's very well working on an alkaline condition. So similar way we tried actually some modifications. So first we tried our laboratory whether nickel sulfide is working out or not actually. In that way the similar step one we followed, then found out actually nickel sulfide is working out. More than 70% of reduction of ruthenium is absorbed in the effluent sample. It's the actual sample we used for the experiment. It's working out. So we have devised the experiment. So in the place of polymer, we have tried to impregnate, like coating on nickel sulfide on the polymeric resin. By the way, actually, we have taken ADS 400. It's like alternative to XAD7 resin actually. So in that resin we have taken and soaked with used with nickel nitrate solution, and then absorbed nickel nitrate onto the resin. Then we have reacted with ammonium hydroxide. Then nickel nitrate converted to nickel hydroxide. Then we added sodium sulfide. Finally, nickel sulfide ADS 400. It is the plan of work. So we have the experiment is nickel synthesis of compound, characterization, a removal study, and selectivity. So in that way we started an experiment. So first step is actually we have taken ADS 400 and washed with acid, water, and alcohol, wash everything. Then heated at 660 degrees centigrade in the oven. Then we have soaked with the nickel nitrate solution for 30 minutes. So we have continued. Actually, as per Sonasar paper, is they are saying 50% of nickel sulfide loading can be possible. But while coating, actually we want to improve the thickness of the coating. So we washed again and again. Nickel nitrate soaked with the nickel nitrate, again washed with water, then soaked with the nickel nitrate. That way we have started experiment. Then finally, after nickel nitrate, sufficient amount of nickel nitrate coated, then we treated with ammonium hydroxide. nickel nitrate become, you can able to see here that green color become off-white color, yellowish color actually. This is showing that nickel hydroxide is formed. After that, sodium sulfide addition will give you a black color bead with nickel sulfide coated on the resin. So we have started, but in our experiment, we have not started straight away for exploring this resin. Actually, we explored this resin, nickel hydroxide coated, because our earlier experience shows that cerium hydroxide can take some hydroxides can take ruthenium. That way we started. Characterize the material also. Product 1, nickel hydroxide we synthesize, even powder form as well as in the bead. Actually, we characterize by XRD. XRD is confirmed. It's using it. We confirmed with the JCPDS file number PDF 140117 hexagonal phase, and even bead also be characterized actually, which shows that the XRD spectrum shows that actually the compound, it's not having any chemical reaction between the polymeric resin and the compound. The next we carried out thermal studies actually for ADS 400 alone, nickel hydroxide alone, and nickel hydroxide coated ADS 400. It shows that based on the thermogravimetry analysis, we come to know that actually almost maximum of 16% is coated. Based on the weight loss, we calculated 16% of nickel hydroxide coated on it actually. So after that, particle size growth also we studied actually. After that, first step, second step, 3 steps we have quoted actually. After that, how much growth is there in the thickness grown on that, we have characterized by particle size analyzer. It's almost, we are got this is the spectrum you can see actually. Yes, sir. So finally, that ADS 400 and nickel hydroxide coated ADS 400 we characterize separately for uptake also. Similarly, actual sample we characterized actually. So this is how the spectrum look like actually after different quantity of compound. Ruthenium 106 uptake was almost 60 to 70% we could observe. Different pH range. Cesium uptake is nil actually. After that actually the final one, nickel hydroxide, so that way the nickel sulfide also we want to check actually. We characterized by that way, same way. The same effluent sample we have taken with the batch extraction study of 5 ml ILW effluent, equilibration time 60 minutes. We can able to see that actually ruthenium uptake, ruthenium peak is so much comes down actually both the way. Cesium peak is, because the dilution factor is different, that's why I have not given y-axis. So that shows that nickel sulfide is working out well actually. So we want to do it in the engineering scale, like column studies and all. We are going to do it further actually. Summary: nickel compound impregnated, synthesized and characterized. Preliminary studies on the separation of ruthenium and selectivity over other radionuclide were assessed, and the studies found to be promising. The maximum loading we are trying now actually, as of now, the maximum loading in nickel compound on ADS 400 resin and characterization column studies will be carried out. So thank you for your attention.
We can have few quick questions.
The very much aim of your studies is you are looking for removal of ruthenium only or something else?
Sir, actually we want to remove both technetium and ruthenium. But if it is selectivity is there, is well and good actually. For technetium separately, ruthenium separately.
Okay.
Then I'll take it out technetium separately and different host material, because very high off life. Ruthenium may be used for some other application. I elute it. I'll use it for concentrate and use it for some other application.
So whatever you have this resin you have developed, means
Yes,
it is working for ruthenium right now.
Ruthenium is working.
Okay.
See, you have shown 60 to 70% loading. Is it like that?
Hi, sir.
Then that is in a not very efficient. No, you need more than 99%.
Yes, sir.
or so.
That's why last slide I told we will increase the thickness of the nickel sulfide on the resin. Even required binder will use it, sir. Actually, that we started without binder, minimum, maximum, because paper also saying that 20% is more than enough. We achieved up to 16%. We'll increase up to 13. If it is 30%, couldn't able to stick onto the resin, we'll use some binder to make it, sir. Actually, we'll increase the thickness. Surely 99% we are.
But by increasing that much, you cannot go to 99%. You are having 60-70%. No? You
Yes,
can
sir.
go maybe up to 75-80%. 99% you cannot go. And second thing is that you are a chemistry.
Chemistry only, sir.
So you should know actually what is the speciation of ruthenium.
Yes, sir.
You have never mentioned anything in your lecture about what species is going, how it is interacting. So those things better you should try to
Yes, sir. Yes, sir.
study.
Yes, sir.
Because it is a very complex chemistry of ruthenium. In alkaline feed also, a lot of anionic species are formed.
Yes, sir.
So how
they are going to interact with your this
That's the
resin
thing, sir.
that
Our
you should
laboratory
study.
experiment, whatever the resin I used actually, maybe for example, anionic resin I'm using, there only 30% uptake is there. If I'm going for inorganic ion exchanges, something 60% is there. It itself very clearly saying that different.
Anionic resin you have shown DOX 1/8 or so.
Yes, sir.
That is very high. It is more than 99%.
Yes, sir.
Okay.
Actually, that same paper we followed actually. Our group only carried out in BRC, but problem is technetium is so high in that. Like for example, if I am saying the value 10,000 becquerel per gram is there, ml per is there technetium. But if you go for ruthenium, maybe maximum 700 becquerel is there. It is first attracting technetium only. It is taking very selectively for technetium also. So even that kind of problem is there. Actually, we couldn't address it, sir. Actually.
Okay, thank you, Dr. Selvakumar.
Yes, sir.
Now I request Chairman to give a small moment. Thank you.
On applications of X-ray spectrometry during fuel fabrication. May I request Dr. Ashish Pandey?
Thank you very much, sir. So, the topic of my lecture is today applications of wavelength dispersive X-ray fluorescence spectrometry during fuel fabrication. Before I start my lecture, I would like to pay homage to our the chief guest of our last NUSUC 2018, Shri Dr. A.K. Bahaduri sir, and we have a great loss to our DA fraternity. So the layout of my talk is like introduction and whatever applications we are dealing with the XRF during fuel fabrication, I will try to incorporate for the determination of uranium and plutonium in uranium plutonium oxide mixed oxide fuel during using XRF. Second application is the determination of plutonium in the clean rejected oxide, again using XRF, and direct non-destructive determination of uranium in sintered DDO2 fuel pellets using WDXRF. So presently fuel fabrication facility is fabricating MOX fuel. Basically it has two composition, 21% and 28%. 21% and 28% PO2 along with the DDO2 for the PFBR reactor. As far as chemical quality control is concerned, for the determination of uranium and plutonium heavy metal content, that quality of the fuel should be as per the which has been laid down by the designer. That we have to take care. So as I proceed further, I would like to mention here that how this mixed oxide fuel has been fabricated. This uranium oxide and plutonium oxide has been mixed in the iterator, then pre-compaction, granulation and final compaction has been done, and after the sintering, all these are the process flow sheet of this MOX fuel fabrication, and these are our chemical quality control steps. And right now, because of we have developed our WDXRF technique, and we have implemented also in the plant scale. So at the 3 stages, we have replaced the existing techniques with the WDXRF. So these are the various chemical quality control steps during fabrication of PFBR MOX fuel. First one is the determination of plutonium oxide percentage in the mixed blends, that is the mixing and milling, and the determination of uranium and plutonium in sintered MOX fuel pellets, and determination of plutonium percent in the clean rejected oxide MOX powder. And these are the other dissolution tests, O/M ratio, metallic impurity and non-metallic impurity determination. So determination of uranium and plutonium can be done with the both way. One is the destructive method and one is the non-destructive method. For the destructive method, we are following titrimetric method, and we have developed for the non-destructive determination WDXRF. So actually why non-destructive method is required? At our plant, we are struggling with the analyzing the samples for the uranium and plutonium. We are generating so much of our nuclear waste and alpha bearing waste, and it is very much burden to the plant. Then how to handle it, all this liquid waste. So we have to have think that why can't we go for the determination of uranium plutonium at par with the titrimetric method. So these are the some shortcomings of our titrimetric method. Let us suppose that analysis time is 11 to 12 hours. And tiresome, and then the sample preparation. Skilled persons require 3 to 4, and around 250 ml of alpha bearing waste has been generated during the titration, and lots of our corrosive acid has been used. So our plant has decided we have to use non-destructive method for the determination of uranium and plutonium. So whatever WDXRF we are using, these are the means our some of the parameters of XRF we are using of 200 watt capacity. And as you know that plutonium is a radiotoxic in the nature, so we have to have handle inside the glow boxes. So we have made adaptable our WDXRF spectrometer inside the glow boxes here. And for making the sample, we have installed a hydraulic press inside also for the sample preparation. So it is a very clear step how to determine uranium and plutonium directly in the sintered pellet. So first of all, we have to have prepared the calibration standards, and then we have to make a calibration plot, and we have made a collet where we have put it our pellet and directly analyzing the samples, and of course results using the calibration plot. So as I have already earlier mentioned, the composition of the fuel is 21% PO2 and 28% PO2. So accordingly, we have made working standards as per the samples we are receiving. So once here I am telling it is as lower composition MOX fuel, and for the 28% I am telling it is higher composition MOX fuel. So for the standard preparation, we have to have first of all we have prepared a master standards, and we have 20 grams of the one sample mixed with the DDO2 as per the standard I have already shown in the slide, and mixed with our polyethylene glycol, and put it in the aluminum cup and press with the sample hydraulic press with having 25 ton of capacity for 1 minute. This is the parameter for the hydraulic press. This is the typical photographs of the calibration standards we have made for our analysis of uranium and plutonium in the sintered pellet. This is the calibration plots. Though actually it is our main application, whatever during sintering, we are getting the MOX pellet in the form of sintered pellet of diameter 5.6 to 5.7 mm, of the length 7 mm. This is here. So we are having a collet. We are just inserting these pellets inside this hole, and just using this wing nut, we are tightening the samples, and we are putting this collet along with the samples in a sample holder. This is our sample holder of size 44 mm. The cutout is 40 mm. So we have to have this collet type of things so that it can withhold with the sample holder, so that our sample should not fall in the spectrometer. So after we are just sending our sample holder along with the sample in the spectrometer for the analysis of for the getting the uranium and plutonium alpha intensity. So it is a typical WDXRF spectrogram of sintered MOX pellet. Here you can see it is the peak of uranium to L-alpha, it is the peak of plutonium L-alpha, and the angle of the 2 theta is the 226.13 for the uranium, and for the plutonium is 24.89. So whenever I go for replacing a method, we have to have very much sure that whatever we are determining with our non-destructive developed method, it should have the comparatively good value as with our existing titrimetric method. So we have compared whatever samples we have analyzed, we have compared the results with the titrimetric method, and we have found that none of the samples is going beyond the specification limit. Here you can see that the red one is the titrimetric value, and the green black one is the XRF value, and these are the upper and lower limit of our specification. So none of the our results, whatever we are get from the XRF, is not violating with the specifications. It is with the higher composition 28% MOX fuel. Here also we are not getting any single value outside our limiting value, specification value. So if you see the comparatives to the titrimetric method and XRF method, it is very clear that using titrimetric we are using 11 to 12 hours, and we have reduced 2.5 hours only analysis time, and no sample preparation, skilled person only 2, no leakage waste generation, nothing corrosive acidity, nothing. And this is the very good actually for what our MOX fuel fabrication plant requires. It is for, let us suppose 170 number of samples have been analyzed. Suppose it has been analyzed with the titrimetric method. So we could have generate 45 liters of liquid waste, alpha waste. But using WDXRF, we are generating as such no, means directly we are analyzing our product only, and after analyzing product, we are sending back for the fabrication line. So we are generating no liquid waste. And here you can see, after the analysis of this sample pellets, it can we have said around 1.6 kg of MOX powder also, and it has been used again in the fabrication line for encapsulation of that fuel pellet, which has been analyzed by the XRF, and it has been encapsulated in the pin, and we have made approximately 7 number of spins extra. So if titrimetric method we had used, so we have lost 7 number of spins we are losing. But with the use of XRF, we have fabricated 7 more number of fuel. So that's why this such type of techniques, if it has been implemented at the plant scale, it is very much required. At second application, as I have told that, it has been again when we have got good reliability in the samples. It has been implemented in the determination of plutonium in the CRO and DRO. Actually, what is CRO? During the fuel fabrication, certain types of waste has been generated. It is CRO, clean rejected oxide, and dirty rejected oxides. What is actually clean rejected oxide? Because of sintering, sometimes we are having some chips of, means we are not getting the density. Pellets are perfectly okay, but because of some physical defects, it has been rejected. So that type of waste is called as clean rejected oxides. But when these clean rejected oxides has been reprocessed at our plant, it has been mixed with the various batches. So when these batches has been mixed, we do not have the isotopic composition of each batch because it has been mixed. So at the time of fabrication, we are determining the percentage of in the CRO with the NWCC technique, neutral well coincidence counting technique, which is basically depends upon the isotopic composition. But in the CRO, we do not know what is the isotopic composition and all. Suppose we have to do the plutonium percentage determination in the CRO, then again we have to do the analysis of the isotopic with using the T.A.P.S. So here again we have used our calibration standards. Why don't we go directly for the analysis of the CRO powder using the WDXRF with the existing calibration standards? And we have analyzed the samples, and this is the typical WDXRF spectrogram of the 21% MOX powder. This for 28%. And here you can see that we have compared the values we are getting with the NWCC method, the titrimetric method, and the XRF method. Here you can see very clearly that our values are very much matching with our titrimetric method. So here again we can say we do not need any isotopic composition for the analysis of the plutonium in the clean rejected oxide. And this also we have implemented in our plant, and we are routinely analyzing the samples of CRO using WDXRF. Other important applications of during fabrication is the direct determination of uranium in sinter deeply depleted uranium oxide, and of course we have also developed a technique for the determination of uranium and thorium in the AHWR field, and we have standardized all these things. Suppose the task given to us, we can directly analyzing the samples in the thoria-based fuel with the non-destructive method. As you know, that for the determination of thorium using dissolution itself a very big task because of single oxidation state. So where we can use this WDXRF method. So there are so much applications we have developed at our plant. So this is a conclusive summary. A complete non-destructive direct WDXRF method can be used for the uranium and plutonium determination in MOX fuel. The method has comparable analytical parameters with the titrimetric method. It is a very fast sample analysis, almost no sample preparation, non-destructive, no wastage of sample, avoiding laborious dissolution of acid and all these steps, And due to the complete non-destructive analysis, the sintered MOX fuel pellet could be used directly for their encapsulation inside the fuel bin. These are the publications we have got published during this program, and thank you for your kind attention.
Not completing within time. You can have few quick questions.
Ji sir. Yes sir, it can be done with the EDXRF also, but we have to have for the EDXRF or WDXRF, we have to have the calibration standard should be very perfect. If you are not having the calibration standard to the range, the accuracy and precision you require, you will not get the results. Like when we have prepared the synthetic sample or working standard for making the analysis in the direct sample analysis, we have theoretically prepared the samples with our weighing basis. After that, we have characterized that plutonium and uranium using the existing titrimetric method, and we have used that practical or experimental yield value using the calibration plot. That's why we are able to get the good results. Thank you.
You are telling this method as non-destructive testing,
yes,
but you are preparing sample and you are pressing the pellets, and that cannot be used again to fabrication of pin. Then why you are calling it non-destructive?
Can I get my slide? Actually, sir, it's only for making the calibration standards, and which can be used for the years. Only 5 calibration standards we have made using the aluminum cup. Almost it can be recovered also by back pressing the aluminum cup. And right now what I am telling, I am not making any sample preparation. I am not doing any sample preparation because whatever the product during fabrication we are getting sintered fuel pellet, I am directly analyzing that. I am not making this powder again and making this using the hydraulic press and all. It is used only for the calibration standard. That 5 pellets I have shown to you.
Thank you.
Thank you, sir. Yes.
Laser-induced breakdown spectroscopy that
Yes.
is also used for element analysis. Could you comment upon that?
Yes, sir. Laser-induced breakdown spectroscopy, our FCD of BRC Mumbai is working very nicely, and they have reported this thorium and uranium analysis using this LIPS techniques. They have.
How do you compare your XRF with the LIPS?
As far as this LIPS and XRF in this XRF is concerned, LIPS is some type of means you have to again break over the samples, or you have to.
That I understand. I am saying when now you have done practically BRC LIPS is being done and you have done XRF.
Yes.
Now at the end, what is the conclusion? Which one is better, or could you comment upon that?
Actually, both the techniques have their advantages and disadvantages. As far as my application is concerned, WDXRF is better than LIPS. And because we have achieved that much of accuracy and precision after round robin test and all. And this technique has been approved by the specification committee of the IG car, and after that only it has been implemented. Thank you, sir. Yes, sir. Yes, sir. Yes. Yes, sir. Yes, sir. Actually, yes, sir. Actually, I have seen one of the BRC report in the published in 1994, and I have seen that at the reprocessing plant they have they have actually proposed that such type of XRF systems should be directly should be installed during the online reprocessing of all your cells, cell 1 and cell 2 and all, so that you need not to do all this getting the sample and doing the coulometry and all this stuff. You can directly analyze the sample in line of your cell also, and definitely if I am getting the results because of my calibration standard accuracy and precision, I am getting the results. If you can make the sample of your own interest, means good accuracy and precision in the calibration standard, of course it can be done. It is my personal opinion. Actually, for this XRF, I have observed that if you do this ratio analysis, uranium by Pu or Pu by uranium intensity, so when it is perfectly means for the year it is constant. But if you go for the only uranium alpha intensity or plutonium alpha intensity, you measure today and tomorrow it will be fluctuated. But if you go for the intensity ratio, it is perfectly stable. I have personally carried out experimentally for the month of the same sample. I am getting again the same and the same result for the second digit, sir. Thank you, sir.
Thank you, Dr. Pandey.
Thank you, sir.
Now I request session chair to present the memento to speaker.
Come to the last oral presentation of the session. Presentation is by Sri R. Velmurugan, IP-CAR Kalpakkam. The title of his presentation is Challenges in Qualification of Particle for Fast Reactor Full Reprocessing. So this is probably an online presentation.
Velmurugan sir, can you hear us? Velmurugan sir, can you hear us? Velmurugan sir, can you hear us? Please unmute your mouse, mic. Sir, can you start your presentation?
feel regret for this technical hitch. We'll wait for another 5 minutes. Sir, can you hear us? Welcome, sir.
Yes. We could able to hear you, sir.
Yes. Sir, kindly share your presentation.
Sir, that screen option is disabled, sir. Here, sir.
Sir, just आप लॉग आउट करके वापस लॉग इन करेंगे. Can you?
Yeah, we are doing it, sir. We are doing it. We are doing it.
Please log out and log in again. Hello. Sir, can you try again? Welcome, sir. Can you hear us? Okay, sir. No. Please present your presentation.
Sir, now screen is visible, sir.
You are audible, but your my camera and presentation is not visible to us.
Sir, when we test Sir, when we tested at 11:50, it was working, sir. I could able to share the screen. But now that screen option, once it is coming, sir, now afterwards it is disabled, sir, actually here.
So that is all for this technical session. So there are some technical hitches while connecting online, so we feel sorry for that. On the behalf of the organizers, I thank speakers of this session. I extend our thanks to session chair Dr. K.S. Pindra sir and session secretary Sri J.K. Gayan sir for conducting this session. And I request Sri R.V. Bhatt sir, Chairman NCAS Tarapur chapter, to present a token of our appreciation to session chair and secretary of this session. Thank you, Bhatt sir. Thank you, Chair and Secretary. Now we all will disperse for a lunch break and will assemble sharply at 2 here in the same hall. And there is one important announcement for poster presenters. Please display your posters during the lunch time only. That is all. Thank you. Hello, check. Welcome back to post-lunch session. That is session number 7 of this 2 days symposium, NUSUC 2022. In this particular technical session, we have total of 3 invited talks by eminent speakers and a oral presentation which is converted from contributory research paper. The first among the invited speaker is Dr. T.A.P.S, Associate Director, Material Chemistry and Metal Fuel Cycle Group, IGCAR Kalpakkam. Second is Dr. P.K. Mahapatra, who is an eminent speaker from Radiochemistry Division, BRC, Mumbai. Third one in the series is Dr. Amrit Prakash from Radiometallurgy Division, BRC, Mumbai. The oral presentation from the contributory research paper will be by Dr. Jitendra Kumar from RMCAT Indore. For this technical session, may I now request Dr. Anant Sivan sir to chair this session and Dr. Vinit Kumar Mittal to conduct the proceedings of this session as secretary. Over to session chair and session secretary. Thank you.
Thank you, Mr. Ethan. Hope I'm audible. Very good afternoon to all of you. Welcome to this post-lunch session. As Ethan said, we have some interesting papers that are coming up. This will be very nice. I'm sure about it. Now I have the pleasure of introducing the first speaker of this session, Dr. Kiteri Joseph, who has been my colleague for more than 3 decades. It's my pleasant privilege to introduce her to the audience. She's from the 33rd batch of chemistry in the VRC training school and joined IGCAR in the year 1990. She has gained a lot of experience in the field of sodium chemistry, electrochemical hydrogen meter. She had made seminal contributions to the development of this, a very important contribution to the FBR program. She is an expert in thermal analysis, solid-state nuclear materials, and she did her thesis dissertation on nuclear waste management and continues to work on that actively and develop the iron phosphate classes for the first time, especially from the viewpoint of IGCAR. Based on the experience in thermal analysis, she indigenously built a drop calorimeter and built also an in-house made DTA setup for handling molten salts. She is part of the Indo-UK civil collaboration in the field of nuclear waste management, and she is presently heading the metal fuel fabrication and the pyroprocessing subgroup. It's my pleasure to invite her to deliver the talk. Dr. Kiteri Joseph.
Good afternoon, one and all. Thank you, Dr. Rananshwan, Chairman, and the Secretary who is present here. I know it is very tough time. Soon after lunch, first session, I know the time is a little tough, but I'll try my best to provide an overview of what we have done in metal fuel program. And I am representing a team earlier called as chemistry group, presently material chemistry and metal fuel cycle group, and I'll be giving the presentation this way. The overview will be on metal fuel fabrication. All the topics which I am going to discuss is on whatever we have done and what are the gap areas and what are the future plans. And metal fuel fabrication and characterization, achieved and future plan, pyroprocessing at lab scale again, and pyroprocessing at engineering scale, and the gap areas which I am going to cover. Metal fuel fabrication and characterization, Our objective is, future plan. As per our DAE program, we will be concentrating more on metal fuel. And so we have to have a hand-on experience for the fabrication and the characterization of the metal fuel. So initially we try to get experience on the casting of the blanket slug, which is uranium 6% zirconium slugs, and experience in fabrication of metallic fuel pins, and finally test irradiation of metallic fuel pins at FBTR. Now the slugs which of uranium, plutonium and zirconium was provided to us by BRC, and it has been converted to sodium bonded metal fuel pin. The dimension is shown here. I call it as 0.5 meter pin. And the facility for the fabrication of the blanket slugs, both at the lower level, say 1 kg injection casting system, as well as the bulk 10 kg injection system, casting system was fabricated. And what is this? This gives the schematic of the injection casting system. It consists of a process chamber, which is double wall water cooled system. The top one, which shows which gives the mold which contains quartz rods, which is inner surface is yttria coated. It has a facility for vertical movement and the facility to preheat and maintain at a specific vacuum and temperature. The bottom chamber, which consists of a graphite crucible, again this is yttria coated, an induction heating facility and vacuum and pressure ports and measurement facilities are available. This entire injection casting system containing process chamber, quartz cassette, associated mechanical systems are housed inside the glove box. All the control systems, power supplies, chillers, vacuum pumps, accumulation tanks, etc. are placed outside the glove box. This gives the flow sheet of the fuel pin. So first I will talk about slug casting and then fuel pin fabrication. Used are metal feedstock, induction melting and injection casting, demolding of the quartz and shearing of the slug, and then you have to go for characterization, both physical, chemical and metallurgical characterization. If it is yes, it goes for fuel pin fabrication. If it is not processing the quality control, it is again going back to the induction melting and injection casting. In the fuel pin fabrication, if you see, we use, you all know, T9 clad, and which is having end plug already welded, sodium extruded to have sodium bonding, then loading of fuel slug, end plug welding, sodium bonding. Again the fuel pin also goes for the characterization. Accepted fuel pins are gone for assembly. You all know uranium is always supplied to us by BRC and zirconium from NFC. We have optimized all the casting procedures for uranium 6% zirconium, both in 1 kg injection casting system as well as 10 kg injection casting system, meeting all the required specification, both physical, chemical and metallurgical. And this gives the fuel slug, which is blanket slug, which is uranium 6% zirconium. One particular slug, typical dimensions I have given here. Length around 345 mm, mass is around 113 grams. The specification is 4.94 mm dia. Density is around 17 gram per cc, which is greater than theoretical density, 98% higher. We are more concerned about the non-metallic impurities, especially oxygen and carbon. You can see the allowed specification is around 100 ppm, and what we got is around maximum is 85 ppm, and specification as per carbon is less than 5000 ppm. What we get maximum is around 1000 ppm. This is the process parameters. As I told you, we always use induction melting system. So the graphite crucible inner surface need to be coated with yttria. Presently, plasma spraying coating is used here. I'll come back to that later. And this graphite crucible is charged with the required amount of uranium and zirconium and then loaded down melting of the charge by induction, preheating the quartz mold inside the coated, again this quartz mold is coated with yttria, and the pressurized injection casted, withdraw the molds, demolding, ensuring, and again slug inspection. Right now we have done 3 pin capsules containing this dimension. ID and OD are provided here. We have done a small modification in yttria coating with respect to the inner surface of the quartz. Earlier we used slurry based coating system, which you can see how opaque it is. Solution route was resulted in improved adhesiveness. This is also yttria coated, and the surface of the slug, it is very, very homogeneous, and in addition we are reducing the waste volume. And this 531.5, this pin is under irradiation. What we need to fabricate is 1 meter pin, which is shown here. This shows the green color, shows the blanket slug, and this is the fuel pin around 320 mm and filled with sodium, and of course plenum and the end. Next is the physical inspection and the chemical characterization, what we are doing. Physical characterization, if you see, the dimension, density, defect study, morphology and distribution of major elements, and fuel, as I told you, it is given by BRC. Blanket set we have prepared. Pin dimension is this, and bonding is done, sodium bonding is done at 550 degree. This gives the XRD pattern of the fabricated slug. This gives the SEM picture, it's IDAX. And as I have told you, we have always seen the density always greater than 98%. Actual density, theoretical density is around 17.06. Next goes to the figure is not very clear. This gives the distribution of uranium as well as zirconium, the mapping. Major element tunnel analysis we have carried out by our typical Davis-Gray method for uranium and zirconium by gravimetry, and the trace impurities by ICP-OES. Non-metallic impurities, as I told you, carbon, sulfur by combustion method, and oxygen, nitrogen by inert gas fusion. And this is the uncertainty we observed with respect to the major elements uranium and zirconium. As you all know, the specification of the metal fuel and the blanket segments are well documented. And this gives the facility what was built in our lab. This shows the 1 kg injection casting system. The trial runs taken with copper melting with 10 kg injection casting system, sodium wire extrusion, sodium bonding at 550 degree, slug retrieval facility, and the characterization lab with respect to the metallurgy characterization as well as the carbon combustion method, cutting polishing machine. You can see the molten alloy which is prepared using IC, and of course the entire system needs to be under argon atmosphere, and so allied argon recirculation and purification system is also available. And we can proudly say that the entire this inert glove box train along with the facility has been it is a state-of-art facility dedicated by to the nation by the present Honorable President of India and at its allied facilities. And the fabricated sodium bonding fuel pin, that is UPUZR, received from BARC, is under irradiation. This gives the test irradiation data. Capsules containing fabricated pin, test irradiated, already discharged with this uranium zirconium. The objective is to understand the post-irradiation examination and hand-on experience with pyroprocessing at hot cell IGCAR. The irradiation which is going on is with 14% enriched uranium-6 zirconium, and the sodium bonded fuel pin with uranium, 19% plutonium and 6% zirconium. And we have uranium which is enriched with 19% uranium and 23 Pu6ZR, all are under irradiation at FBTR. And sincere thanks and the continuing support of BARC for providing us the fuel slugs. And the future plan, as I told you earlier, we were working on 0.5 meter fuel pin. Presently we need to prepare a sub-assembly which is 37 fuel pins to be provided to FBTR with uranium, plutonium, zirconium. And so you require a facility to have fabrication and the characterization of 1 meter fuel pin, which is in progress right now. This gives the schematic of that, and probably in the month or first week of July, we'll be getting all the glove boxes and we'll be assembling all the glove train. The second part of my talk, which is about reprocessing, which is that too a non-aqueous route, that is pyroprocessing. Pyroprocessing is, as you all know, high temperature electrochemical process, and there are two methods. One is electro-refining, another one is electro-winning. Electro-refining is done by ANL, RIR, Russian people do electro-winning. We follow the pyrochemical route developed by ANL, that is electro-refining. This gives the flow chart of the pyroprocess, the spent fuel, metal fuel, hexagon cutting, pin chopping, sodium distillation, and the fuel containing UPU, ZR, minor actinides, fission products along with clad taken for electro refining. And initially uranium deposit is taken, and subsequently we go for deposition of other things, and this is the flow sheet given. During the electro refining we have LiCl, KCl, eutectic. That salt has to be recycled by giving a salt treatment and actinide recovery, remove the fission products through passing through zeolite column, and this salt, which is free of fission products, can be reused again in the electro refining. Of course, we need to go for off-gas treatments, all the ceramic waste form, and the hulls and the noble metals which are present in the anode basket needs to be taken care, because it is a metallic waste form. What is the advantage of this pyroprocessing? High burn-up fuel can be taken, short-cooled fuels, and small high-level waste volume, because it is a solid waste form, and applied to the treatment of wide variety of spent fuel. Criticality hazard is low. Of course, we are able to deposit minor actinides along with the system. So that is for actinide recycling and burning. Co-location with the reactor. The process is compact, although the major disadvantage is you will be handling chloride salts at very high temperature, that is highly corrosive, needless to say. And then this is the chemistry behind the pyrochemical reprocessing. This gives the refiner cell, which consists of the eutectic salt along with uranium chloride, and you take all your fuel pin, chopped fuel pin in an anode basket, and by applying a suitable potential, you deposit uranium in solid cathode, and by applying a suitable potential again, you electro-transport some amount of uranium, plutonium, minor actinides into the cadmium liquid pool, and free energies of formation of chlorides are shown here. This clearly indicates that all the alkali and alkaline chlorides which are coming out are highly stable in the chloride medium, and the rare earth chlorides are mediocre level, and you are able to, because the uranium chlorides are less stable, you are able to deposit, and all the rare earth, the noble metals will be very, very less stable, so they remain in the anode basket itself. Generally, this entire process is carried out at 500 degree, and we, as I told you, SS crucible is used for this purpose. Uranium gets deposited at the solid cathode. Again, this SS 430 cathode, around it is at the voltage of minus 1.4 with respect to silver plus silver system. Co-deposition is done. Similarly, initially we do the solid cathode, and subsequently we go for deposition of the remaining. And as I told you, all the chlorides of alkali and alkaline are very, very stable, and so they remain in the salt, and this needs to be recycled. And what is the experience we have gained with electro refining? Actually, we started with 50 gram of uranium and UZR system inside a glove box with all the facilities. Subsequently, we went for building up a 26 meter cube containment box containing all the facilities for electro refining, transporting. This has a partial remotization methodology where we gained experience handling 10 kg of salt, one order higher, And maintenance of high purity argon atmosphere is containing 26 meter cube. And chopping of UZR alloy fuel pins, we have done even sodium bonded fuel UZR alloys. We have done electro refining of uranium UZR sodium bonded in 1 kg scale. Distillation and consolidation of uranium is also done. This gives the inner view of the system, that 26 meter cube containment box. This is the perforated anode basket where we take uranium or UZR or sodium bonded UZR. This is the salt bath containing LiCl KCl eutectic. This is the electro-refining vessel. This shows the uranium deposit, which is in the which I have shown it in an enlarged version. It's a dendrite form on the SS cathode. This uranium deposit will always have occluded salt also, because it is immersed in salt. So it will contain something like 10 to 20% depending on the methodology we use. So this gives the picture of uranium done. Actually, we have used the uranium received directly from BRC for the first to do 12 mm dia. 1 kg uranium was taken. We got the deposit of 1.05 kg along with occluded salt. The occluded salt was around 18%. Processed by vacuum distillation, salt removed, uranium consolidated, and we are able to get. Earlier we did uranium and uranium zirconium at the lab scale. Then we wanted to have an experience on molten salt electro refining of UPUZR, of course at a very low level, lab scale 50 gram level. So all the facilities we need to bid in inside hot cell. So we have done everything. It took some time for us. We have done electro refining of the UPUZR alloy at the 50 gram scale, and we have taken the alloy. This gives the solid cathode uranium deposit. This is the anode basket after electro refining. This is the photograph showing liquid cadmium cathode after electro refining. And the salt we used is around 400 gram. Redox behavior of all these things have been carried out, and cathodes uranium recovery, liquid for plutonium recovery. And once you know we have done uranium, plutonium, zirconium, we wanted to have experience on the irradiated UZR which was discharged from FBTR. So recently, 2.5 months back, we have completed this process also. Electro refining of irradiated UZR slug, and this is the cask which brought the UZR from RML to RCL, and irradiated. This gives the picture of the pin. Of course, RML helped us to cut the pin, as well as they distilled the sodium and provided us the pin, and we have done the electro refining. Once the electro refining is the first stage where uranium, the irradiated uranium deposit is shown here, and the characterization of the deposits is in progress. So what is our experience? In the lab scale pyroprocessing, electro refining studies were on plutonium UPUZR alloy done. However, consolidation studies, because the content of plutonium is very, very low, and we could not get conclusive results on the plutonium. Electro refining studies with respect to uranium, UZR, sodium bonded uranium zirconium alloy we have done, and we have also done electro refining of irradiated UZR at very low level, 50 gram level. Based on the lab scale experience, now we are building a pyroprocessing facility to have a batch process with respect to UPUZR at 250 gram level. That is also in progress. Having done the lab scale facility, we have gone for an engineering scale facility, which is called as PPRDF, Pyroprocess Research and Development Facility. Of course, this is a pre-engineered building, and it is internal steel structure. Our major aim of this study is to have complete remotization. That is the only this thing at 10 kg level of pyroprocessing. This gives the containment box, which you can see. The containment box capacity is around 500 meter cube. We have achieved around 0.12 volume percent as a leak leak rate. All the facilities with respect to pyroprocessing have been built. 10 kg level of pyroprocessing. This gives the salt purification system and allied facility. We have already synthesized 1 ton of LiCl, KCl eutectic, which is also pumped inside. And all the everything has to be, as you know, we have to take care of the moisture level, which should be less than 50 ppm, and nitrogen should be less than 20 volume %. And we have to handle highly hygroscopic LiCl salt. So all the system should be under argon atmosphere, which we have achieved. And this gives the overall picture of the electrodes, attaching, detaching system, electro-refining vessel, scrapping station, automated vacuum distillation system. We have tested this using KCl salt at 950 degree with a vacuum of 10 tar, and we have melted copper, which I'll show you in the next slide, around 1100 degree as a prerequisite. This gives the picture of the copper taken and after melting. And this is what we have completed. The entire cadmium metal has been transferred, and melting of the salt, all the testing has been done. Cold and hot purging of argon is done. Totally 900 kg of LiCl, KCl salt has been transferred, and presently it is at the temperature low. We are keeping it 400 degree. We have already added cadmium chloride. Salt sampling had been done. Transfer of uranium has been done for equilibration into uranium chloride. It is in progress presently, and then shortly we will be consolidating and quantifying and characterizing. Based on this is the future. First plan is with uranium, next to do with UZR, and next to do with UZR. This is the first phase. And the gap areas, metal fuel fabrication side, if you see, today Sri Satya was talking about laser decontamination system of the fuel pin. We will be taking their expertise on that. And additional characterization facilities for handling UPU-ZR alloy, and for the characterization using SEM. Already SEM has arrived, and sample preparation facility, everything in progress. And presently, as I told you, spark, it's not plasma, spark spray coating is done inside a graphite crucible, but we are able to use this crucible only for 5 runs, not beyond. So we have to look in for subsequent usage using dip coating, and we are working on that. We are working on the after demolding broken quartz tubes. The experts are here who are working on borosilicate glasses, and we'll be working towards that. In the case of pyroprocessing, all the characterization facilities we have to build in. Experience on compact distillation facility inside hot cell, and of course we have already carried out lithium tagged zeolite. Bulk synthesis up to 2 kg done, and we have to go for now to the pilot scale and the plant scale. And actinide drawdown process is the second phase of the pyroprocessing, where you selectively take care of the minor actinides. And this is our team. Without them, which is not possible, who takes care of PPRDF, metal fuel fabrication, and metal fuel pyroprocessing, and this thing. My sincere thanks to Director IGCR, Director RDTG, EIG, and Director MC MFCG for providing me this opportunity to present before you the facilities built and the achievement done. And my sincere thanks to the organizing committee of NUFUC for providing me this opportunity. I stand before you for proceeding this, especially because of the former director of IGCAR, Dr. A.K. Patil. Thank you, one and all.
Thank you, Dr. Kiteri. It's been an excellent portrayal of the accomplishments at MP and MFDG. And now the talk is open for questions. Time for a couple of questions. Yeah, Mohammad.
Excellent presentation, madam. This uranium deposit from pyroprocessing we have been hearing for quite some time, yes. I think for last maybe 15-20 years. Yes. And recently I see that your plutonium thing you started.
Yes.
Now what is the purity of plutonium you are getting in the
Sir, actually whatever we have done, 50 gram of UPU-ZR itself is 50 gram. Okay, so you know the amount of plutonium we could not get consolidated result with respect to plutonium, to be honest. So we are building the facility to have little higher handling higher amount of plutonium. Only when that facility is ready, we'll be able to give you data on.
250 gram you were saying.
Yes, batch process 250 gram. Maximum 500 we would like to do, but in batches of 250.
What about minor actinide americium or something? Any plan is there?
Presently, we do not have facilities. We have to go in for a specific facility for handling MA.
Okay, madam. Thank you.
Okay. If there are no further questions, then it's my pleasure to thank Dr. Kiteri Joseph for illuminating with the recent advances in the metal film recycle development. With that, we move on to the next talk by another accomplished researcher and my long-standing friend, Dr. P.K. Mahapatra, who in fact doesn't require much of an introduction to this audience. Yet, for the sake of completion, let me do this. Dr. P.K. Mahapatra was born in Cuttack, Odisha, did his MSc from Utkal University, Bhubaneswar in the year 1985. He joined the Radiochemistry Division BRC in the year 1987 after graduating from the 30th batch of the BRC Training School. He did his PhD from the University of Bombay in the year 1994 and did his post-research at the University of Mainz, Germany, under the Alexander von Humboldt Fellowship, which is one of the most celebrated fellowships. His research interests include complexation of actinides and separation of actinides and fission products using novel extractants. A fellow of the National Academy of Sciences, Allahabad, Dr. Mahapatra is a recognized guide of Mumbai University and the Homi Bhabha National University, Kumbh National Institute, which is a deemed university. Dr. Mahapatra is an associated editor of Separation Science and Technology and one of the editors of Radiochemica Acta. He is the editorial board member of several prestigious journals, including Solvent Extraction and Ion Exchange and Desalination and Water Treatment. Currently, he is heading Radiochemistry Division of BRC and has over 400 publications in peer-reviewed international journals with over 7,500 citations. Over to Dr. Mahapatra.
Thank you, Mr. Chairman, for your kind introduction. In the beginning, I want to thank the organizers for giving me this opportunity to present our research in the actinide extraction in room temperature ionic liquids, which is carried out over maybe last 10 years or so. This is the outline of my lecture. This is what are ionic liquids. I think many of you in the audience know about the ionic liquids, but for those who are not aware, I will give a brief introduction. Ionic liquids in separations, metal oxide dissolution, mostly actinides, solvent extraction of actinides, mechanism of extraction, applications in the nuclear fuel cycle, and conclusions. Now coming to the room temperature ionic liquids, I think this room temperature ionic liquids are known for the last maybe more than 100 years. That is in 1914, the first room temperature ionic liquid was reported by Walden. But the real application has come in the maybe this last part of the last century, that is in the late 90s actually. This room temperature ionic liquids application are there mostly for this solvent extraction, because the water immiscible ionic liquids were discovered by then. Previously it was very difficult to carry out solvent extraction studies. Now these ionic liquids, as you can see that this is the sodium chloride, which is a salt, and this is the C4-MeM NTF2, which is a liquid. This suggests that at room temperature these salts are ionic liquid. These salts are liquid form, so that's why they are called ionic liquid. Now the ionic liquids, they are considered as the green alternative to the normally used solvents, which are which has very high VOC content. That's a volatile organic carbon in the solvent extraction. Now these ionic liquids, they opened up possibilities whether we can really carry out studies with the non-volatile solvents because of the problems like toxicity, the inflammability, etc. Now one of the major advantages of ionic liquid is that the ability to fine-tune the properties which will allow their use in place of a conventional organic diluent. So these are the cations, typical cations of ionic liquids, and these are the typical anions, and there can be thousands of ionic liquids can be constructed by using this type of cations and anions. Here I have shown some of them. There are of course many more such ionic liquids are possible. Now the properties of the ionic liquid are non-volatile, almost no vapor pressure you can say, non-flammable, and one very interesting property is the large electrochemical windows. Many electrochemical studies have been carried out using these ionic liquids. As Dr. Kithiri Joseph has shown in the previous studies, the previous lecture, this pyrochemical processing. So people have suggested ionic liquid as actually alternative of this pyrochemical processing, where instead of using high temperatures like maybe 500 degrees as Madam was telling, you can have in room temperature, you can carry out this dissolution of the metal oxides, and also there subsequently you can do the electro refining or electro evening, whatever you would like to do under the suitable experimental conditions. Now this also there are applications of these ionic liquids in synthesis and catalysis. As I mentioned, these water immiscible ionic liquids were prepared in the 90s, and that's how the solvent extraction possibilities have opened up. But there are of course some people criticize the ionic liquid, even though we call them as the green solvents, ionic liquid, because of their non-volatile, non-toxic and non-flammable properties. But some people say that not so green, that I will discuss maybe in the course of this lecture. Ionic liquids in separations. Ionic liquids have really displayed very unique properties in the separation science. First of course will be like, I will discuss about the dissolution and electrowinning. In solvent extraction, solid phase extraction. This solid phase extraction and liquid membranes I will not discuss in the lecture because of this lack of time. But I will mostly give some example of dissolution and solvent extraction. Now coming to metal oxide dissolution in ionic liquids. Metal oxide dissolution is quite logical for room temperature ionic liquid because it's similar to pyroprocessing. And these are factors which are responsible for the metal oxide dissolution are several factors like free chloride in the medium, free acid in the ionic liquid. You can add RTL acids into the ionic liquid phase, or it can be generated in situ. Water content. This helps of course in the chemical reaction, as well as it reduces the viscosity of the ionic liquid. Lattice energy of the metal oxides, it is mentioned here, greater than 10,000 kilojoules per mole, it's difficult. Less than 7,000 kilojoules per mole, it is easy for the dissolution. Structure of the oxide, temperature, viscosity, oxide particle size, gas purging, and also sonication. All these things will be helping in the dissolution of the metal oxides in ionic liquids. Pyroprocessing I will not discuss here because Madam has just given a lecture about pyroprocessing, how in the LiCl and KCl you can carry out the electro refining at 500 degrees Celsius. But so I go to the dissolution. What I can do is, we have taken some uranium oxide we have taken, and we have done the dissolution in this reagent, that is T.A.P.S, and T.A.P.S was taken in ionic liquid. So what was the beauty of this work is that you can carry out this UO3 dissolution in T.A.P.S or SDSP in ionic liquid, and this the dissolved product whatever you get, it gets split into two parts. There is one upper phase and the lower phase. So the upper phase is rich in the uranium, the metal ion is there, and the lower phase is depleted. Actually you don't have much of uranium in this lower. That way you can have sort of a dissolution as well as pre-concentration. So this we have seen actually by what is the species in this case. We have seen it normally whatever these uranyl complexes of T.A.P.S, where two T.A.P.S dimers are actually forming this complex. As you see here, this was seen that this organic extract, these UV spectra of this uranyl extract, and whatever is dissolved in the T.A.P.S in RTIL, the spectra appear similar, suggesting that the species are similar. So that means this T.A.P.S molecules are coordinating with the uranyl ion. We have also carried out cyclic voltammetry studies suggesting that this uranium can be isolated from this ionic liquid dissolved phase. Now I will give some example of solvent extraction. Of course, the first prominent publication in ionic liquid, this solvent extraction involving ionic liquid was this crown ether, which is a dicyclohexane 18 crown 6, and this extraction of strontium using this crown ether. So you can see here these are the values shown here, like this crown ether generally is used in, previously it was reported in chloroform or this toluene, this type of solvents were used, and you can see that this metal ion extraction with the crown ether is almost not measurable. NM means not measurable, you are not getting any extraction. But if you have this ionic liquids, if you have, then you can get very high extraction. And here you see that ionic liquid without any crown ether, so you get D values maybe are a little less than 1, so that means maybe 40 to 50% extraction. But if you add the crown ether in the ionic liquid, then the extraction becomes very large. Particularly this particular ionic liquid, you can see 10 to the power 4 is the D value, so it increases enormously. So this was the first major actually publication which suggested that ionic liquids can be used for a very high extraction of metal ions, which was not possible in molecular diluents. So this is one very interesting observation with this ionic liquid based solvents. Now I will take for the actinides, because that previous one was strontium. See, this is very famous, our you can say the bread and butter of our nuclear fuel cycle. This is the uranium extraction by TBP, and this is the use of dodecane or any non-polar solvent is used for this as a solvent. The dodecane plus 30% TBP is used, and this is the profile. D value of uranium as a function of nitric acid concentration, molarity. You see that this extraction goes up, and then after certain concentration of nitric acid it starts falling off. That is because of the computation of the acid cations for this TBP. Now in case of ionic liquids, several ionic liquids are taken here, where the only difference is that this alkyl chain, this is a C4-MIM NTF2. NTF2 minus is the anionic part, and C4 MIM plus, this is the cationic part. And we have changed actually this alkyl chain from C4 to C5 to C8 to C10. And you see that when the alkyl chain is, length of the alkyl chain is minimum, that is the butyl chain is there, the extraction at lower acidity, that is 0.01 molar, is rather high compared to dodecane and all other ionic liquids. And you start increasing the alkyl chain length, then this extraction falls off. But with increasing nitric acid concentration, this extraction increases. With all these ionic, first it decreases and then it starts increasing. So this is because of some different peculiar extraction mechanisms in the lower acid range for ionic liquids and also at the higher acid concentration range. One important point here is that if you increase the cationic or the alkyl chain in the cationic part of the ionic liquid, it starts mimicking that of the molecular diluent. The C10 MIM NTF2, more or less it follows the pattern of that which you see in case of the dodecane. That is, you have a sort of a monotonous increase and then subsequently falling off. So the mechanism of this is that you can have this type of mechanism, that where you have uranyl ion with TBP and this CN MIM plus, this is the cationic part of the ionic liquid, and this is in the ionic liquid phase which is exchanged to the aqueous phase. That means you have this UO2 2 plus ion, it forms a complex with TBP, and this is without any counter anion, it gets extracted to the ionic liquid phase, and where you have this the simultaneous partitioning of the cationic part of the ionic liquid to the aqueous phase, suggesting that this extraction equilibrium is complete. Now in case of the molecular solvent, this is the mechanism where you have the TBP in case of dodecane. But if you have this ionic liquid like C10 MIM NTF2, then also you have similar type of extraction mechanism. So this is a solvation mechanism, that is a cation exchange mechanism. So these are the very typical of the ionic liquids where you have this cation exchange mechanism. Now I go to another very important ligand which is studied in the nuclear fuel cycle is the DG, or the diglycolamides, which for the minor actinide partitioning it is used. Now the relative extraction of americium and europium was studied by one American group, the Bruce Mincher, and they have taken this tetrabutyl diglycolamide in octanol and C4-MIM NTF2. So octanol is a molecular solvent and C4-MIM NTF2 it's an ionic liquid. The top figure shows the extraction profiles in octanol, and you see here there are interesting properties similar to TBP in molecular solvents. you have an initial increase up to a certain acidity. Here it is around 2 to 3 molar, and then subsequently the europium value is more or less saturating, and the americium value is showing slight decrease in the extraction with increasing nitric acid concentration. Second point is that the europium extraction is always higher than that of americium. You can have a separation of minor actinides from the lanthanides by tuning the acid concentration. Now you go to the ionic liquid medium, you find that it is the other way. So it is actually falling off with increasing acidity, and that is showing slight increase at acidity higher than 6 molar. And also second aspect is that this americium and europium extraction profiles are more or less superimposable, suggesting that the separation behavior what you see in case of the molecular diluent is not there in case of the ionic liquids. This is the work which we have carried out in our laboratory, where you have taken this ionic liquid, this C8-MIM NTF2 as the ionic liquid, and TODGA is the diglycolamide extraction. We have studied the extraction of americium, uranium and plutonium, and you see that in all cases we are finding a decrease in the extraction of the metal ion up to 6 molar, which we have studied, and this Mincher et al. They have reported beyond 6 molar there was slight increase. Now coming to another very popular extractant, which is the beta diketones like TTA, which is used in the, I think, in the process laboratory, in these are plutonium process reprocessing laboratories. So this HTTA, you see, this also is it forms a extraction with the metal ions. The way it is shown here, like metal ion in the aqueous phase and the TTA in the normal molecular diluent phase, it gives the TTA N of the TTA. Mostly it is 3 TTA, because that charge neutralizes the charge of the metal ion if it is americium. Or if it is europium, it is again 3 TTA, but if it is uranium, you have again 2 TTA. So depending on the metal ion, the species changes. But if you go to the ionic liquid medium, actually there the extraction behavior becomes different. Instead of this 3 TTA, you have actually 4 TTA minus. That type of species is reported in case of the ionic liquid medium, suggesting again a very different extraction mechanism, and the extraction of metal ions, this trivalent metal ions by TTA, is taking place by another mechanism called the anion exchange mechanism, because you have the anionic species here and it is gets extracted with the anionic part of the ionic liquid. Extraction with amines, this is another class of extractants which is used in the front end of the nuclear fuel cycle. Here we have seen that again anion exchange mechanism is prevalent in this case. The extraction is rather very low in these cases, but then the amine solubility also was very low in case of with the ionic liquid medium. But what we have seen that we are taking these different amines like tributyl amine, trihexyl and trioctyl amines. We have seen that with the again with the increasing alkyl chain you find that the extraction is decreasing, but the profile is showing that it is actually you get reasonably good extraction with these amines. But if you see this as a function of hydrochloric acid concentration for uranium and plutonium, we have seen that because of the presence of the anionic species, the extraction increases with increasing concentration of the HCl, because it forms anionic complexes which are getting exchanged. As shown here, you can see that it's uranium UO2Cl4 2 minus, and similarly for plutonium also you get PuCl6 2 minus species which are getting exchanged with the anionic part of the ionic liquid, that is the NTF2 minus ions. This is that we have also carried out studies with multiple DGA ligands. This is a calixarine with DGA arms grafted onto it. We have shown in this case some very interesting observations. We have seen that the extraction was taking place at a very low concentration of the ligand. You see here with ionic liquid, of course, as I have shown in case of the crown ether case, for strontium extraction, that extraction is enormously high. If you take 0.01 molar TODGA in ionic liquid, that is C8-MIM PF6, then we have seen that this D value is, you get reasonably good D value even with 0.01 molar. And if you go for the C4 DGA ligand, which is the calixarine, you go even very low concentrations of this ligand to get very high extraction. So it's shown here is the comparative performance of these extractants. This TODGA in dodecane, you get the separation factor D americium by D uranium is 132, and americium plutonium is 25. TODGA in RTIL slight improvement with the americium uranium, and again improvement with the americium plutonium. Then C4DJ in dodecane, you have americium uranium is 45 and 173 for americium plutonium. But you go to the ionic liquid medium, then you find an enormous improvement in the suppression of americium and uranium. Again, this may be because of the typical mechanisms which are operative in case of the ionic liquid medium. You get good suppression factor improvement also in americium plutonium, maybe around a little less than twice. But for americium uranium case, you get a very, very significant improvement in the suppression. Now the mechanism extraction I will summarize here as shown in case of the amines. It's the anion exchange. Also the TTA in ionic liquid medium is anion exchange, cation exchange for TBP, and solvation or ion pair also extraction is possible if you have, I have shown in case of the C10 MIM NTF2 for TBP. So now this nature of this extracted species were elucidated from several type of studies like slope analysis from solvent extraction studies, or spectrophotometry, ESIMS, or even EXAF studies were carried out at RRK at Indore, which has which has confirmed actually about this nature of this extracted species. This is a cation exchange mechanism which I have already mentioned, that with increasing this cation of this this alkyl chain of the cationic part, you see that whatever extraction you get at the low nitric acid concentration start falling off. But if you want to carry out some studies at low nitric acid concentration, definitely you can go for this type of ionic liquids. So this one I will skip. Now this is the anion exchange mechanism. As I have shown for the uranium nitrate nitric acid medium, you see this type of species are formed, and the exchanging part of the ionic liquid is the TF2N minus ion, which is from ionic liquid medium it goes to the aqueous medium. And for the TTA medium I have told, this is again TTA4 minus is formed here, which is go to the ionic liquid medium, and this TF2N minus anion in the ionic liquid, it goes to the aqueous phase. Now for the basic extract analysis amines, actually this is very much favorable with Cl4 minus if it is there, that means a hydrochloric acid medium in presence of amine, the extraction is significantly enhanced. So here I would like to again highlight here that the one thing you can see that this TF2N minus is partitioned to the aqueous phase, and in the previous this TBP extraction case you find that this CN MIM plus ion is partitioned to the aqueous phase. So this is actually basically the disadvantage people talk about the ionic liquid system. Even if you get a very high extraction, but the problem is that if you are also partitioning certain cases this cationic or the anionic part of the ionic liquid, which can be actually problematic while processing these aqueous raffinates. This is a summary of this extraction mechanism, what I have shown here. Now this is a solvation mechanism which is similar to what we see in the case of the TBP dodecane system. You have metal ion with M number of nitrate and then X moles of these ligands, and you find this type of species which is formed. This is also formed in the ionic liquid medium, and also this is some sort of a, you can say, ion pair mechanism also which is formed here. So this is a summary of the cation exchange mechanism, and this is the anionic exchange mechanism, and this is the ion pair exchange mechanism which is summarized graphically. Now apart from this, there are some unusual extraction mechanisms, as I have already shown in case of TBP with the longer chain longer alkyl chain cationic part of the ionic liquid. Similar thing also has been reported for the extraction of uranium as well as americium using Cyanex-272. This is actually a acidic extractant, and for this it is taken actually C10 MIM NTF2. This is the ionic liquid which is taken, as well as dodecane, and you see the profile of this extraction is more or less same for this ionic liquid as well as dodecane. This suggesting that a similar type of extraction mechanism, but this was reported in 2005, so people are thinking it is a sort of a unusual extraction mechanism. But now we understand that because of the alkyl chain length effect, so this type of behavior is there. If you go to the lower alkyl chain ionic liquid, then the behavior will be different. Similar also was the pattern seen in case of the americium extraction using Cyanex-272. Coming to applications in nuclear fuel cycle, metal ion back extraction can be a problem because, as I have already said, normally if we have our solvation type of mechanism, then low concentration of nitric acid you have very low extraction, and at a moderate concentration, maybe 3 to 4 molar, you have very high extraction, and then it is falling off. So if you want to strip the metal ion from the extracted phase, what you do is you do the back extraction at a very low concentration of the nitric acid. So that is what has been working for the normal molecular solvent systems. But if you go to the ionic liquid, low nitric acid concentration, the extraction is very, very high. So that means stripping is a problem. So in such cases, what you should do is you can take actually a buffered medium of a complexing agent. Like you can take acetohydroxamic acid or DTPA or EDTA, and you take in guanidine carbonate medium. So this is a Japanese work actually where they have shown that the very high stripping can be possible when you have this type of DTPA or EDTA in guanidine carbonate medium. And then of course finally they have shown that this directly they have deposited this uranium, extracted uranium from the TVP phase. Another important aspect is the radiolytic stability of the ionic liquid, which is very, very important, because ionic liquids are once you want to use them, so we should know actually how is their radiolytic stability. So we have taken several ionic liquids with cationic part varying from the alkyl chains in the cationic part varying from C4, C6 and C8, and the anionic part we have taken PF6 and NTF2. So then these type of ionic liquids we have taken, and we have seen that very strange color change was seen after you irradiate to around 1000 kilo gray. It was gradual, of course. So color change was there for the ionic liquids, and also there are changes in the physical parameters. Viscosity values also they increased. So I will show here in the next slide. So this is actually the water uptake values in case of this ionic liquid, irradiated ionic liquids. So it is plotted as a function of the dose. These are the PF6 ionic liquids, and you don't see any regular trend here. But in case of the NTF2 ionic liquids, we have seen some sort of a regular trend as it is increasing. But also we see that more or less there is not much change actually in the percentage water uptake values if you take this NTF2 type of ionic liquids. Also we have carried out this acid uptake studies, and apart from the water uptake, we also carried out acid uptake and uranium extraction studies. And as shown here, you find that this uranium extraction behavior almost not showing much change if you take the NTF2 type of ionic liquid with a varying dose rate up to maybe 1000 kilo gray. There is not much change actually, taking 1.1 molar TBP from 3 molar nitric acid. Another important parameter is the third phase formation. This is a work from IGCAR colleagues, Dr. K. Venkatesan and Dr. T.G. Srinivasan, their group. What they have shown that this europium loading they have studied with 0.2 molar CMPO and 1.2 molar TPP in dodecane, and also 0.2 molar CMPO and 1.2 molar TPP in C4-MIM NTF2. So what they have shown that third phase formation was seen in case of the dodecane medium, and if you carry out these studies with ionic liquid, there was no third phase formation was seen. So this also they have carried out studies with varying temperature, and this was very interesting because the ionic liquid medium third phase formation was not there. Now to conclude, the room temperature ionic liquids are superior diluents compared to the molecular diluents because of high D values and high separation factor, as I have shown in a particular case where we have used the caligzarines, diglycalamide functionalized caligzarines. Whereas the American people, they have reported with the linear diglycolamides that separation factor was not so good for americium and europium separation. Applications to environmental sample are to be a big advantage, because environmental sample will be at generally if you carry out the separation from environmental samples, then what we do is for most of the extractants, because they are working in the acidic medium, so we do some sort of a feed adjustment. Then we maybe around 3 to 4 molar nitric acid we carry out the extraction. But in this case ionic liquid medium, you don't have to do that feed adjustment, because at low acidity itself that extraction is enormous. So you can carry out maybe the as received samples from then maybe water samples can be used directly for the extraction using ionic liquid. Radiation stability suggests better performance compared to molecular diluents. This again, of course, because of the viscosity of the ionic liquid, that the recombinations of the radicals is much more favored in ionic liquids compared to in molecular diluents. Loading of the metal ions appears very promising, because no third phase formation was seen in that study which was reported from our IGCAR colleagues. Major disadvantages include, of course, the slow kinetics of when you use ionic liquids because of the viscosity effects. Most of these ionic liquids are highly viscous. Also high aqueous solubility, as I have shown in the cation as well as the anion exchange mechanism, because of this cationic part solubility and the anionic part solubility respectively in the water phase. And of course stripping issues where you can carry out the stripping by using a buffered complexing medium. Studies on large scale processing, these are lacking, and I hope that people will take it up at a large scale. The ideal option, of course, is a direct dissolution and the electrochemical deposition resulting in processes which are free from aqueous processing. And this may appear more promising than the pyrochemical processing of which people have been reporting. But then there are a lot of challenges in this study also. We have to see the different metal ions, how their separation will be there, how this can be managed. Actually, there's waste from this ionic liquid medium. All these things are challenges which should be taken up. Thank you for your kind attention.
Thank you, Dr. Mahapatra. Really a wonderful talk, very comprehensive and a crisp presentation. So I congratulate you on your accomplishments and the talk.
Thank you.
I myself have become inquisitive after listening to your talk. One major problem which we have also been pondering over has been the viability of room temperature ionic liquids as an alternative medium for reprocessing applications. So what is your general comment on that?
Actually, there is a long way to go. Actually, if there is no large scale studies are available, and the problem, as I said, it's a viscosity. When you run a process, the things you expect should be done fast compared to ionic liquid, where it taking sometimes even hours to attain the equilibrium. But then there are people are going for other type of ionic liquids, maybe nitrogen or phosphorus based ionic liquids, which are much lower viscosity. So that is one thing. But then again, this has to be validated by extensive studies. So this is many very stressed reports are available, lab scale studies. At this moment, I will say that even though this has been suggested as early as maybe this beginning of this century, but still the lot of work needs to be carried out. I think there is excellent review, chemical review, I think 2012 by Seng Dai, who is an ORNL very established worker, who is the first paper appears to be that strontium iodide with the crown ether, that is by Seng Dai's group. So Seng Dai has a review written a review in 2012, chemical reviews. There he has suggested that this can be alternative to the nuclear fuel reprocessing, and our IGCAR colleagues, Professor Basudeva, they have also written a review in separation science technology suggesting it can be. But then there are also other people who have said that have criticized heavily, like Jed Kolaric. He has written a review suggesting that ionic liquids, they may not be that much possible to. So I think a lot of studies has to be carried out to answer this that blanks which are there. Those needs to be answered by carrying out extensive studies and scaling up. And of course, even though radiolytic degradation, again there are many people suggest that degradation is less, but there are some reports which suggest that that can be detrimental also to the process.
Very elaborate and very correct answer. In science, we can always, afford to differ. And I feel why the pyroprocessing have been chosen with the molten salts is the worst that can happen to a solvent is it will get ionized, radialized to give ions. And already the molten salts are ions, so there is no further possibility. But whereas in the ionic liquid, still we have molecular entities, molecular ions we still have. So that's going to be a number one problem. Number two problem, I am also not sure whether we'll be able to solubilize a metal as such. Therefore, this being a contestant to the pyrochemical process, still I am not able to think of as on today as a technology. So
very mostly oxides. People, whatever report, there are a lot of works. I think this year we have published a review also on oxide dissolution in ionic liquids, and we have reviewed. There are a lot of people have carried out studies, very interesting studies, but then a lot more has to be carried out.
Sure. Thank you. Now, more questions from the audience? Right, if there are no questions, hopefully there will be more discussions during the free time. I thank the author for the wonderful presentation again. Thank you very much.
I request you.
the third talk in this session will be by Dr. Amrit Prakash, who joined the 32nd batch of training school after the completion of MSc Chemistry from the Patna University. He completed his MBA in Human Resources in the year 2002 and PhD in Chemistry from Mumbai University in the year 2003. He joined Advanced Fuel Fabrication Facility in 1989. He was associated with the quality control of various types of nuclear fuels, namely mixed oxide fuels for PHWR, BWR and PFBR, using various analytical methods. His area of research includes developments of the techniques being used for chemical characterization of the fuels, apart from the design and development of components of the systems for the glow box adaptation. In the radiometallurgy division, he is associated with the process control of the carbide samples for analysis of M2C3, oxygen, nitrogen and the carbon content. He is also associated with the quality control of pellets and fins, which include the inspection of dimensional checks of fuel pellets and the integrity of welds using X-radiography. He was also involved in the study of oxide materials for hosting minor actinides and investigations of their phase relations and thermophysical properties. Presently, he is a head of the process control and nuclear material accounting section and quality control and inspection section at the radiometallurgy division. He has more than 100 publications in various national and international journals, proceedings and papers in symposia and conferences. It's my pleasure to invite Dr. Amrit Prakash. Over to Dr. Amrit.
Thank you, sir. Good afternoon to everybody. So my topic is experience of alpha waste management at RMD. But before I proceed, I would like to thank YANCAS chapter Tarapur, because I have seen the nascent YANCAS Tarapur chapter to now it is completely matured, and the way this symposium has been organized is really very it is appreciating to all the organizers as well as the management who are supporting them. The topic of this alpha waste management is having a different relevance, because wherever the fuel fabrication facilities are available, you require to have alpha waste management. Generally, we give afterthought, and when the drums get generated, we start storing. But at the same time, we have to think about the processing of that alpha waste. So thanks to our NRG BRC, they have taken lots of drums from CAT4 and they have also taken proactive action to process that waste, and already the lab is in a good form, and I think it will start processing very soon. So in RMD, Radiometallurgy Division, the work was started with a view that if we can have a demo facility for the processing of this alpha waste, then this will be a good feedback to our waste management persons, waste management divisions. So that feedback also they have taken, and they have modified also some of the processes, and that has taken a good shape. Whatever I am going to talk, this is not the only route for the management of alpha waste. There are many other routes also. This is one of the route, and we have just you will see that this is very much successful in getting the alpha category 4 has become category 1. Though it was a small scale experiment, few drums only we could take up, but this was a good feedback. If you see, generally I will be talking about fabrication in RMD and MFD. Similarly, there are other divisions also, but RMD is mainly involved in the fabrication of FBTR fuel, as well as some R&D work on mixed oxide, thoria, uranium oxide, etc. And MFD, metallic fuel division, is mainly involved in the plutonium metal fuels. Source of alpha active waste generation at RLG. What is the source? So main source is it is globox generated waste. As you all know that plutonium is to be handled inside the globoxes. So waste mainly it consists of your PVC, that anyway I will go in the next slides, but considerable amount of pure contained solid waste generated during various activities connected with plutonium fuel development and fabrication. In addition to this, potentially contaminated waste generated in amber areas, mainly from decontamination and housekeeping activities in the laboratory. If you see, generally this waste is categorized broadly. Alpha waste broadly is categorized in two categories. One is category 1 and other is category 4. Category 1 waste is lab generated waste, amber areas. We always tell the people that whatever waste has come to amber area, whether even if it is a cardboard, it has to be disposed in the drums only. You cannot take it out just like that. So category 1 waste, the lab generated waste, and it is having less activity, less than 4000 becquerel per gram, and it is anyway, it is suitable for shallow ground disposal. But category 4 waste, which is of a waste of our concern, it is the process generated waste from glow boxes, and it is having the activity of more than 4000 becquerel per gram, and it is having low beta gamma emission, of course. So what is the strategy for alpha waste management? As you all know that for any waste philosophy is reuse, recycle, reconvert, all those things are there. But what we do at our end, first is how to minimize the generation of waste. That is the first philosophy. Recover all or major portion of plutonium from the waste and reuse recovered plutonium fuel cycle. As you all know, plutonium is not only strategic, it is a very, very important material so far as our nuclear fuel cycle is concerned. Volume reduction. Volume is another thing. Generally, you all might have experienced that many times we do not think that this material I am taking inside the glow box, whether really it is required. If you want to introduce one, we generally introduce two. So similar, there are many incidents we don't apply our thinking. So that reduction in, if you reduce the volume itself, half of the problem is solved there itself. Production of a suitable waste matrix to render it safe and economical to store, transport and dispose in deep geological depository. The above can be addressed. How it can be addressed? Selection of a proper process for assaying, conditioning and recovery. It is very important. For example, in our radiometallurgy division, packet counters are there for assaying of plutonium. That is based on sodium iodide thallium detector. So packet counter are having the advantage over the wisdom monitors, because in wisdom monitors, all the packets you are counting in a drum. You do not know, some of the packets may be category 1 also. But in packet counters, a cake packet when you count, you sometimes find that this packet qualify for the category 1. So there itself you can segregate. So you should have a proper process for assaying, conditioning and recovery, optimization of process layout, use of glow box strain instead of isolated or freestanding glow boxes. More number of glow boxes, more is the volume of waste generated. So if you are having a glow box strain, so less bag in and bag out, obviously the waste generated also will be less. Use of automatic hand dryer instead of blotting paper. This anyway has completely discontinued so far I am seeing in the RLG. Now nowhere this blotting paper and other papers are kept. Everywhere automatic hand dryers are being used. Avoid mixing of category and category 4, that I told. This is possible only by the proper assaying system and training or retraining of operators. This is the general flow sheet for our mixed oxide or this carbide fuel fabrication. I am not going in the detail of this. This already has been discussed by sir's morning session. In general, this waste is categorized in 3 parts. By physical means, that is physical nature, that is solid, liquid and gaseous. My today's talk is based only on the solid waste. Solid waste again you can divide in 2 parts, compressible and non-compressible. Among the compressible, it is the plastics and cellulosic, and non-compressible, it is the metallic. Of course, the metallic waste generated is very, very less as compared to the compressible waste. Type of solid waste generated at radiological laboratories are: category 1, waste generated in day-to-day functioning of lab. You all know that this cotton mop, surgical gloves, plastic sheets, whichever is used outside of the glow boxes for general cleaning of the labs, or suppose some equipment has come, so the cardboards or the boxes, they all become category 1. Category 4, that is generated inside the glow box. Now, management of solid waste. Both the solid wastes are anyway category 1 is they are packed in 200 liter MS drums and compressed volume reduction and disposed in air surface depository. Category 4 is being stored. Now this also practice we have started, that category 4 is now stored in, I think in T.A.P.S also they have started earlier. They are storing in SS drums, because when we observe that the processing lab is getting delayed or proper procedures not there, so better to store in SS drums, because after 10 years, 15 years, when you start taking the drums for processing, you may feel that the bottom of the MS drums has got some problem, some broken, then it will be another problem. So problem with another problem it will become. So better to keep the category 4 waste drums in the good SS drums, so that processing after the labs are ready, that time it will not be a problem. Alpha waste management in RMD, this demo facility, the philosophy of that, minimize the amount of waste, recover all or major portion of plutonium, and activity and volume reduction. Broadly speaking, this management consists two parts. One is volume reduction, other is activity reduction. Volume reduction, either you compress it, the volume gets reduced, and activity, that I will show that how by this series of filters the activity can be reduced. This is a general picture of showing that how much the volume of plastic, cellulose, metallic, graphite, etc. are generated. You can see here that the plastic waste or cellulosic plastic waste are much percentage is very high for so far as volume is concerned, but the activity wise, if you see, cellulosic waste activity is more, volume is less. Plastic waste activity is less but volume is more. Metallic, graphites are anyway they are less in general. This demo facility, which is in one of the lab in our M39, this consists of the trains. This train is having, it starts with, if we enter the waste material from this, there is a oxidation box, then there is the ultrasonic system. This is mainly used for metallic waste. Washing machine, that is for, and it is having centrifuge also, filter bank or shredding machine, then it is hot compaction is there, and the pneumatic press, and finally for cellulosic waste this incinerator is there. This is a general diagram of our globe boxes, the train of globe boxes which is housing this facility, and here again you can see that the PU estimation and categorization. After PU estimation and categorization, this is category 4 waste. If you divide into compressible, non-compressible, compressible again comes into cellulosic and plastic. The cellulosic waste is incinerated, then it gets converted to ash, and from ash you can recover the plutonium. Similarly, the non-compressible, compressible other part is plastic, where it is mainly the most source is that your gauntlets and gloves. This plastic, this is washed and then it is hot compacted, and then it is suitable for burial at NSD like category 1. The other part is, other is metallic also, but this volume is very less, so I will not discuss much on that. Category 1 waste, of course, that is compressible, non-compressible, and it is finally directly it goes for burial. Now very good practice have started, I think, in all the plants because of the RIT and different committees coming. So different drums are I have seen everywhere is kept, so that compressible is separate, non-compressible is separate. Long back that practice was not there, but now this practice is very good in everywhere. This practice is being maintained, so that the segregation or the processing becomes very, it is convenient. Now I will go step-wise for plastic waste. Plastic waste, that is mainly your gauntlets, gloves, which are having very high volume. So first it is, you have to sort it out so that non-plastics is separate. You have to cut it. Then we are doing preconditioning, which is not required for the A3F waste, which is already oxide waste. And this is then washing and filtering. Then it is shredded into small cut pieces, and then after cut pieces they are studied for both cold compaction and hot compaction. Hot compaction is more successful as the volume reduction is 10:1. So if it is 10 drums, it can be converted into 1 drum. And filtrate contains activity that has to be taken care of separately. Washing for plastic waste, we do this washing. In our RMD, we have gone for alkaline washing. There is acid washing also. There is no debate over that. Acid washing also equally it is applicable, and in many countries acid washing are being taken. In our case, we have taken alkali, that is 0.1 normal sodium bicarbonate. There is a small, and you are very happy to see that most of these equipments were like our Atmanirbhar Bharat, except few equipments. Most of these things were indigenous. Washing machine was only purchased locally. So there was a agitator washing inside a washing machine. There was a basket centrifuge that is also available in the market. Ultra filtration bank up to 0.1 micrometer. This filter also is our typical membrane filters available in our nowadays. You all may be knowing that BRC has been supplying this filters for domestic purpose. It is similar to that. There is separately an offline filtration by membrane filter up to 0.01 micron. Advantage is effective pollutant recovery, simple technology. Only disadvantage, or you can say we have to take care of the criticality issue because it is a liquid handling. So criticality is, it is more prone to criticality as compared to solid things. Generation of secondary liquid waste. You are ending up with liquid waste, but of course that is not a problem, as I will discuss afterwards. This activity of cleaning mediate various filtration steps. You can see that the washing machine, this after this mainland water comes for washing machine, where all this your plastic waste, after washing, there is a strain and cloth filter where it is further filtered. Then is a basket centrifuge. What I want to say that there is a series of filters, and all these filters, nothing is they are very imported or very costly. They are mostly available in the local market, indigenous one, and after series of filters, it has been seen that the waste gets completely activity free. Washing machine, you can see here that this is the washing machine and centrifuge assembly. In the subsequent photos, you can see it in a better way. This washing machine is a whirlpool washing machine, but it does not give any rotatory motion. It is only gives to and fro motion. So this is the typical first glow box, which is housing this facility for the plastic waste. You can see here tanks. Behind this tank 2, overhead tank 2, there is overhead tank 1, where overhead tank 2 first is filled with water, and this water is overhead tank 2. This goes water to the your washing machine, and washing machine first we put the plastic waste, which is cut into small pieces. Then it is filled with the water. Then there are small pumps through which first it goes through the centrifuge or the cloth filter. Then it goes to the underground tank is there. From there again it is pumped over at that tank 2, and from tank 2 again after filtration it goes to tank 3. Then again from tank 3 it goes to the washing machine, and in this way a series of filtration it goes to different tanks, and finally this water becomes completely free afterwards. This water is also reused. It is not taken out just like that. We see the color after series of operations, and when the color fades or it is not good for reuse, then only it is taken out and sent for ETP, effluent treatment plant. But otherwise this water is reused for the subsequent operations. Membrane filter for final filtration of cleaning media. This is the ultimate one. This again is a typical membrane filter. This is the final one after the giving the series of washings to one cycle. Then finally it is taken through this membrane filter, where we get up the 0.01 micron size particles also getting trapped, and we get the clean water from there. Shredding machine. This is the shredding machine, where this after washing, whatever these plastic waste are coming, they are shredded into a small pieces. After this shredding, small pieces, this is the hot compaction press, where these pieces are taken and they are heated up to and compacted in a hot environment around, we give 80 to 90 degrees centigrade, and this become small pieces. And then after compaction, you can see that this is hot compact. These pellets, if you come to RMD sometime that visit the lab, then we can show you. This is the hot compact pellet. After this hot compaction, this becomes this type of shape. And if you go for cold compaction, this is the shape. But this was just for study purpose, that hot compaction is better than cold compaction. So this type of pellets you get after your this PVC, gauntlet, etc. bags processing. Compaction press, this is the, you can see here, these are the pellets which has come afterwards, and these all, some of them had taken out, and they were counted again, and it was found that they have become category 1. That was a very good feedback, that with this process we can make category 4 into category 1. These pieces are still kept inside the glow box for demo to the visitors or to the people who are interested in going for this process. This again is showed the same picture. 1 drum PVC waste hot compact pellets in glow box. Now the second part, the plastic waste, this was the process. So volume control by the hot compaction and activity control by the series of filtration. Now this is the cellulosic waste, which generally having more activity, more plutonium content. You can see these are the cotton mops or the filter papers or the papers or similar type of things. Nowadays that also process discontinued. Now ashless filters have come, so people have gone for that, but still this cellulosic some or other material come or are generated inside the glow box. So for cellulosic waste there are many techniques, but in RMD a study was made with the incinerator. The cellulosic waste from process line category 4, after sorting, means it is cellulosic or non-cellulosic, this is sorted out, and then charge compaction as 1 TSI, and then incineration is excess air, and this finally it gets converted into ash. So here also you can see that the number of drums become a single drum, and it is only ash. Though we are still having ash, and we have given to different laboratories to process it and to find out if we can recover the plutonium. Very good encouraging results we have got, but still we have not continued that process, because in A3F also they have done the dissolution microwave, and I think 75 or 80% was got dissolved, and some organic materials were there. So still a study has to be done if this process has to be followed further. Volume reduction of cellulose by incineration. This is our laboratory type incinerator. This incinerator again was made long back. This incinerator was not made in my time. It was made long back some other person, and this incinerator was already available. Only this incinerator glow box was connected to the plastic processing glow box, and then this incinerator was used for the cellulosic waste. So laboratory type incinerator, completely it is indigenous, made in our workshop only. Batch type incineration, and takes 4 hours to 5 hours to complete one cycle. Batch size is 1 kg. Temperature, it is heated up to 800 to 1000 degrees centigrade. Flue gas treatment after burner. Heat exchanger is there. Mist eliminator, pre-filter and HEPA filter. Secondary waste genesis kept minimum because it is solid waste. If you see, this is the diagram. This series of diagrams, only main you can see that this is the ash which is coming out from at the bottom of that burner, and these are only to take care of the flue gases or the fly gases which are coming. Heat exchanger is for cooling, and mist eliminator if some water droplets or water vapors are, in case it is there. This is a copper wire mesh where it is trapped, and this pre-filter is there because it was observed that the HEPA filter is getting choked frequently. So afterwards there was a pre-filter was provided there, so that this HEPA filter can be used for some more time. So this is a simple incinerator where it is charged by a air. You can say it is a air blower. So our Sarjay Khan used to tell it Sigri. So सिगड़ी में आग लगाते हैं and then it starts burning. It is so impressive to see that you can see even fire, and slowly it used to burn and used to control the air by regulator, and slowly it will burn for 4 to 5 hours, and then you will get the ash. Pneumatic press for cellulosic waste. So before we put inside the incinerator, this also is compacted, and after compaction only we are putting inside the incinerator. Volume reduction of cellulosic waste and recovery of plutonium by incineration. This is the globe box which is containing the entire incinerator, and the cellulosic waste processing is done here. So these are the category first 4 waste drums, which are now sent to RSMS and the other places. And thank you for your kind attention. And I am very much thankful to Mukesh Chaudhary, Nete, Sarjay Khanji, whom I always tell Guru, because he was the person who has developed, made all these things. We are getting the fruit from his karmas, I can tell. PG Behre sir, head RMD, and Vivek Bhasin sir, that NFG. And I am thankful to all the audience for their patient hearing. Thank you.
Thank you, Dr. Amrit Prakash, for a very elaborate and nice presentation of great practical value. Now the clock is open for questioning.
Yeah. No, sir. By hot compaction, it is the volume which is reduced. And category 4, no, sir. Category 4 gets converted into 4 into 1 by the successive filtration. Because these entire particles get trapped in the filters, and filters again are cellulosic. So again you can incinerate these filters, and you can use it, you can again trap from the ash. So it is the successive filters which make category 4 to category 1. And hot compression leads to the volume reduction.
Sir, what do you do with the filtrate? Because filtrate will be carbonate in nature.
Yeah, that's what I told. Filter or filtrate?
Filtrate.
Filtrate, we are again taking it for filtrate of liquid. You were telling.
What about the washings?
Washings, we after successive runs, we see the color of the water, as I told you, and we see the activity also. If it is having some minor activity, we send it to ETP after its treatment or the checking, and if it is completely free, it can be used.
This contains plutonium, no?
It is no, plutonium gets gets trapped into the filters, membrane filters. I told you, na.
Okay.
There are successive filtrations. There is a cloth filter, then is a basket filter.
And
there is
from the membrane, how do you recover back
from that filters? Again, these filters, membrane filters, are again cellulosic in nature.
Achha.
This cellulosic is taken as a cellulosic waste.
Thank you.
Yeah.
Sir, this incineration process, it takes around 4 hours for one batch of 1 kg.
Yeah.
And then second, the reduction ratio is around 1:20, you have shown. So can we go for plasma gasification, because it will take only 1 minute for the complete process, and then reduction is around 90 to 92%.
Yeah, I told you in the beginning, this is not the only route, because now BRC, where the processing lab has been put, they have slightly modified this, because they have even for, I think, gauntlets also, instead of washing, they have gone for incineration mostly, and for incinerator also they have gone for some other process. So there are very different routes, but here you can see the cellulosic waste are having volume is less, but activity is more. So even if you are taking 1 kg, it is a very big amount, because after compressing you are getting this, and then 4 to 5 hours you getting completely ash. From ash you can again find out some procedure to take the urine plutonium back.
Plasma gasification is completely BRC technology.
Yeah.
We have developed it,
Yes,
and
yes.
then it will take only 1 minute as compared to 4 hours.
Yes. But that has to be come out, because that has to come out. Now you have to start taking category 4 waste drums. You have to do this. Then only we can have some feedback over this. But this is being done, and we are having the feedback. That is the difference.
Thank you, sir.
Okay. Category 1, category 4 waste. Yeah.
Falling under alpha and non-alpha waste.
Alpha.
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 That is 200 nanogram.
100 nanocurie per gram, or it is coming similar to 4000 becquerel per gram.
Yes, sir.
Yeah.
Then less than 20 nanogram is a non-alpha.
Yes, yes. Yes, yes.
Okay, that shows that it's a talk of very practical importance, a lot of practical importance. Thank you very much once again. And also I thank the secretary of the session, Mr. Vinit Mittal, and I thank the organizers for this opportunity. I'll do the honors to the speaker as usual. Yeah, there is some rescheduling. There is an additional oral presentation in this session. Yeah, titled Fiber Bragg Grating Sensors for Temperature Monitoring in Nuclear Fuel Cycle Facilities by Jitendra Kumar RRCAT Indore.
Good afternoon, everyone. And, first of all, I would like to thank the organizing committee for allowing me or providing me the opportunity to present my work, which we are carrying at this RRCAT Indore. And this is our team, including both from RRCAT and from BRC Tarapur. And title of my talk is Fiber Bragg Grating Sensors for Temperature Monitoring in Nuclear Fuel Cycle Facilities. Basically, at RRCAT, we are developing this advanced type of fiber Bragg grating sensors, and we are searching for the applications in radiation environment or high temperature environment or other inaccessible areas where normal sensors cannot work easily. The outline of the talk will be like this. First, I will discuss some challenges in this sensor deployment in the harsh environments. Then this FBG or this fiber Bragg grating based sensor that we have developed at RRCAT, and the studies we have carried out like for the enhancement of the temperature sustainability range of these sensors, and radiation hardness testing of these FBG sensors, and finally deployment or the installation of these sensors in some radiation environment like fuel fabrication BRC Tarapur. Challenges for sensor deployment in harsh environment. The main challenge is the high radiation. In this environment, normal sensors cannot work properly, so the new sensors are to be required to be installed at these locations. Then the temperature range is up to 800 degrees centigrade, and the required accuracy is of the order of plus minus 1 degree centigrade. Acidic environment is there. In acidic environments, normal metallic sensors cannot work properly. High microwave power is there. It may lead to some sparking of the sensors if the metallic sensor is there. Then EMI is there, high voltage, and multi-point sensing is required. So multiple thermocouples or multiple RTDs are required for sensing the temperature or strain or any parameter at several locations. Temperature sensors that are already available in the market are like thermocouples, RTD, IR sensors are also there. And what we are doing, we are basically giving the solutions to this temperature monitoring, a new type of sensor, that is FBG sensors. And this can be used in the areas where these sensors are, it is not easy to use these sensors in the areas. And that is known as fiber Bragg grating or the FBG sensors. These type of sensors are basically fabricated inside the core of an optical fiber. What is an optical fiber? Optical fiber is basically a glass wire. It is made of silica, and the diameter or its structure is like this, in which inside the core of it is of the 8 micron or 10 micron around, and then there is a cladding, then there is a buffer of 250 micron, then there is a jacketing. So the size of this optical fiber is of the order of a human hair. So by this slide I want to show you that the size of the sensor that we are fabricating in the optical fiber is very small. So it can be easily integrated into the wide variety of structures if we are going to monitor the strain or temperature of, or if we want to encapsulate this type of sensor in any type of tubes like metals or ceramics. So it is very easy to install in that locations. Now what is fiber brag grating? Fiber brag grating is basically this I have shown, it is the optical fiber. In this optical fiber, this is the fiber core. It is of the basically diameter around 10 micron. What we are doing, we are creating a periodic refractive index modulation inside the core of this an optical fiber. This structure, this fiber brag grating structure, or we can say this is going to act as a sensing element in fiber brag grating sensors. And the important thing is, this is wavelength encoded sensors. For this fiber brag grating, like this is the lambda cap, if it is the period of this two fringe patterns, or I can say this is the period between two planes of the refractive index modulation, then the this brag grating is going to reflect a light at this particular brag wavelength, and that brag wavelength will depend on two parameters. One parameter is the effective refractive index of this optical fiber, and the other parameters is this period of that optical fiber grating that we have created inside the core of an optical fiber. This I am going to show you by this small animation. Like if a particular light, it is having 4 colors and it is incident on this optical fiber from one side, what we are going to observe is one light is going to be reflected this is the brag wavelength, or this lambda b, depending on this effective refractive index and that period. And we can see in this figure also, if this is the broadband light, this is coming from one side of this fiber brag grating. So in the transmission spectra, what we are going to get, it is a dip, and in the reflection spectra, there is a peak which we are going to get. So this type of sensor can work in remote locations where we have to install these sensors, and by monitoring this change in the brag wavelength or by monitoring the reflection spectra of the FBG. For FBG temperature sensor, if we apply temperature to a particular fiber brag grating, then what is going to happen? This lambda b, basically this brag wavelength depend on two parameters. One is the effective refractive index and other is the period. Temperature is going to change either the refractive index or the period, and in the due to the combination of these both effects, the brag wavelength, this delta lambda or this lambda is going to change. So this delta lambda b is the change in the brag wavelength. So by monitoring the change in the brag wavelength, we can estimate the temperature at a particular location. This is the one of the example of this I have shown, as the temperature is changing from room temperature to 100 degrees centigrade. This is, so the brag wavelength is also changing. So if by any mean we can monitor the brag wavelength at a particular location and some temperature is changing, then again we can monitor the brag wavelength, again temperature is changing. So by monitoring the change in the brag wavelength, we can estimate the temperature at that location. This is one of the one in this trace I have shown that if this is the trace at 30 degrees centigrade or the room temperature, and the temperature at the particular location is changing, this wavelength is moving. So by the shift of this wavelength, we can monitor the temperature at that particular location. Like for 300 degrees centigrade, it is moving forward in the right direction. So it can work up to 1000 degrees centigrade, and there are two parameters are there that are going to affect the temperature sensitivity of this particular fiber brag grating. Advantage of this fiber brag grating sensors are that it is very small size and lightweight, so it can be easily integrated, and in normally inaccessible areas it can be easily used. It is, since it is made of this glass fiber, so it is immune to this radio frequency, microwave and electromagnetic interference, And for nuclear radiation, it is also resistant to the nuclear radiation. This can be used in distributed sensing, or multi-point sensing can be done using this type of sensor. Its response time is very fast, and the remote location sensing we can do. Even at the distance of 1 to 2 kilometers, we can sense that temperature or strain very easily with a normal optical fiber. FBG activity at RRCAT. What we are doing at RRCAT? Basically at RRCAT, this fiber bragg grating setup based on the second harmonic, or we can say this copper vapor laser based, this writing facility has been developed at RRCAT. This CVL or this copper.
We have only 2 more minutes, please.
Just 2. Okay, and this facility has been developed at RRCAT, and by this facility, what we are doing, we are fabricating the fiber bragg gratings and utilizing them in various applications. This is the fabrication facility in which this is the copper vapor laser. From this copper vapor laser, we are getting 2 radiation. One is green radiation and one is yellow radiation. And by using this second harmonic generation setup, we are generating UV light from this setup. And then by using this inscription setup, we are writing fiber bragg grating. This is an indigenously developed setup at RRCAT. And the parameters of the FBGs fabricated this setup are that we can write gratings of different type of grating, like type 1, type 2, or different type of grating that are reported in literature. We can write this type of gratings with this setup. Normally, this normal fiber bragg gratings, they cannot sustain temperature for more than 500 degrees centigrade. So we have basically developed a technique to increase the temperature sustainability of this fiber bragg grating, that is by thermal regeneration. And this is the typical setup used for this thermal regeneration, in which the fiber bragg grating is kept inside a oven, and on the one end there is a AC source. It is providing the light inside the optical fiber, and on the other end, what we are observing, we are observing the change in the bragg wavelength. And this is the type 1 grating. Initially, it can sustain up to 300 to 600 degree temperature sensor. But what we do, we apply a proper thermal annealing schedule, in which we increase the temperature of the FBG in a very fast manner, and up to 900 degrees centigrade. And what we observe, initially the reflectivity of the FBG decreases, and after certain time the FBG reflectivity increases. This area, this is the type 2A, or we can say regenerated FBG, and this type of FBG can sustain temperature up to 900 to 1000 degrees centigrade. So basically we can fabricate fiber bragg gratings that can sustain the temperature up to 1000 degrees centigrade. And the stability of this fiber bragg grating sensor has also been, we have done basically the thermal stability studies, in which the reflectivity of the FBG, what we have done, we have monitored the reflectivity of the FBG at particular temperature, that is at 900 degrees centigrade, and by extrapolating the decay in this reflectivity, what we can estimate, the FBG at 900 degrees centigrade can sustain up to 6 to 10 years. So this is the lifetime of our FBG. And these FBG sensors have been validated at intense gamma radiation at higher up BARC, where the cobalt source was used and dose rate was 11.7 kilogray. What we have found, the reflectivity of the FBG initially decreased, but the wavelength shift was of the order of 35 picometer. And the sensor I have already discussed is the wavelength encoded sensor. So there is no any major effect on the sensitivity of fiber bragg grating. So this type of sensor we are using for the temperature sensing. And this type of sensor has been installed at the fuel fabrication facility BRC Tarapur. The challenges at these locations were the high temperature. This was overcome by regenerated FBG. This can go up to 1000 degrees centigrade. Then the high radiation part that we have tested for 1 megagram radiation. Then HNO3 environment, we have done the Teflon coating on this optical fiber so that it can survive HNO3 environment. Then high microwave power, the ceramic tube packaging was done so that the high microwave cannot affect this the performance of the fiber bragg grating sensor. Then temperature monitoring at multiple locations, since the multiple fiber bragg gratings can be written in the same fiber, so it can be used for the multiple locations. Then data collection from remote location. It is the property of the optical fibers, as we can sense the temperature at very far locations. And this is the temperature sensor setup that is developed, and this is the display system for this optical fiber grating sensor, and this is the fiber bragg grating encapsulated in this sensor. And this type of sensor was installed at this fuel fabrication, and the result what we get, that reliable and accurate temperature measurement helped in precisely controlling the process, and the spillover of the uranium plutonium reactor solution was avoided. To summarize, I can say that FBG from copper vapor laser radiation we are writing at fiber bracketting. They can sustain temperature up to 900 to 1000 degrees centigrade, and the radiation hardness of this type of sensor has already been tested at 1 megagray. And these types of sensors have been, and one of the location is like A.P.S Sitarapur, where we have installed these sensors. And there is a huge scope of this FBG sensor deployment in capital intensive sectors, national security, and a wide variety of industries, research installations. We are basically providing these type of fiber bracketings to various institutes, including R&D institutes and research, basically universities and IITs, IISc, for their research work and their the use of this type of fiber bracketting in various applications like strain sensing, temperature sensing. And these type of gratings are fiber bracketings are available through incubation center RRCAT. So if anyone requires this type of grating, they can contact to the incubation center RRCAT, and from this we can provide the fiber bracketting. Thank you very much.
Thank you, Mr. Jitendra. It's been amazing. And the talk is open for a couple of questions now before we depart for tea. Okay, if there are not particular questions, probably the discussions can ensue. One question there.
Hello, I have a few questions.
Yes,
first of all, that how fast your detector can measure the temperature?
Sir,
I believe that it's a contact measurement system.
Yes, sir.
And what is the minimum time it requires to sense the temperature?
Basically, it's optical signals. So all these things depends on the interrogation system.
No, suppose I have a setup where I am just heating it for milliseconds.
Yes, sir.
Suppose it is a laser heating.
Yes, sir.
It is heating for milliseconds. Within temperature, it goes to 700. Then it comes down.
Yes, sir.
Will it be able to measure the temperature?
Yes, sir. It can measure the temperature. It depends on the interrogation time that is the interrogator is taking.
Okay.
For the safe side, we can say it is less than 1 second. It can easily measure. If the interrogation time of this interrogator that is available in the market is of the order of millisecond, we can measure.
Okay. And then when you are writing the fiber with your copper vapor laser second harmonic,
Yes.
that is ultraviolet laser, what actually happens to the core? Physical, I am asking that it changes the refractive index.
Yes, sir.
Why
yes.
the refractive index changes, that is one thing. And whether you are removing the clad, where you are making the
No,
grating.
sir. No, sir. Very good question, actually. So you have the, I think, basic understanding of this fiber bracketting. Actually, we are not removing the clad. The coating of the fiber is being removed so that this UV light or the interference pattern of UV light can fall on the fiber, this optical fiber. The grating is being generated inside the core of an optical fiber, and that is very important. Why? Because the core of an optical fiber is doped with germanium, and the cladding is never doped.
Okay.
So the core is having basically absorption of this UV light, and what is going to happen in the core? Basically, due to the doping of the germanium inside the core, there are certain defects. These are known as germanium oxygen deficiency centers. These are there. And due to the absorption of this UV light, that is in the range of 240 to 260 nanometer, the defect centers, this germanium oxygen deficiency centers are going to change to defect-induced defect. New defects are being created. And due to the change in the new defects, there is a change in the absorption spectra. So we can say due to some this Kramer-Kronig relation, if there is a change in the absorption, the refractive index of that location changes. So if the fringe is falling on the core, so at the certain location where this light is falling, refractive index is changed. And nearby location where the fringe is not falling, refractive index is the original one. So there is a refractive index profile inside the core of an optical fiber.
And then how do you change this what I call grating period?
It depends on two things. We can write fiber bracketings using phase mask. That is basically phase grating is phase mask grating is there. If the light falls on the phase mask grating, we are having +1 order and -1 order, and their interference is there. Fiber is kept at that locations. If the period of this phase mask is changes, so the wavelength of this FBG can be changed. And second method is, this is basically interferometric methods. If we take the light to certain angles, and the angle of this light is changing, this gap is changing.
Okay, thank you.
Okay, thank you, sir.
Okay. Thank you, Mr. Jitendra Kumar.
Hello. I thank all the speakers of this session and thank for becoming part of this symposium, arriving at Tarapur from different parts and distant parts, especially despite of their busy schedules. Further, I thank session chair and session secretary for conducting this session. May I now request Pradhan sir to present. May I now request Pradhan sir to present a token of our appreciation to session chair and secretary for conducting this session successfully. Thank you, Pradhan sir. Thank you, sir. Now we all will disperse for tea break and will sharply assemble at 16:05. And this after, there is a last technical session which will go in 3 parallel sessions. One is for the contributory oral presentations, one for offline posters and one for online posters. Please assemble at 16:05 again in the hall. Thank you very much.
Hello. Hello.
Hello. Hello. Hello. Hello. Hello.
Hello. Hello.
Hello. Hello. Sir, hello. Hello. Sharon, sir. Can you hear us, sir?
You are audible, sir.
Okay, I will try sharing the presentation.
Okay, sir. Fine.
We are shared, sir. Could you see it?
Yeah, sir. We can see your presentation.
Yeah.
Sir, please pin your.
Yeah, we have put it on full screen.
Your
Can
camera,
you see on full
your
screen?
camera is not there.
Okay, I will switch on the camera also, sir. 1 minute. Can you see our video stream, sir? Camera?
Yes, yes. We can see your camera. Your audio is okay. And sir, one
Okay.
request. You are present.
Yeah.
You are showing, sharing your PPT. So
Yeah.
please share slideshow.
Yeah, sure, sir. 1
By
minute.
pressing F5, that window you please
Yeah.
share.
Yeah, I pressed F5 now. Can you see full screen, sir?
Slideshow I am not able to see, but your PPT is visible to me. Us.
Oh, it's not in the slideshow mode. It is shown in the PowerPoint now.
You.
Okay, sir. I will just share it as an entire screen share, sir. 1 minute. 1 minute, sir.
Okay.
How about now, sir?
Yes, sir.
Hello.
Yeah, sir. That is perfect.
Are you seeing it full screen, sir? Okay.
Yeah, it's perfect, sir.
Okay.
Sir, please next slide. Okay, sir.
Yeah, we are
Okay,
moving
sir.
to next slide.
Yes. Okay, sir.
Okay.
Okay, whenever you say we will present, sir. Whenever you are alerting the time. Hello.
Yes, yes, sir.
Yeah, whenever the time is allotted for this presentation, we will share immediately.
Okay. Yes, sir. We will ring you. That means Jitendra sir will ring you.
Okay.
Before that.
Okay, okay. We will be online actually. I'll talk to Jitendra sir again.
You be please online, sir.
Okay, okay,
Okay,
okay.
sir.
Thank you, thank you.
Okay, okay.
Thank you. ஒன்றும் பண்ணலையா எனக்கு திருப்பி பண்ணி ஆகும்
Hello. Very sir.
Yeah, we are available here, sir.
Sir, please close your presentation right now, sir. Your presentation will be taken at the last, sir.
Okay, then. We will be logged in and we will wait online, sir. Hello.
Sir, pardon?
We will be online, sir. We will continue to be online.
Yeah, you please remain online, sir.
Okay. Thank you.
नहीं आया नहीं
I request all the delegates to have their seats. For this technical session, which is the last technical session of this 2 days symposium, I invite Dr. T.A.P.S. Joseph ma'am as session chair and Dr. Alice Rathore to assist her as secretary of the session. There are total 5 oral presentations in this session. I request session chair and secretary to conclude them within 10+2 concept. And over to session chair and secretary. Thank you.
Good evening. Good evening. Thank you. A sincere thanks to the organizers for providing us this opportunity. And as indicated by the organizing committee, please take care that the presentation is only for 10 minutes and the question and answer session is for next 2 minutes. Thank you.
Good evening, Chairperson and fellow delegates. I thank organizers for providing this opportunity. Now for last 1 day, and we have been listening to all high-profile research and high-quality R&D perspectives. There are some basic fundamental infrastructure development which we would like to share with the delegates. And I will be sharing a case study of NRB Tarapur, where we have planned and designed for a long-term flood management perspective of a low-level solid waste. Basically, after Chernobyl event, Fukushima event may be taken as one of the watershed event for nuclear industry, which have changed many paradigms of design basis and design fundamentals of the nuclear infrastructure. And flood has attained a significant importance in view after this Fukushima event, and all over the world the review codes or design bases have been revised and they have been upgraded to look after the perspectives which were perhaps earlier were never thought of. So in the same line, now we know that Fukushima event, the flood which has occurred in Fukushima, that has the waste management problem is still persisting in Japan of the low level waste management, and where the nearby sea area has been still contamination issues are there. So there has been a review in Indian scenario also, and ARB has subsequently revised its siting provisions and the design basis of the different nuclear infrastructure facilities have been now accounted in the revised codal provisions. Earlier it was mostly focusing on nuclear power plants and other nuclear facilities like recycle facilities or fuel cycle facilities or support infrastructure support facilities. They were not part of the ARB safety guides or codal provisions. Now in the revised codal provisions, they have accounted for the all kind of facilities, and in that the solid waste, low level waste, their design basis of flood protection has been now made at par with a low power research reactor or a MOX facility, and they have categorized in 4 kind of categories. And this category 1 is where the highest or the off-site hazard potential are there, that is of the all nuclear power plants, power generation plants. NSDF has been given in this next category, that's category 2, where on-site radiological hazard potential is there. So now the design basis for the flood management or design basis flood is now for category 2 structures has been defined as return period of 10 to the power minus 3 of 1000-year return period. And to give a perspective, this is the design basis which for all our earlier nuclear reactors have been designed, their flood management part. So T.A.P.S 3-4 or Kakrapara or MAPS, they have been designed to that flood basis now for which now we have to design the low-level solid waste burial facilities. I'm giving just an overview of now whatever the revised code provisions are there. Apart from that, the grade levels should be sufficiently high, or it should be designed such a way that they are able to take the flood load or flood hazard to a return period of 10,000 years, 1,000 years. That is all cyclones or any intense precipitation or any kind of a river flood or dam break studies. In addition to that, there is another perspective that is of local intense precipitation. For that, the revised siting code has given the guideline that it should now, the drainage system should be designed for a return period of 100 years. So all nuclear infrastructure facilities, irrespective of whether it's a low level or category 1, category 2 or category 3, they have to be built with infrastructure of drainage, site drainage with a return period of 100 years. That is quite a conservative design. So with this this revised code provision which came in 2015, that coincided with our development of expansion of solid waste management facility of BRC Tarapur. This is the overall layout of earlier layout of BRC Tarapur, and we come from we are somewhere here 13 kilometers away. As we go towards Tarapur side, we come from this way to the plant premises. First, there is NRP construction which is going on. Then BRC complex is there, T.A.P.S 1-2, T.A.P.S 3-4. Now this NSDF or low level solid waste management facilities are here. This is earlier name as waste burial facilities. Now it is being expanded. This is in satellite how it looks like. This is the road which is coming over here. Now this has been expanded. Earlier was a rectangular kind of thing. This further expansion we can see, that is expanded part, for which now this revised codal provision has been was required to be implemented. This is that layout. This was the existing facility. This is almost filled up with low level waste from BRC as well as from T.A.P.S. Now this is the expansion part. It's almost of the same area, almost of the same. And now total area is something like 25 hectares. For this, the first phase which is being planned or which is under execution now, only for this purpose, this much of battery will be filled. Subsequently, as the waste comes over a period of 25 or 30 years or 40 years, then subsequently other areas will be filled up. So this boundary wall got constructed with acquisition of this additional area. By that time, this provision came up, and we started reviewing in addition for this design for how to plan and execute the design of a flood hazard for this expanded SWMF. In addition to this burial facilities, this premise also have some structures also. This is where one AWTSF alpha waste transistors facility is there, which is again a separated structure. One more separated structure is coming over waste processing facility. Similarly, for the handling of this waste which is coming, solid waste which is coming, there are facilities over here, and these all infrastructure places are there. The burial grounds are on this side. So we had to account for all these facilities which are coming over right now and in the future with this revised codal provisions. I'll just give a brief description that actually this additional expansion is of the order of 2.25 hectares. So approximately 25 hectare land is there. In addition to burial facilities, there are other structures which are safety related as well as non-safety related. And the ground level was sloping. It was like starting from almost 10 meter to and going down to up to almost 5 meter to extreme corner on north side. The site has to releases its drainage to on the western side at two places. I'll just give much more detail after a few slides. So there are two number of outlets for existing SWF, and we have to planned in such a way that those outlets, numbers of outlets are not increased with a higher, larger area as well. So we started implementing the design provisions, and the design basis flood level which has been recommended for this site for that annual frequency, as I mentioned, there's for same as per with T.A.P.S 3 and 4, that is early nuclear reactors. So that is coming 8.33 meter above mean sea level. That means the entire site now has to be at this level or higher, 8.33 meter or higher. So we carried out the rainfall analysis, and the design basis for the drain has come out 136 mm per hour. With this, the challenge was that the initial fund allocation was only for the initial part, that is of a first phase. But if you have to raise the site, that entire cost would have been beyond the sanctioned amount, and we have to maintain the same number of outlets, as well as to, if you do something now and then subsequently do it, there will be a lot of reconstructions and redoing the things, unnecessary wastages. So how we tackled that, we divided the entire area in 3 zones. The 2 outlets which were there, that was taken outlet number 1 here and outlet number 2 was here. So based upon the contours and other things, it was designed such a way that outlet zone 1 where this is everything is released to this outlet. Zone 2 was given for entire area, another outlet where entire load can come over there. Now we devised the 3rd zone also, which we named as a green zone. That was a patrolling road. Reason being that if we raise the entire thing up to 8.4, now this area is up to 5.3 or something like that. So then raising to that design basis flood level, that grade level, would have required filling of this area up to 2.5 meter, and the already constructed security wall would have gone below that level. So that means we would have reconstruct those things which were recently constructed at that point of time. So what we did, that we segregated it, that we kept as a green zone which can release its drainage to normal public domain area. Rest of the drainage which is coming through the burial grounds are controlled drainage which are under monitoring aspect also. So these 3 drain zones were planned. The drains were planned in such a way that as the developments are happening, this building is coming over, almost getting constructed now. So we planned the drains in such a way that the downstream part, this we designed as a new drain or an RCC duct to take care of entire load. It was designed in such a way that as we developed the...
Sir, please conclude.
Yeah, I'll just finish it up. This drain, this will take care of entire load. As we develop, supposing now this area is filled up, we have to develop this area, we just raise it up that level, we construct this drain, connect it to here, and then entire thing will be systematically developed, so that a module kind of design, after completion of filling of this area, now whichever the pocket or whichever the sub zone we take up, we raise that part only, support with this drain, then entire design basis perspectives are made. That is how we met this design requirements of next 30-40 years. The things can be developed without putting any additional expenditure or unnecessary expenditure at this point of time. I think I will just skip those parts. These are regular thing kind of civil engineering designs, and it was found to be in pure design basis cases also examined, and it was found to be safe. So that's how we wanted to share with the delegates that how we have carried out this design for a low-level waste with long-term perspective without putting too much load on the financial aspect, as well as meeting all the design requirements. And thanks for the patient hearing.
Now the session is open for discussion. In the absence of questions, we thank the speaker. Thank you.
Thank you, Chairperson. Thank you, delegates.
I invite to speaker and requesting to chairperson, please give a memento. Thank you.
Now we call upon the next speaker, Mrs. Khushbu Singh, for her presentation on engineering scale demonstration on sequencing process for technetium removal from LLW at BRC Tarapur. At the 8th minute, there will be a bell. Just please take care.
First of all, good evening all of you, and myself, I am Khushbu Singh from Process Development Division, NRG BRC Mumbai. My today's oral presentation topic is engineering scale demonstration on sequestration process for technetium removal from low level liquid waste at BRC Tarapur. So these are the points that I will cover in today's presentation. Introduction, background, lab scale trials, and how we have moved towards pilot scale to engineering scale. So first of all, how the technetium is generated. Technetium-99 is generated in nuclear reactor during the fission of uranium-235. So it gives molybdenum-99 and it further decays and gives metastable technetium-99, and further with a half-life of 6 hours it gives technetium-99. So from nuclear reactor, this technetium-99 is coming in reprocessing plant, and it is distributed in various streams, HLW streams and ILW streams. And we know that during the treatment of HLW treatment and ILW treatment, it is not getting trapped there. So finally it comes in low-level liquid waste. And the problem with the technetium is that it is having a very high half-life of 10⁵ years and a high fission yield of 6%. And technetium is present in the form of pertechnetate, which is TCO4 minus. It is very highly mobile, so it can easily come into the biosphere, and it can easily uptake by the plant, animal tissues, and by the ingestion of the human body, it can concentrate in the various human body parts like kidney, throat, stomach, and can give prolonged exposure. Can prolonged exposure. These are some processes which are already existing and various countries are doing. The last process is the sulfide process, which is currently being used in LWTP Tarapur and ETP Trombe. The problem, why there is a need of adopting new process, because the current process which are being used in LWTP and ETP Trombe, it is not giving the sufficient DF. So in order to meet the final C discharge limit, we have to do lots of dilution and lots of dilution. So my division had developed a new process of sequestration of technetium-99 from low level liquids, and the benefit of this process is that it is a reductive co-precipitation process. So what we are doing, we are using a mild steel wool, which is easily available and it is very cheap. So this mild steel wool is corroding and giving the corrosion product of goethite and magnetite. So it is converting pertechnetate, which is TCO4 minus, into TCO2. So, and finally we are trapping that TCO2 in the crystal structure of goethite and magnetite. This is the beauty of this process. We have used mild steel wool. So in order to study the process parameter, this is a mechanism how the technetium is. So first of all, the iron which is present in the mild steel wool is getting converted to Fe2 plus, and it further Fe2 plus it converts reduces TCO4 minus into TCO2, which is a less mobile, and it precipitate with the help of Fe3 and comes into the solution. So in order to study the process parameters, we have carried out the lab scale trials. So we have varied the pH, pH2, 4, 6 and 8. We have seen that at pH2, the rate of, we have carried out the experiment with tracer, which is technetium-99. So we have seen that the rate of technetium count is very good in the case of pH2, and as the pH is increasing, the rate of technetium count is with the time is decreasing. And so we have finalized and fixed the pH at pH2. Then we have observed the effect of volume of waste or solution and the ratio of mild distilled wool. So we have also varied V by M 100, V by M 200, 500, 1000, and as we are clearly seeing from the graph that as the V by M ratio is increasing, the rate of technetium count is also decreasing. So for further studies, we have fixed. We can also choose between 100 to 500. So we have right now we have fixed 100. So we have fixed pH2 V by M 100, and now we have seen studied the effect of the presence of oxygen. So we have seen that in the presence of air and oxygen, the rate of technetium count is very good. In very less time, we have observed that the technetium count is reduced significantly. But in absence of or in inert atmosphere, it will decrease, but it will take long time. So by doing all these experiments, we have fixed pH2 is the most effective, and V by M 100 to 500 we can take anything, and we are seeing that if we start from pH2, at the end of the process, the pH is raised up to near neutral, around 6 or 8. So after lab scale trials, these are the things that we have established. We have done the experiment on actual TRIX effluent waste at LWTP T.A.P. on 50 ml scale, and we are seeing that we have fixed the initial pH at pH2, and the pH has raised to up to pH 8, and the activity has reduced. Means we have taken 0.1 millicurie per liter, and after 2 to 8 hours of air sparging, it is drastically reduced. Means it is coming into background level, and pH has raised up to 8. So it has given a very good result, and now we have carried towards the pilot scale active trial at 40 liter scale. Here it is also we are seeing that the TRIX effluent activity is mostly because of the technetium 9 activity, which is 10 ki power minus 1. So by doing this process, we have almost get a DF of 700 with respect to technetium 99. These are the lab scale trials. But so finally adopting this process into the actual plant scale, we have carried out one engineering scale inactive trial at OTF Trombay. Actually, the objective of this trial was to see the effect of how the sludge has generated, how should be the design of the sequestration tank. So we have carried out several runs. Here only 6 runs results have been shown. So we are seeing that in every case, if we initial pH of the solution, if we start from 2, at the end after 4-5 hours of sparging, it reaches near neutral, and we are seeing as the process with the same wool, we are seeing that as the process will continue with the same wool, the rate of pH increase will decrease with the increasing runs, because the reason of this is the passivating of the iron will take place. So after 2-3 trials, we have to replace or top up of the extra wool. And what should be the main objective of this process is that in lab scale trials, the sludge which is generated, it is very amenable, means it is very free flowing. But in the case of 100 liter scale trial, what we observed that after 2-3 trials, the drain pipe started getting choked, and what we did that we modified the conical tank design. We have placed one welded mesh where we can place our mild steel wool. So these are the some outcomes that we finally adopted in LWTP T.A.P. So what we have seen that the engineering scale, the after 2-3 trials, the drain pipe were getting choked, and the how should be the design of the tank. These are the outcomes of the inactive scale trials. And finally, after this is the setup. Mild steel wool looks like that. Initial fresh MS wool. After 2-3 trials, it get corroded. And for sparging, I have used ring spargeon and draft tube. This types of system is there. And after all these trials, I have developed an engineering flow sheet. So first what we will take the TRIX effluent, and we will maintain the pH 2. Anyhow, in the current process, previously they were maintaining pH 2 for their chemical co-precipitation. So we will maintain the pH 2, and after that we will place the mild steel wool with a ratio of 100:1 in a sequestration tank, and we will place feed the low level waste in the sequestration tank, and after 4-5 of sparging, we will see that the effluent activity and the supernatant activity is almost free from 99% of technetium is getting removed. So the free liquid, then we will do the settling, and from there we can directly discharge this effluent to the sea. This is the actual implementation at engineering scale at LWT Tarapur. Current till date, we have treated 185 meter cube of low level liquid waste with the, and we are getting a, initially we were not getting DF in case of chemical co-precipitation, but right now we are getting a DF of almost with respect to technetium 200, and overall DF of the plant is improved by 10. And now we have to, and initially with the chemical co-precipitation, for seed discharge we have to do 10 to 15 times dilution, and this dilution is reduced half. So, and this process is already being currently used. So, what we are saying, like if the activity, beta activity is -1, so initially with the chemical treatment process, even after the chemical precipitation, technetium 9 activity is going up to -2. But with this process of sequestration process, we are almost reaching to 10 to the power -4. So very less dilution we have to do before a seed discharge. And finally, the technetium which is getting converted into the pertechnetate to TCO4 in goethite sludge, and we are working on a new matrices development. Currently, we are in worldwide we are using cement for the sludge, for the co-precipitate sludge, but we have started working on the new matrix, which is geopolymers. Geopolymers is the inorganic covalently bonded amorphous aluminosilicate framework, and it is a highly, its durability is very far better than the cement. Is half compared to cement. Cement half-life is 300 years, but if you will see the geopolymers, its half-life, its service life is more than 1,000 years, and its leaching characteristics also good compared to the cement. Like in cement, we are getting 10 to the power -4 gram per centimeter square per day, but with geopolymers, it is better than cement, but we cannot say it is the best matrices. So right now we are working in this matrix.
I request the speaker.
Thank you. Thank you.
Pushpu, it's a very wonderful talk, because technician, you know, we are all struggling with that. And what is the percentage of loading of technetium in geopolymer?
Ma'am, it is 7%.
7%.
Yes, it is low compared to cement. In cement, it is 10%. But right now, what we have carried out some active scale experiments, so we are getting only 7%. We are trying to improve the loading. We are
But still you are working with phases and active systems.
Yes.
That's something very good. Session open for discussion. In the absence of any questions, I thank the speaker for the wonderful talk. Thank you.
I request chairperson to hand over memento to speaker.
I request the third speaker, a model for quasi-static perturbation analysis for 540 megawatt PHWR.
Good afternoon to all of you. I would like to extend my thanks to this organizing committee to extending and allowing me to show this work of mine. Here I will be discussing the thermal hydraulic coupling with neutron kinetics for quasi-static perturbation. By quasi-static perturbation, what I mean is these perturbations are slow, time-taking in nature. The lifetime or the cycle of this perturbation is of the order of 6 hours or more. Typical examples are refueling in a PHWR, or slow going power change, like a power increment from 80% to say 100%, which typically occurs after criticality, or sometimes due to some reasons or the other, if you have to decrease or increase the reactor power as per our operational requirements. So first I'll introduce you. It's a T.A.P.S 3 and 4 because I am currently working as a reactor physicist at T.A.P.S 3 and 4. So my work was predominantly related to 540 megawatt PHWR units of Tarapur. So these were the first of a kind indigenously built 540 megawatt reactors. The first criticality was in 2006 and 2005 of Unit 3 and Unit 4. So up till now, TAPS 3 has completed 12 full power years of operation, and TAPS 4 has 12. So cumulatively, we have accumulated and experienced 24 reactor years of operation. Uh, so what is the status of coupled core development worldwide? See, in recent years, this has been actually a phenomena which has been started. People have been started working seriously in this field in recent years. One of the main reasons was that these coupled codes take enormous amount of time. Because what happens is that these codes have two parts. One is the neutron kinetic part, and the second part is the thermal hydraulic part. Initially, what people did was they did them separately in modular structure. Means there was one group which was completely involved in neutron kinetics. There was another group which was completely involved in thermal hydraulics, and they used to exchange data via some soft files or like that. So the attempt to couple them was very time taking, because these two individually were also very computer intensive. So the coupled code itself typically used to run for more than 48 hours or 72 hours to give a viable result for one phenomena. Right now, advancement in computing technologies, new numerical and mathematical models have become available, and access to even more powerful desktop computers. These results are now taking less time. But still then, some of the results I will show you in the further slides. For one particular refueling perturbation of a single channel, the complete coupled code takes about 1.5 hours. So if I take one channel as a representative for one zone, and the reactor is in 14 zones, so for a coupled code analysis for one channel per zone, I will need approximately 2 into 14, which means 28 hours still. But this is far more improvement as compared to earlier, when for a single channel simulation, we used to take 72 hours or even more. So these coupled codes are very important because these are needed for the life extension and operating nuclear reactors, for the safety analysis of new and innovative reactor designs as well. Because earlier coupled codes were segregated and modular in nature. Now they have become very much necessity for innovative nuclear reactor designs, where we have to go to regulator and establish for the safety in the case of passive you can say passive safety features, like for natural circulation, or even if there is a loss of coolant, still the thermal hydraulic properties of the material is such that the reactor can be safely cooled down or it can be shut down. So the coupled code development is an exciting new area of research. There has been a lot of work going on. In US, it is called for advanced simulations for the light water reactors. This has led to the MOOS project. This is freely available. What is the beauty of this is they have allowed access to everybody for all these codes, so that everybody can understand, try to modify, and use it as their own requirement. Similarly, is the NeuroSafe project in Europe, RELAP AR for ASWR in India. In our work, we have coupled the core physics with CFD code named OpenFOAM. It's an open source CFD code which is being used. It is completely, the complete source code package of this code is available open source. So anybody can download and understand the mechanics and the solvers. The another component of our work is the use of a Salome platform for generating the mesh. I'll show you one of the meshes, how complex a mesh is needed for a proper CFD simulation. So here we have presented a quasi-steady state. The transient state I have not, right now I am not showing, because then the presentation would have been very long. So this is a typical bottom-up architecture of a quasi-steady state. Here this is, Triveni is the neutron kinetic solver, OpenFOAM is the CFD solver. Both of them have been coupled, where this Triveni gives its data to a characteristics calculator for temperature, power profile, bundle power profile, channel power profile, the flux profile of the core. OpenFOAM has a solver called OpenFOAM Temp. This FCCal and OpenFOAM Temp, both of these codes have been written and developed by us, because in Triveni this was not available. In OpenFOAM also there was no such code. So we developed these two codes in these two particular platforms. Then we coupled them using a Python language coupling supercode. So this is like a supervisor. So this initiates the computations, calls Triveni, feeds input data, calls FCCal, takes the output data, processes it, and gives it to OpenFOAM for simulation of temperature, and then that is given as a coupled code. The output is detailed flux profile, detailed power profile, detailed bundle power and fuel temperature profile of the reactor. This is for a fast transient. Here the same thing is happening, but in case of in place of Triveni, we use a numerical analytical method. The beauty of this method is that it is solving the point kinetics code numerically. What I meant to say is analytically. It is solving the point kinetics neutron transport equations analytically, and then giving the results to be fed to ICOFOAM Temp for a coupled code. So I'll skip this. This is just the background of that. So mesh. first what we had to do is we had to understand how to model the geometry of the flow profile or the flow pattern of the coolant. For that we needed to numerically discretize the flow, means the channel containing the fuel bundles. So we investigated two different meshes. Both the meshes are geometrically and topologically closed. What I mean by this is that each of the individual numerical component of the mesh, if added, then it should give the net volume of the channel profile. That is what is meant by geometrically closed. By topologically closed, what we mean is the boundary of each mesh should contain only two cells. There should not be such that the boundary has an overlap of any other cell. So that when the information is transferred from one mesh to the other, then there should be only single boundary intervening between the two. So in the first mesh, the fuel coolant assembly geometry is discretized by splitting the assembly along the lines of symmetry of the fuel. The splitting lines are drawn from the center of the adjacent fuel elements. The result is a hexahedral mesh. In numerical solutions, hexahedral mesh is considered to be the best form of discretization, because here you can easily implement a Cartesian solver and still you will have very small numerical error, because all the mesh elements, the mesh surfaces will be nearly perpendicular to the interface. So the current you need not scale the current, or you need not, you can say, modify the current with any numerical approximation. In the second case, the assembly is repeatedly subdivided into smaller regions. I should better show you the figures. So this is the first kind of discretization. Here, this is very fine and hence it is showing so blur. I tried to make it sharper, but it's very fine mesh. It is still very fine as compared to this one. In this, you can simply imagine that in these lines, the distribution is of the order of 147 plus. Means approximately 150 cells are in this line. The total mesh size of this one is more than 7 million. For this, it is of the order of 2.5 millions. And these holes are actually the fuel elements. Since this is a fluid flow dynamics simulation, so these places are the fuel elements where there is no fluid flowing through the elements. Hence, we were only interested in the intervening structure from where actually the fluid is flowing. Yeah. Okay. So this is how this discretization was done. I'll quickly, this is the distribution of the reactor into 7 radial zones. This is the whole core. This is a comparison of the developed code. So this is how the implementation is done. I'll try to skip all that. This is a typical animation of how fuel temperature profile inside a pellet. These all were calculated through those codes. I'm just skipping for time. So there are 2 codes. This is how the time marching occurs. Numerical analytical solver gives its output to the open form. Open form then proceeds, and like this the time marches n plus 1 till the transient. So at the time n, or the time t is equal to t naught, the transient has started. Then till the end of the transient, the simulation will go on proceeding. So these are some of the results. This is the analysis of the mesh. So here we see that pressure. This purple colored line is for the pressure. This green colored line is for temperature. So this is the error, in the numerical error in the simulations. So we see that initially there is some oscillation in one mesh. The oscillations are not very rapid and they died on very early, and afterwards the error progression is very small. This is all smaller than 10 to the power minus 3. That was the error threshold for our simulation. So both the meshes were good, but here since there was oscillation in the pressure and temperature, so we opted for this mesh for further analysis. So that is what it is. This is the fuel temperature profile, typical fuel temperature profile. I've taken only two you can say the temperature measurement points, the fuel center line and the fuel periphery. So there is an order of difference of more than 900. Here it is approximately 300. So a 600 degrees Celsius temperature gradient occurs between the pellet center and the pellet surface. This is the typical, you can say, the simulation temperature profile. So after a approximately steady state has occurred, you will see that there is a very hot, this is actually green means low temperature, yellow to red is the higher temperature gradient. So this is the first mesh, this is the second mesh. In the first mesh, you will see that there is still there is some this thing, you can see the green places. That is because this mesh is very fine. So in this mesh, we had to run the simulation for a still longer time so that we could achieve the equilibrium profile. In the second mesh, the time taken was smaller. The other thing was that in this mesh, the time step had to be of the order of milliseconds. In the second mesh, we could take the time step of the order of seconds. So this is the typical for the 7 you can say the 7 channels, one in each zone for mesh 1 and mesh 2. We see that the error between the detector readings, the actual RTD readings and the simulations are very small. So this way we will able to, in Pineform we were trying to simulate whether if there is no transient introduced, then also the simulation should show that the reactor is stably operating. This is called zero power analysis. It proves that there is no numerical error in the simulations. So that why we were able to establish that okay, this is a stable numerical scheme, and we can go forward with this scheme for transient analysis.
Sir, please conclude.
Yeah, just now. I'm skipping for that only. So here there is a transient where no feedback is available. In this case, the fuel temperature feedback is taken into account. So after a very rapid power increment due to the fuel temperature feedback, we see that power starts to decrease and then it stabilizes at a point. These were all obtained from Pineform, and these all have been benchmarked. The mesh that I showed you earlier, that mesh has been published in an international conference by American Nuclear Society. They accepted that in their transactions. This particular result has been accepted for fuel temperature calculation at another international journal. So these were all benchmarked and accepted results. So we analyzed IPSWR LoRa, loss of regulation analysis, and we were able to show the results. So in conclusion, I would like to say that this is for quasi-static reactor operating state, TOCC, Triveni open form coupled code. The numerical analysis code is for transient like LoRa, and it is applicable for reactor core on a global scale. However, this is all for single phase. We are trying to do it for phase change as well, where the temperature is such that the coolant changes phase. We still are working on that. These are some of the references. Thank you.
Session is open for discussion.
Thank you, sir, for such a nice lecture, wonderful lecture. Actually, I would like to know that whatever code you are discussing here for the 540 megawatt electrical, and right now India is moving ahead for the some 700 and 1000 megawatt electrical. So what is your future line of action for your coding?
Yeah, as I told you, for this one is very much benchmarked and established for single phase coolant. We are working to benchmark it for the phase change of coolant, which is for 700, and for LOCA type of analysis where phase change is also occurring in 540 megawatt. So we are in the process of developing results and obtaining results and benchmarking them. So I'll also be presenting that in the future when we will again assemble, and I'll show you the results, whatever developments are afterwards.
Okay, sir. Thank you.
Any more question? I request our chairperson to honor speaker with our NUSUC memento, please.
The OP8 session, development of empirical relation for strength parameters of self-compacting concrete with manufactured sand.
Good evening, everyone. Myself, Kontesh Singh, working in NRPC NRB Tarapur. Today, I am presenting symposium paper on development of empirical relation for strength parameter of self-compacting concrete with manufactured sand. Today, I will discussing about need of self-compacting concrete, its benefit, and its mixed design. Finally, test result on green and hardened concrete and their relation of the empirical development of empirical relation for the strength parameter. Nowadays in construction industry, there is a requirement of a smaller size, high load carrying capacity structure, faster construction with less manpower. While achieving this, main difficulty arise in placement and compaction of concrete due to heavy congestion of the reinforcement and EPs. To overcome the difficulty, self-compacting concrete has been designed. So self-compacting concrete is an innovative type of concrete which does not require vibration for placing and compaction. It can flow under its own weight, completely fill the formwork and achieve the full compaction even if there is small space between the reinforcement or a small space between the existing concrete or shuttering. So for all this difficulty, self-compacting can be used. And this two photograph exactly show the requirement of self-compacting concrete, because from here we can see that there is no enough space for proper placement of the concrete, as well as if we are using the conventional concrete. In that case, we need to introduce needle vibrator for compaction of concrete. So here no enough space is available. In that case, only self-compacting concrete will provide the innovative solution to this problem. Similar case were also present in the NRPC, where we were facing lot of challenges in placement and compaction of concrete due to heavy congestion of reinforcement, EPs and their interferences. Now I'll discuss different thing for self-compacting concrete. Like here we have seen that self-compacting concrete we are discussing for the congestion of the reinforcement and EPs. Now we'll see where self-compacting concrete has been used due to SAP constraint, as well as there is a limitation on the construction joint. There is a ventilation duct in one of our block of NRPC, which is coming from vault of 6.2 elevation to the 11.3. Now if you look on the section of the ventilation duct, there is a seizure joint is given which divide the construction of the duct in two parts. First is lower U portion and the upper is slab portion. The first U portion will be casted and later slab of the duct will be casted. And there is a SS lining inside. To cast the U portion of the duct, the shuttering arrangement is shown here. So the only shuttering arrangement is the only for placement of concrete in the lower horizontal base of the duct, only way to pour the place the concrete is pouring from the top of the duct. In this way, concrete will be poured. But here we have two problems when we are using the conventional concrete. First is that there is no way to ensure proper placement of concrete in the lower base horizontal portion of the duct, which is the base of the duct. Because for this portion we are totally blind. We don't know whether it has filled with the concrete or some air pocket has been left. And second problem is that we are also there is no also way to ensure the proper compaction in lower horizontal base of the concrete, which has a width of 1.35 meter, because needle vibrator we use needle vibrator for compaction. But while lowering the needle vibrator, only we can lower to the vertical portion of the duct, so the mid part of 800 mm will be remain unaffected from the compaction, so we can't ensure while using the conventional concrete. So, need of self-compacting concrete. To find the solution for presence of highly congested reinforcement, heavy congestion of EP, SAP constraint and restriction on construction joint, which I have discussed just. Benefit of self-compacting concrete. Easier placing of concrete, improved durability, because the degree of compaction will be improved, so durability will be improved. Non-requirement of vibrator, better surface finish, faster construction, reduction in site manpower and freedom to design the thinner section. Now we'll look upon the mixed design, how self-compacting concrete is designed. So mixed design is a process of selecting the suitable ingredient of concrete and determining their relative proportion, with objective of producing the concrete with desired workability, desired minimum strength, desired durability and as economical as possible. To start the mixed design, first we should know the material ingredient property, for which all required tests were conducted in our laboratory, and once the test result came, we designed based on the ingredient property, we designed the self-compacting concrete, and once the mixed design was finalized, trials were continued. Trials were continued till the desired strength, desired minimum strength, desired durability and economic was achieved. So finally adopted mixed design for M40, M60, M80 grade concrete is listed here. Once the mixed design is fixed, then we'll test the concrete for workability and strength parameters like compressive strength, flexure strength, modulus of elasticity, split tensile strength and all. The first we'll look upon the test on the green concrete. So for green concrete, workability tests were conducted. The workability of self-compacting concrete generally ensured by mainly three factors: filling ability, passing ability and resistance to segregation. So filling ability is the ability of self-compacting concrete to flow into and fill the all space within the formwork under its own weight. This ability is ensured by the slump flow test. We can see here the truncated cone in which concrete will be filled and it will slowly lifted, and a concrete will allow to flow in circular portion, and finally at the end diameter of the circle will be measured, and the time taken by the concrete to reach the 500 diameter also measured, which is known by T50 centimeter. And second is the passing ability, is the ability of self-compacting concrete to flow through the tight opening, like a small space between the reinforcement without blocking or segregation and all. This ability is ensured by the U-box test and L-box test. We can see there is a U-box in which there is a sliding gate in between that. There is two limb in U-box. So first limb concrete will be filled up, and for to to mock up the site scenario, here congestion has been placed with the reinforcement, like there is a small space between the reinforcements are there, like 20 mm, 25 mm. When the gate will be lifted up, the concrete will be allowed to flow from here to up the second limb. And so if the concrete can be flowed, the height difference between the two limb after opening the gate should not be more than 30 mm as per codal provision. And this second one is L box test, in which there is also a gate. First that gate will be closed, and first the concrete will be filled up in the vertical portion of the L portion, and then gate will be open and concrete will be allowed to flow in the lower horizontal portion of the L. So once the concrete will be flow through the dense congestion of the reinforcement over here, then the height of the concrete here at the junction of L and the end of the portion will be taken, and the ratio should be 1.8 to 1. Now third factor is resistance to segregation, is the ability of self-compacting concrete to remain homogeneous in composition during transportation and placing. This ability is ensured by the V-funnel test. For V-funnel test, we just use the V-funnel in which there is a gate at lower portion which will be closed, and this will be filled up with the concrete, and this gate will be open and will allow the concrete to flow outside the funnel, and time will be measured. Again the same concrete will be filled up in this funnel and will wait for 5 minutes, and again it will measure the time taken by the concrete to empty this funnel. The difference between these two times should not be more than 3 seconds to ensure the resistance to segregation of the concrete. These are the few pictures which has been taken during the testing of self-compacting concrete at site. This is for slump flow test, this is for L box test, this is for U box test, and this was for V funnel test. Now we'll look upon the result and discussion, where now once the slump workability of self-compacting concrete has been identified, now we'll look upon the strength parameter, like this is the result of workability of self-compacting concrete, for which we just discussed about slump flow, T50 centimeter, L box, U box, V funnel, and V funnel at 5 minutes. Here the test result for all three grade of concrete is mentioned, and they range from the various code like ACI, FNRC, and 10262 is mentioned, and all test results are in line with the various codal provision. Now test result and conclusion. So the developed self-compacting concrete was also tested, and tested for compressive strength, split tensile strength, flexural strength, and modulus of elasticity. All test results for three grade of concrete are listed here, and their requirement as per Indian standards is also listed here, and all test results are in line with the IS codal provision. Here we have tried to predict some empirical relation for a split tensile strength, like Ft is 0.07 FCK, which depends upon the compressive strength of the concrete, and flexural strength also 0.73 roots FCK, where ISO code has given 0.7 root FCK. We have derived to the we have come to conclude that is more than the IS code requirement, and modulus of elasticity is 4650 root FCK. Finally, I would like to express my gratitude to Sarbit sir, Project Director NAPC, and Dr. Praveen and Mithun, the Head Civil Construction Section, for their support and technical guidance and motivating to entire project work. And I also would like to express my thanks to my parents, family members, all of my colleagues to their motivation and continuous supports. Thank you very much.
I sincerely thank the speaker for keeping up his time first. Thank you. Session open for discussion. I have a question.
Yes, ma'am.
Where do you get the M sand from?
What, ma'am?
M sand.
Manufacture sand, ma'am.
Yeah.
Just we are getting from the locally, ma'am. Locally, where we are aggregate source like Vada and different Nagsari and all, ma'am.
I asked this question because the M sand composition, will it change depending on the location?
No, ma'am. For that we do all the required tests for M sand, like grading and specific gravity and all. All tests are done before taking any sand from outside source.
Fine, thank
you. Okay, ma'am. Thank you.
I request our chairperson to honor a speaker with the memento, please. Thank you, ma'am.
The next talk is the online talk. This is the last one, which we missed in the previous session. We are trying to have it now.
You are now co-host. Velmurkan sir, you are now co-host. You can present your presentation.
Sir, now screen is visible, sir?
Yeah.
Yes. Good evening to all. I'm going to present the topic on the challenges in the qualification of hot cells for first reactor fuel reprocessing. Actually, this work was carried out as the part of the commissioning activity of the DFRP. So on behalf of that, I am presenting this work. So actually, this fast reactor fuel, this reprocessing plant handles the spent fuel of the high plutonium content as well as the high specific activity. When you take these solvent extraction equipments in thermal reactor fuel reprocessing plants, they go for the pulse columns as a solvent extraction equipment. But in fast reactor fuel reprocessing, because of the high specific activity of the fuel, we need to have some short contact time residence contactors. That's why we are going for the centrifugal extractors as the solvent extraction equipment. But this, when you go for the centrifugal extractors, this requires this remote operation and the remote maintenance during the plant operation. And also the sampling also has to be carried out for effective process control. So what here the plant design is these equipments are housed inside the specially designed the stainless steel containment box, and that containment box is surrounded by the lead and the concrete walls for the shielding, which is called a hot cell. Now, in the view of handling the high plutonium content, this containment box needs to be qualified for the alpha leak tightness. And as a whole hot cell, which has to be qualified for handling the radioactive material, the number of activities as a part of commissioning activities we need to carry out, like starting from the leak testing of the containment system and the radiometry of the hot cell for evaluating the shielding integrity and the performance testing of the equipments with water and acid TBP, then the demonstration of the remote handling equipments inside. So all the number of activities has to be carried out for qualifying the hot cells to be able to take up the radioactive operations inside. So here my talk is one of the activities, which is the leak testing of the containment box, which was carried out for the DFRP for the qualification of the hot cell, that I'm going to present here. For the remote operation and maintenance of these equipments, as I stated, like centrifugal extractors and sampling systems, this containment box, which is basically of the cuboidal shape, has following provisions like viewing window openings for operator to view inside what is happening and do remote operation maintenance. Then we have a lighting windows for illuminating light into the containment box. Then we have a master slave manipulators for carrying out various remote operation maintenance, and for in-cell crane, which is erected inside the containment box for aiding the remote operation maintenance, and various glove boxes has to be integrated into the containment box for for housing the drives for the in-cell cranes or material transfers into the into the containment box, or cable entries for requirement inside the containment box. Now I will show you the picture of the containment box right now in our DFRP. If you see the first picture, where we have the containment box of the sampling system, where you have the windows. One is a viewing window that is actually fitted with non-browning glass. Then we have a lighting window. Then we have a manipulator opening. When you see the right side picture, where we have the centrifugal extractors and the associated piping systems which are inside the containment box. And the last one on the left is the glove box, which is integrated into the containment box, which is basically houses the crane drive boxes inside for aiding the maintenance during a plant operation. Now, In DFRP, if you take, there are 6 numbers of containment boxes and 1 dissolver cell. So if you take a typical dimensions of these that is containment boxes, basically the first 1 is a contactor cells which houses the centrifugal contactors, basically of dimensions 8.7 meter by width 2.5 into height 4.5, basically approximately volume of around 100 meter cube. And then we have 2 numbers of sampling cells for the process plant facility, which is about a volume of 100 meter cube. Then we have samplings for the waste wall, which have a containment box which is of about 3.6 meter cube volume. And then we have a dissolver cell where we house all these everyday chopper, dissolver and centrifuge systems, which is approximately of volume 660 meter cube. All these systems has to be qualified for the leak tightness before putting into radioactive operations. So hence, as a part of qualification of hot cells for handling radioactive materials, the leak testing of all these containment boxes and dissolver cells along with the glove boxes has to be carried out to achieve the leak tightness within the acceptable level. Now, what we have followed for leak testing in these containment boxes and dissolver cell is, before taking for leak testing, we have done a physical verification inside the system, inside the box, where we traced all the pipelines and penetrations for any openings or discontinuity. And then we checked for the proper closure of all the openings of the containment box and the glove boxes. Then we have made all arrangements like the pressurization of the containment box, then the instruments for leak detection like pressure transmitters, RTDs for temperature measurements, all this integration, all these things. Then the main, after this one, works, this leak detection is mainly carried out on the outer surface of the containment box by pressurizing the containment box inside. And basically these methods are followed for the leak detection, that is soap bubble test, smoke test, and smoke test coupled with thermal imaging technique. Once we have arrested all the identified leaks, we have gone with the pressure decay method for carry out the final leak testing. This is the stages of leak testings. So we have carried out in 2 stages. One is a preliminary leak testing. In that, what we have done is all the window openings, manipulator openings, glove box openings, etc. were actually closed with the SS plates instead of actual glasses. Mainly because we can take this containment system to a higher pressure of the order 300 mm water column, that is gauge pressure. And then the major leak points, especially on the minor weld joints or corner joints, all these things, leaks were arrested. And then we have qualified the containment box structure in the preliminary leak testings. Once we have completed this stage, we have gone with stage 2, where we replaced all the SS dummy plates with the actual non-browning glasses in the lighting and viewing windows, and actual glass panels and glove ports with gauntlets in the glove boxes. And in manipulator openings, we replaced with actual bootings and alpha type cable flanges, etc. So here in confirmatory, the main leak detection is mainly confined with the glass seating surface on the frames. And here the leak detection we have carried out with maximum pressure. We have gone up to only 50 mm because of the glasses. So the main challenges we faced in stage 1, that is in preliminary leak testing, is because this containment box is of large volume with large dimensions, as well as this containment box has extends from one floor level to another floor level. So because of this, the number of challenges, that is the location of leak points, detection on the surface, that is one thing. And another one is these containment boxes are housed inside the concrete wall or lead wall. So what this one has is because there is a very minimum gap for access for a leak detection. And also at the top of the containment box to the concrete wall, they have a very low headroom. So the leak detection is one of the main challenging one. And another one in the preliminary leak testing was there are certain locations where we cannot be able to access and do any soap bubble test or whatever. So what we have done is we have used this thermal imaging technique where we have generated smoke inside, and then wherever in inaccessible locations, because of this the smoke which is coming out from the containment box, because of the temperature difference between that with respect to the ambient, we used the existing concrete openings in the cell. With that, we have introduced this thermal imager, and then we have located the leak points, and then we have arrested. So after arresting all the leak points, in preliminary one, we have carried out the leak testing and we qualified the box, and then we have subsequently taken the confirmatory leak testing. In this confirmatory leak testing, the main challenge is we have put all seals with respect to actual plant conditions. Like we have put the windows with non-browning glass, lighting windows, manipulator booting, glove box with glass panels, glove ports, gauntlets, everything. So because we have put the glass, there is no, because we have to be very cautious about the pressurization of the system because of safety considerations. So the number of safety features were incorporated for carrying out the leak detection. That is, pressurization is stopped. That is interlock for air supply cut off at 50 mm, the water column pressure. Then we have a passive system water seal. So if any
I
pressure goes
request
beyond
the
that,
speaker to conclude.
Oh, yes, right. So water seal. So this thing, a main challenge in this is that arresting the leak points on the glass seating surface on the, because this the planarity has to be maintained for proper glass seating. After arresting all the leak points, we have conducted the leak test and we have qualified the box. So as a DFRP, 6 number of containment boxes and 1 dissolver cell was successfully leak testing was done and it is completed. And this activity was carried out as a first time effort, which are unique to fast reactor fuel reprocessing plants. Finally, I would like to acknowledge our RPG mechanical team, RPG instrumentation team, RPG electrical team for their constant support for this work. Thank you for your attention.
Thank you, Dr. Velmurugan, for your nice presentation on the leak testing system. It's open for discussion.
Escape.
If no questions, so I request our chairperson to give a memento to Velmurugan, and on behalf of Velmurugan, Mr. Kankan Patra will receive. I request chairperson to.
Velmurugan.
Thank you.
We thank the organizers for giving us this opportunity. Thank you.
Thank you, Session Chair and Session Secretary, for successfully conducting our last technical session. And I extend my thanks to oral contributory research papers for presenting their work in this symposium. May I now request Shri R.B. Bhatt sir to present a token of our appreciation to Session Chair and Session Secretary. Thank you, Bhatt sir. Now I request you all to give some time, at least for 5 minutes, to prepare this stage and ourselves for the last part, that is the valedictory session. We'll assemble around 5:25 over here. In the valedictory session, we have prizes to the best posters, a small panel discussion for 5 minutes, and a felicitation program to Shri Sanjay Pradhan sir, and finally a formal vote of thanks. So we'll assemble at nearly 5:25 or 5:30, around that. And I ask all of you and nearby to join for this last session.
hello, 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 check. Huh? Hello, 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 hello. Hello, hello. आता बघ. Hello, hello, hello. Okay, okay ना? Hello, 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 hello. Hello, hello. Hello, hello.
Hello, check. Hello, check. So very good evening to all of you. Finally we are at this time, we are at the last session, which is the valedictory session. Proceed with, I request Sri R.V. Bhatt sir, Chairman NCAS Chapter Tarapur, to accompany Sri Dae-Brns sir, HPC NRD, Director T.A.P.S, Sri P.G. Dae-Brns sir, Sri D.B. Sathe sir, Sri Dae-Brns sir up to the dais and grace this valedictory session. Respected dignitaries on the dais and in front of me, dear delegates of NUSUC 2022, on the behalf of NCAS Tarapur chapter, I thank you all for becoming part of this symposium and making it a grand success. Proceeding further with the first part, we'll start with the prize distribution to best posters. We have received around 94 contributory research papers, out of which 8 we have made converted into oral presentation. Remaining 86 were presented either in offline mode or via online mode. So we have made some committees for evaluation of the posters. For the offline evaluation of posters, it was convened by Shri P.G. Dae-Brns. Thank all of them for this evaluation of posters. Now for giving away the prizes, I would like to request the Sanjay Pradhan sir to give away the prizes to our 4 best posters. For online mode, the best poster award goes to poster number ART 4. Title of the poster was Performance Evaluation of High-Speed Centrifuges during DFRP Commissioning, and the first author was Saurabh from IGTAR. So Saurabh, somebody may receive on behalf of Saurabh from IGTAR. Somebody may receive. We are actually running short of time. You can receive. Saurabh. He's from he is Mr. Saurabh and he is related to K. Anand Shivan Sarsu. Thus, now for offline posters, what he has decided, ART number 19. So the title is Vacuum Distillation System for Recovery of Pure TBP and N-Dodecaine from Spent Organic Solvent in INRP. The award goes to Mr. Mangesh M. Malusare. Mangesh sir, please come. The third one in the sequence is SSMP 5. title is Non-Dispersive Solvent Extraction for Bulk Purification of Strontium Nitrate Solution Using Hollow Fiber Membrane Contractor. The first author is Pranshu Parikh and it is related to NRG group. Pranshu Parikh. Somebody may receive. Qureshi sir may receive. The last offline poster award goes to SSMT number 6. Title is Development of OPLA AF Force Field for Reprocessing Applications to Mr. Arya Das. Mr. Arya Das, you may receive. Moving on to the second part of this last section. A quick panel discussion. We have planned for 2-3 minutes only. Mostly we would like to take only the feedbacks and the improvement suggestions from all of you. If you have one or two, you can be taken up, or to further improve upon the conduct of NUFOC of this symposium. Now this panel discussion is open for any suggestion from your side and from the panelist side.
NUSUC-2022 has covered a very vast topic, and with the current times, most of you by now might have seen that reprocessing, waste management and fuel fabrication of PHWR fuel is quite well, I will say ki we are getting the good delivery. It's not that we have conquered everything, and lot of things still need to be improved. And such a symposium is very much a place where we will take the challenges and know the what people are doing in different groups of BRC and different DAE units, and utilize the expertise of the relevant persons or the groups, and way ahead for our front. For FRFCF and other these facilities which are not yet proven, definitely a lot of things that need to be done and proven. We have already done many things. IGCAR has already demonstrated many good things, but when it will come to the field scale model, definitely much more challenges may come, and we may have to conquer them. We all know FRFC will be having much more dose rates and troubles. So such knowledge sharing is very much required, and I would wish that the frequency, if it can be reduced, and if we can have maybe say yearly or 2 yearly, we may focus relatively more on say 1 or 2 group rather than having this long group. That may be relatively better. BRNS, I think, can approach and they can use the frequency. That's what they also had indicated.
On the delegate side.
Thank you, sir. This NUFOC, nuclear fuel cycles.
mainly it caters uranium and plutonium as a fuel. And in bulk handling facilities, accounting of these materials are very encumbered. So what we believe that if you can arrange some expert talks on this, what are the latest techniques, what are the latest model we are using to find out accounting as well as the error associated with accounting. Because this plays a very important role basically in the bulk handling facilities where significant amount of SNMs are measured and a small error can cause the SQ level. So if you can arrange some topic on that in your next symposium, it will be greatly helpful.
Dr. Parsati, you yourself is an expert. And so the NUSUC was open for NMM and the activities for that. Definitely we can invite more, and Amrit Prakash is also there, and we can invite more people from other place. But definitely it is a very relevant point, and I hope no paper had come for that. Otherwise today have been selected.
Sir, I have one small suggestion. That is, as Pradhan sir already told, we can reduce the frequency like that from 3 years to 2 years or single year. And I also suggest that then it should be increased by one more day. Instead of 2 days, if it is possible, future symposium we can organize for 3 days. And one major part of the nuclear fuel cycle in the all 3 last seminars we have missed, that is the UCIL and role of heavy waters. So Uranium Corporation of India Limited is a very front end, and if you can add some speakers from heavy water road, I think that will be nice. Then really we can complete the entire cycle in future seminars. So that's my suggestion.
It can be taken care in future programs.
Thank you.
Instead of 3 days, I will suggest you have 1 day team meeting and you arrange such 4 team meetings in 1 year. That will be much better.
To the point what was raised by Dr. Anjit Kumar, I would like to add, we have approached UCIL as well as to Atomic Minerals Directorate, Hyderabad. Because of some important assignments, they could not come for the invited task, but we already have approached to them. Any more questions, or otherwise we'll move ahead? Or suggestions, or from the panelist side some suggestions?
From my side, it is not a suggestion, rather it is an observation. What I have found, all of us who are here, we have become conscious of the waste being generated by the various facilities, and due to that awareness, through that poster presentation and talks, I could understand that due to that consciousness which has developed now, we are moving in that direction, how to deal with that radioactive waste. And in that, whatever work is being presented, I request youngsters to take up some reaching to the end point to get it implemented, so that we proceed now in the waste management side also. There are a lot of things to, and as Dr. Amrit Prakash was telling, reuse, recycle, this 3R concept he had given. In that direction we have now started thinking and working. So I request the people who are in that field should now work more rigorously, so that we get something positive coming out of those works. Thank you.
That's all for panel discussion, I think so. So now I'll go ahead with the further part. Now, as we know that Sri Sanjay Pradhan sir is superannuating this month only, after serving this department for more than 3 decades. He had a spectacular career in this esteemed department institution. He is a mechanical engineer from 27th batch of BRC Training School. He has served on many important positions in the department, starting from DIC, Section Superintendent, Plant Superintendent, Chief Superintendent, and as on today, the Deputy CNRB and Director GSO and Executive Director, Constructions and RB. Besides this all, he has chaired T.A.P.S chapter from 2016 to 2021. Under your able guidance, T.A.P.S chapter could organize several lectures, several other activities, and NUSUC-2018. For NUSUC-2022 also, he has served on the position of Chairman of Symposium Organizing Committee and extended his help and guidance as and when required for conduct of this symposium. Sir, in view of your immense contributions to T.A.P.S Tarapur chapter, the Executive Committee of T.A.P.S Tarapur chapter is pleased to present a Lifetime Achievement Award from T.A.P.S Tarapur side, which carries a memento which will keep on reminding you all of regarding ourselves. Just before that, I request Shri R.B. Bhatt sir, who is the present chairman of T.A.P.S Tarapur chapter, to present a flower bouquet to Shri Sanjay Pradhan sir. Shri R.B. Bhatt sir, may please present token of our love to Shri Sanjay Pradhan sir, a shawl, a cap and a Shrifala. And now please hand over the Lifetime Achievement Award from T.A.P.S Tarapur chapter to Shri Sanjay Pradhan sir, which is a token of our gratitude and our respect and our love to you sir. And thank you very much for kindly accepting our memento sir. Now from the dignitaries on the dais, if they wish to convey some message on this occasion, they may come please.
Pradhanji and dear friends, I have taken over this chairmanship of T.A.P.S last year only, and Pradhanji has always guided us, and this new 22 is a result of that. And I think our team of T.A.P.S Tarapur, they have done very well. And on the behalf of Tarapur T.A.P.S chapter, I wish Pradhanji a very happy and healthy life. Thank you.
I wasn't knowing where to fit this, but some quotes are there from famous scientists and related to science. Just actually I have collected and I found it relevant. So just I will take 2 more minutes. The history of science is characterized by interplay between scientific acumen and serendipity that led to discovery of X-rays by Ranjan as well as observation from microwave could melt a candy bar. The word serendipity means the occurrence or discovery of something by chance. In that connection, these are the quote by French microbiologist Louis Pasteur, said, in the field of observation, chance favors only those who have prepared minds. And I feel the aim of such conferences is to prepare mind for getting these discoveries. Thank you very much.
Mr. Pradhan, Mr. Bhatt, Sri Gayanji, Mr. P.V. जी, प्रधान जी के साथ में मेरा जो इंटरेक्शन था वो काफ़ी पहले से है। मैं तारापुर में था, मैंने भी यहाँ 33 इयर्स रहा हूँ। प्रधान जी हमारे नेक्स्ट टू नेक्स्ट नेबर थे। मुझे याद है उनके यहाँ जो मेरा आना जाना ज़रा ज़्यादा रहता था, उनके यहाँ बेलपत्री का पेड़ था। मेरी मिसेज कुछ पूजा वूजा करने के लिए तो मुझे सवेरे 6 बजे बेलपत्री तोड़ने के लिए प्रधान जी क्या जाना पड़ रहा था। तो एक बार मैंने ऐसे ही नॉर्मली आई यूज्ड टू गो, आई विल आस्क एंड देन गो। तो प्रधान जी बोलते थे अरे पूछने की क्या ज़रूरत है, दरवाज़ा खुला रहता है, आके लेके जाओ। तो मेरी थोड़ी हिम्मत बढ़ गई। फिर मैं बेलपत्र कभी शाम को कभी सवेरे लेके आने लग गया। तो ये तो हमारा फैमिली इंटरेक्शन हो गया। लेकिन ऑफिस में जो मुझे प्रधान जी का जो बहुत अच्छा एटीट्यूड या उनका अप्रोच पसंद था, वो बहुत स्ट्रेट फॉरवर्ड है। ज़्यादा बात को घुमा के बात नहीं करेंगे। ही विल कम टू द पॉइंट एंड ही विल बी वेरी स्ट्रेट। 2-3 डिसीजन जब मैं था यहाँ पे TAP में कुछ लेने पड़े थे जो मैंने प्रधान जी से डिस्कस किया था। ही एग्रीड टू दोज डिसीजन। आई विल नॉट डिस्क्लोज व्हाट दोज डिसीजंस आर, बट ही एग्रीड टू दैट। So that time I felt, yes, approach has to be like Pradhan ji. If some decision is to be taken, they need to be taken at that time. And he used to do that. That was the kind of nature which I always liked. And whenever some advice in official matter, he became GSO director also. During that time also we had a lot of interaction. But one thing was always there. Overall, you will see that most of the DRC Tarapur community is benefited by his decision. But he was always taking care. So at the end, I also wish him a very, very great time in future with his family. And I wish from this forum for his daughter also a grand success, but her future endeavors she is looking for. Thank you very much.
Today's speaker, Pradhan ji, Pradhan sir, various of participants, and all my colleagues from different units, ladies and gentlemen. Today, after 2 days symposium, we are the last stage, and we are here to say our few words regarding Pradhan. As Mr. Dae-Brns have bola, that he is very straightforward. I have also seen in many occasions
is very straightforward. He will tell straight away what is required. When I saw him first time, that time I was in T.A.P.S. I have the operation in charge, and T.A.P.S went there as a RIT member. That is the first interaction with T.A.P.S actually. And as a RIT member, within a short time, he found out many points. Not all the points in our ear. He found out all the points and he told very correctly what are the problems are there and all those things he find out within a very short time. And he visited the plant, all the areas. That is also very quickly. It is not taken much time to visit the areas and then come out with a list of things, not like that. It came very quickly. This thing. And I have seen very different safety committees. He gives a very practical solution, seeing both the regulatory aspects as well as the plant aspect also, so that both things are balanced and it will be benefiting the plant as well as the regulatory aspect will not be bypassed. And as Harsha told, he has occupied many positions in the department, and we all know wherever he has taken the position at whatever may be the level, each level he has brought the department into next higher level, higher level. He is the person who has shown and proved that this reprocessing in India, it can give the rated capacity of the plant, and in fact this is more than the rated capacity for tenure. It is a record history in reprocessing. So with this, I wish him a successful and peaceful return life with his family. Thank you very much.
Post a 2 days seminar when everybody wants to these fellows are delaying you are. So I just wish the NITESH as well as all of you for a better future, and if it is do come and we go, not only that I will be going from organization, everybody of us to go from there also. So the organizations, the society, country, they have to continue and progress. So next generations have to learn and keep the flag high. I wish you all for that. Thank you.
Thank you, Pradhan sir. So kindly, I am coming on to the formal vote of thanks. On the behalf of the N.U.S.C Tarapur chapter, I thank members of Symposium Organizing Committee who has worked quite hard in making this event a grand success. I thank DRC, NPCIL Tarapur for infrastructural support, Dae-Brns for financial support, management for the overall help they have provided. Especially thank to Dr. Amit Prakash sir for the guidance during the conduct of this symposium. I thank all the agencies involved over here that helped in organizing this event, transport, accounts, management, and especially E&I is making this program going into air. So finally, I pay my sincere regards and thanks to my entire N.U.S.C team Tarapur, N.U.S.C Mumbai, who have left no area to point out and put their all efforts to make this NUSUC-2022 a memorable event for all of us. So from NUSUC Secretariat 2022, goodbye to everyone. Hope to see you all in NUSUC 2025. Till then, take care of yourselves. Thank you very much. Thank you, everybody. There is one announcement. A high tea is arranged for all the delegates and participants. And buses to Mumbai. Bus to Mumbai may go around at 6:30 sharply. Thank you all.